the ICRA 2021 full-day workshop on teleoperation of dynamic legged robots in real scenarios. This workshop is supported by European Andy Project, European SoftmanBot Project, and iFeel Technologies. During this workshop, we are trying to understand how we can develop teleoperation systems with different legged robotic platforms in order to perform dynamic tasks in real-world scenarios. For different applications, today we are honored to have many very well-known experts and speakers from academia and industry to cover different aspects of this topic. First of all, I would like to mention that this workshop is a follow-up and an extension of a successful workshop we organized at Humanities Conference in 2019 in Toronto, Canada on humanoid robot teleoperation. As an output of that workshop, we performed a survey on humanoid robot teleoperation, which is currently under review, which I invite all of you to read this paper, which covers many state-of-the-art aspects of humanoid robot teleoperation. Now, let me introduce you very briefly some of the motivation behind this workshop and the future promising application of robotic teleoperation, the challenges and opportunities behind deployment of such systems in real-world applications. One of the main applications urging robot teleoperation is in disaster response scenarios where the environment is potentially hazardous to humans. This need arose, for example, in Chernobyl, and as you can see in this video, in Fukushima Daiichi nuclear power plant crisis. As a response to these disasters, robots were needed to perform different tasks, including surveillance, search and rescue, and manipulation tasks. However, to do that, a robot needs to reach the point of interest passing possibly through a dynamic and structured environment. Therefore, different means of mobility, including bipedal and quadruped locomotion, wheeled robots, flying robots, or hybrid types might be required. In these scenarios, the mission requirement identify necessary robot features such as hardware reliability, communication protocols, additional hardware and sensors, autonomy level, and so on. Normally, in natural disasters, the time is very critical. Therefore, an important aspect to consider is the response time and the technology readiness level. Teleoperation of legged robots, despite being attractive, because of their agility and potential to operate in environments designed for humans, are still expensive and not affordable for many industries and research institutes. This inconvenience, in fact, has strongly limited their study to a restricted robotic community. Moreover, very often, either the robot hardware or underlying control software are not designed to comply with control failures.
I don't know if it's only me, but I no longer hear Kourosh.
Me neither. It's frozen.
Me neither.
Oh, okay. So this is the cool thing of the live. Yeah. So this is basically Kourosh is frozen right now. Probably is having some internet issues. So what we may do is that I'll try to somehow understand quickly what is going on, because I know that Kourosh is upstairs in the proper office for giving teleconferences, and I am not. And actually, I am working better than than where the Kourosh is. So I would kindly ask
He's right.
Kourosh. Yeah. Kourosh, we don't hear you.
No, we don't hear you.
No, we don't hear you. So probably it's better that you unplug your headphone. No.
Okay, do you hear me now?
Yes, with some echo.
Okay, stop the other call. Sorry. So probably it's better I don't also share my turn on the camera, since it might be the reason why it stopped. Okay, let me also share with you again the screen. You can see the screen, right?
Yes.
Yeah.
Okay, that's great. So, sorry for the interruption. Let me again to go to the slide which we missed. Probably it was here. Okay. Teleoperation of legged robot, despite being attractive because of their agility and potential to operate in environments designed for humans, are still expensive and not affordable for many industries and research institutes. This inconvenience, in fact, has strongly limited their study to a restricted robotic community. Moreover, very often, either the robot hardware or underlying controlled software are not designed to comply with control failures, the loss of balance, or wrong interaction with the environment, which can lead to a costly breakage. Nevertheless, the need to be telepresent or teleexist in another location raises in many situations. For example, COVID-19 pandemic has either canceled many conferences and meetings around the world and transformed them in virtual events such as this workshop. And the current substitution for such cases currently is to use communication medium, allowing the people to hear and see each other. However, using this means many social cues, which are equally important in social interaction, are not conveyed yet. And in many cases, human-robot teleoperation with anthropomorphic shape and motion similar to a human would allow for a better experience. There are many other equally important applications for a teleoperation that motivated us for organizing this workshop, including space robotics, telenursing, and data collection, just a few to mention. After this brief introduction of motivation and application of legged robot teleoperation, let me quote the definition given in a book of one of our speakers, Professor Tachi, about teleexistence. Teleexistence refers to the technology that allows the human to exist in a remote location through an avatar, experiencing real-time sensation from the remote side. In the literature, teleoperation refers to a human operator remotely controlling a robot, focusing mainly on performing a dexterous task in the remote location. We may use these words interchangeably since they are interconnected throughout this workshop. Moreover, following this definition, we may consider human and robot as a team with a common objective and different roles. Through the teleoperation system, we integrate the cognitive skills and domain capabilities of the human with the physical capabilities of the legged robots to perform a given task. Accordingly, we can identify a generic architecture for the teleoperation and teleexistence. We have the human in the loop of controlling the robot in a teleoperation system, and through the teleoperation interfaces, we can measure human quantities and provide feedback to the human. Since the robot is located in a remote location, we have the communication channel between the human and the robot. We also need to retarget human motions to the robot motions, and similarly, information from the robot needed to be transferred and mapped to the human. Finally, we have the robot in a remote location, which has normally high degrees of freedom and is equipped with the different sensors and actuators. A local control loop may plan and control the robot motion given the human references and estimated states of the robot. It's in charge of generating low-level commands to the robot. In the literature, many works have been proposed based on the architecture we just showed. In the teleoperation system, we have different interfaces, including variable and optical motion capture system, joysticks, treadmills to measure motion-related quantities, and other sensors for measuring physiological information of the human, such as ECG, EMG, and EEG signals. Moreover, we may need also other different types of feedback, provide different types of feedback to the human operator, including visual feedback, haptic feedback, and tactile and kinesthetic feedback. Different planning and control approaches based on complete dynamical model of the robot or based on simplified models have been proposed in the literature as well. Different whole body controller based on optimal control, machine learning approaches, and reinforcement learning are proposed in the literature to solve the planning and control problem as well. Moreover, the development of new and novel actuators allowing a compliant interaction with the environment are facilitating toward a more natural and safe interaction with the people and the environment. Another example abstracted from our speaker's work, the development of haptic devices and allowed to have the sense of touch, to transfer the sense of touch to the human. In a research carried out in the University of Developed, researchers also has developed a whole body haptic feedback exoskeleton cockpit. And as anticipated at the beginning of the workshop, we also cover other types of robotic platform, including quadruped and large robots. In this case, at IIT, they have developed a quadruped robot equipped with a manipulator and a hand in order to teleoperate the robot. And finally, at ETH Zurich, they have developed and deployed a teleoperation system using a hydraulic excavator for disaster response. Looking at the recent history behind the teleoperation system, we can find two milestones that have largely advanced and pushed the development of such system. One is the DARPA Robotics Challenge between 2012 and 15, and the other one is the ongoing competition ANA Avatar XPRIZE, which aim at deploying the senses, actions, and presence of a human to a remote location in real time, leading to a more connected world. Following this introduction of the state of the art, in today's workshop, we would like to address different aspects and topics and challenges related to this this topic. These topics include both hardware, software development, as well as human factors. In this respect, different devices, including sensors and actuation system, and whole body haptic feedback, different whole body retargeting and control strategies, and consideration of the communication delay will be discussed as well. Moreover, we will consider there will be different techniques for understanding the human physical and psychological state and human factors. Before describing the workshop agenda, please let me quickly present you to the workshop organizers who will moderate the workshop during the day. I'm Kourosh Darvish, postdoctoral researcher at Dynamic Interaction Control Lab of Italian Institute of Technology, which I have honored to open the workshop with this introduction. Along with me, we have Joao Ramos, assistant professor at the University of Illinois at Urbana-Champaign in USA. We have Rafael Cisneros as a researcher at ICRA in Japan. We have Luigi Penco, a PhD student in Rio, Nancy in France. We have Eiichi Yoshida. He serves as the director of Cisneros ICE Joint Robotic Laboratory and deputy director at ICE. And we have Serena Ivaldi, a tenure research scientist leading the human and humanoid robot interaction activities in Team Larsen in Rio, France. And finally, we have Daniele Pucci, the head of Dynamic Interaction Control Laboratory at the Italian Institute of Technology, pioneer researcher in whole body motion control and aerial humanoid robots. The workshop is composed of two sessions. In the morning, according to the European time zone, we will have speakers from Asia and Europe sharing with us their experiences. In the first part, we will have 3 talks followed by a break. After that, we will have 4 more talks. And the first session will be concluded by 1-hour panel discussion. In the afternoon, after the lunch break, we will have 3 more talks and 2 accepted paper spotlight presentations. After that, we will have a break. And in the last part of the workshop, we will have 3 talks and 1 online demo organized by Dynamic Interaction Control Lab. Finally, the workshop and the second session will be concluded with 1-hour panel discussion. Before going to start the first talk, please let me mention also a few points. We are recording the workshop and it will be shared with you on the workshop website and our YouTube channel. If you have any questions from the speakers, you can write us on YouTube chat or on Pole Everywhere platform. Okay, so let me stop sharing. And with this, I would like to thank you all for listening to me. Now I'm very pleased to introduce you to our first speaker, Bernd Bollnich. He is the CEO and robotic engineer at HALODI Robotics, a company that builds service humanoid robots. At HALODI Robotics, they are trying to push the future of humanoid robotics forward. They aim to move robotics to the consumer market by building a humanoid domestic robot, a robot that is silent, affordable, and safe, while still as strong as human and able to do real work. Very welcome, Bernd. Please, the floor is yours.
Good morning. I'm guessing that helped. Here we go. Yes. Okay. Thank you for your patience. It's always, like you say, it's always fun with these online events. Hopefully everything goes smooth. Let me try to share my screen here and I'll jump right into it. Can you see my presentation and not my speaker notes? Yes.
Yes, we can see.
Okay, very good. Thank you. So my name is Bernd Bollnich. I'm founder and CEO of HALODI Robotics. My background is robotics and nanoelectronics from the University of Oslo. And I'm the inventor of the Revo series robotic actuators, in addition to leading systems design on our robots in HALODI Robotics. So although I started my career doing software, thanks for the nice intro, my main contributions now lie in electromagnetical space, covering the design of motors, transmissions, and mechanics. So I'll try to keep my talk a bit maybe more in that direction than on the hardcore whole body control, where there's a lot of other people here who has a lot more knowledge than me that I'm looking forward to learning from later today. I'm a big believer in simplifying the tasks of the machines through ensuring low reflected inertia and a high dynamic range variable compliance, both so we can improve the robustness of the operation in unstructured environments, but also to improve the safety for working together with humans. So quickly about our product. So currently we have one shipping humanoid called Eve. And Eve has been designed to explore the markets for capable mobile manipulators in human spaces. So the bot has 8 kilograms of straight arm payload per arm and can operate in all ADA compliant spaces. All the joints are quasi-direct drive open loop torque control to allow for very low impact energy and high dynamic range of variable impedance. The platform is fully self-balancing with a high center of mass for exerting large forces in both push and pull tasks. And the bot is meant to work in human spaces, and safety is therefore a key design requirement and really drives the technical direction of our product development in general at the company. So on the hardware side, Eve has a very lightweight design that, combined with a very low gear ratio, results in very low impact energies in manipulation tasks. And I'll get back to how I think this really helps in the telemanipulation sense. We have a very holistic approach to robotics and design. So we design our own motors, transmissions, and electronics. And just to briefly touch on that subject, I think we're currently progressing very efficiently in the motor space. And I feel that this is a very underexplored space in the size of motors, where we like typically 30 to 100 millimeter diameter range. And that's really where you usually end up when you build this kind of high powered humanoids. A lot is happening in the electronic motor space for cars in general, but not so much for robotics, I feel. So there's a lot to gain there. And Eve is based on our Revo 1, which has about 3 times the peak torque and 2 times the torque per power of the closest competitors we can find. And we see now that our Revo 2, which is currently being integrated into our next generation product platform, has about 2 times the performance of the Revo 1 again on most metrics, while going to an in-runner for more efficient integration. And that this really enables us to do more and more powerful hardware. And a lot of emerging technologies here drive these improvements. But if I'm going to give one big shout out, I'd say GaN transistors is probably the ones that really opens the design space the most, as you can do very, very high frequency current control. So the improved torque control and volume to weight enables us to transition away from high-speed reducers and to focus on developing low reflected inertia transmissions that are robust to impacts and transparent to the controller. So this enables us to model our joints as pure torque sources, with the loop being closed in the current space and having no torque or other force feedback needed to still be able to achieve very low gain control and very compliant motions in both tele manipulation and also if we do autonomous manipulation. So I'm very excited that we are getting out of the lab. We are currently doing 3 pilot rollouts this summer in 3 different markets, and all 3 of them rely heavily on telemanipulation to cover edge cases, and in general to do any task that humans are well suited for. So in patrolling, there's a strong desire for customers to have a human in the loop for handling anomalies during patrolling. For example, a person not being authorized to be in a location, something being stuck in a door, in general tasks that we are far away from solving with autonomy. In retail, we find that having this shared autonomy and being able to drop back to telepresence is really powerful for handling edge cases. So, for example, we are working on restocking shelves in retail, and of course, this is nowhere near 100% success rate, but you can get away with a reasonably high success rate as long as you can do efficient handover to teleoperation. Machine tending has been a very, very exciting subject, where we actually see a lot of benefit in being able to service the machines through telepresence. So that's some very exciting detailed manipulation there. But a lot of these machines are in countries, low-cost countries with very unstable political situations. And there's a lot of downtime just for service technicians not being able to travel to a machine to fix it. So generally here, what we do in all of these different markets really is that we have some level of autonomy, right, to make the system efficient and to scale so that you kind of get a gearing on human resources. We don't need that much autonomy before this becomes very efficient, and then gradually you can introduce more and more autonomy, and efficient telepresence really enables you to have this smoke and mirror effect where your system always seems to be working extremely well, even though, of course, there's a lot of cases where the system is not doing exactly what was intended. But as long as that you can ensure it's safe and you can fall back on a human operator in the loop, you can get a very efficient workflow. So yeah, that's really the short background on what we're doing, and then over to the more fun parts of the robotics. So I just wanted to show a few manipulation examples and talk a little bit about what's going on and why I think this is a good solution to these kind of systems, and then round off with talking a bit about what's not working so well and where we really need in general progress both in the field and with our systems. So this first one here is a good example of something that I would say is a rigid, like a fixed base rigid body system. So opening a door. And we've all seen a lot of examples of robots pulling themselves over by doors, which is a really hard problem. And it's an example of really a system where the robot is not the master. The robot can't force the door to go wherever the robot wants it to do, right? The robot has to adhere to the kinematics of the door. And here we're using just compliance. We started out quite complicated with trying to think about directional compliance, because we can do directional compliance in any frame. So let's say we want to open a door. So we should we can be relatively stiff in the trajectory that we are moving together with the door, but for example, very compliant in the Z-plane because it doesn't really matter for the motion. But in general, we found out that having just enough compliance makes the task very, very, very stable and easy to perform in teleoperation. And that's generally one of the findings that we have so far, that we don't need to overcomplicate these things. It's just about figuring out what's the correct amount of compliance for a specific task. So is that video okay, by the way? It's probably a bit lagging when it's over. Could you see the video?
Yes.
Yes. Okay, good. Yes. So over to the next exciting task. So stable contact forces, really. And this is also a task where, again, I come back to, given that you have the correct compliance, from the operator point of view, this becomes very, very simple. And here we are actually, you're from the controller point of view, you're actually pushing, you're pushing the tool into the table. And the further into the table, like you're going through the table in the controller, the further into the table, the more force. So it's just a simple spring system. And this actually works really, really well. And we don't have any problems with the stability of the system or any of these issues, really. The big challenge here is actually, even though we have a lot of degrees of freedom, the system is 24 degrees of freedom. It is, how do you communicate the end of the workspace to the operator in an efficient manner? And I feel it's a really hard problem because it also depends on where you can drive, like what's your traversable terrain, where will the robot collide with the environment, all of these things. So while we can do these tasks quite efficiently, I feel that one of the big things that we're working on now is to get the training time of the operator down, because currently you need to spend a reasonable amount of time in the system, and then at some point your brain adapts and starts to map the workspace of the robot to your workspace, and that's a quite lengthy process. So when using the system, you can do a lot even after just like 2 minutes, because the kinematics of the system is the same as a human body. It's got the same, well, of course we don't have the scapulas and all this, but we have we have 2/7 degree of freedom hands, we have the hip, we have the full range of motion in the hip, we have all of this. So doing some preliminary tasks is quite fast, even if you've never used a VR system before. But once you start to get into the details and getting really good at the system, it's a steep learning curve. And a lot of it is really limited to how well do you know the workspace of the robot and like the limits of that workspace. And also how well do you know how to keep your compliance, because there are, of course, singular positions where you lose compliance if you extend the workspace too much. So I think this is an exciting application from the real world application of how do you, you're on an autonomous task, you're patrolling a hallway, and you see something that's not like it's supposed to be, or there's an alarm triggered because the door doesn't close, and the robot, of course, is not able to understand why it cannot close the door. So having a human operator step in and being able to resolve the task is really powerful. And this is a good example of using the whole body kinematic solver to do telemanipulation tasks. So if you bend down and try to grab something on the floor, the robot will bend down and put your hand in the correct position. And this is, of course, using multi-objective constraints. So you say, like, I want my hand in one hand here, the other hand over here, and tries to find the best possible solution. And this is also slightly challenging when it comes to communicating with the operator, because everything here is a best effort. The controller is not necessarily going to achieve exactly what you ask it to do. So you could say, put my hand over here at this height above the ground, and you're in task space and everything seems fine, but the robot is not necessarily going to go there because it might not be possible. It degrades really gracefully, so it just goes as close as it can, and we managed to make the system very stable, but it's still hard to communicate with the user of the avatar system why you cannot actually do what you're trying to do. If you get into, for example, either kinematics or dynamic constraints where you, for example, would be off balance, or it is not physically possible with your kinematics to do the task that you're trying to do. But with some training, this also, of course, becomes quite efficient, and you can do these kind of tasks. And I think this, sorry, skipping forward here. That wasn't on purpose. Here we go. This motion where you pull the bag out of the door while the bag is stuck is also very, I think, a very interesting task where we thought it would be very hard. Like there's a lot of forces going on here in this system, coupled between the bag and pulling very hard with the robot. But in general, actually, this works very well with just having the correct compliance. So I feel we're more and more moving the problem over to how do we figure out what's the correct compliance for a task. And I think very exciting future work also here could be, can we efficiently learn the compliance for different tasks? Because I think that would simplify the manipulation tasks a lot. I'm really bad at maneuvering this PowerPoint. I'm sorry. Let's see here. I just want to also show an example of here we go. Show an example of a more classical manipulation task where we're just picking up something. And this is relatively good, given that we have it is quite accurate in position control. It's not as accurate as a more classical system, but we can typically get to within a millimeter or two in absolute accuracy with the robot. And here, this task is a lot more efficient if we do a stiff impedance as we're moving, and then we go to a very soft impedance when we're picking up the kettle. So it doesn't really matter if you know exactly where the kettle is, because you're colliding with the handle, and then you're closing your hand, and that's okay because we have very low impact force, so you can collide safely, and hardware is robust enough that it doesn't care. But it's a very hard problem of finding what's the compliance needed to do this task in a good manner, because this works extremely well if nothing goes wrong. But if you go very stiff and therefore very accurate, but then you didn't know about some object outside of your field of view, or there's a person there, and suddenly the robot is seeing these huge forces from the very stiff system trying to go to the position where you're controlling it in your telepresence, then that's generally dangerous. So we try to go as soft as we can on compliance, basically in any task we do, and that gets you a very inherent robustness to the operation. So things generally don't go wrong, even if there are unforeseen things happening or collisions. And this is just a better view of an angle of like picking up something on ground, which is using the whole body kinematics. And going to this whole body kinematics approach where we're no longer controlling the arms independent of the pelvis and leg, that was a big win. And we see that the extension you get there to your workspace is really it's a lifesaver when it comes to telemanipulation, because it allows you to be slightly out of sync. Like you don't need to be in the exact correct space, and you as an operator don't need to be exactly calibrated with the robot, because you have a lot of margin in all senses. So that was a really beneficial point. So I already talked a bit about it, but if we look at the preliminary findings, I think the biggest wins is really how much the compliance simplifies the manipulation when interacting with fixed-based kinematic systems like doors, how the low impact energy makes interaction very robust, and actually, maybe most important of all, that this approach to how we build the robot makes the hardware incredibly reliable when it comes to collisions. So the robot has fallen multiple times. It has, of course, crashed many times every day when doing manipulation tasks, even at very high speeds. And the system can in general move as fast as a human. So if you're waving your arms around at like a natural high-speed human motion, the system follows this motion. But it can still actually collide with a hard environment and survive. And this enables you to do very fast iterative testing of the system and not have to be very afraid when testing. So if you have a good idea, just test it on the hardware, see how it works. And that's very empowering. We have some proper challenges. The non-holonomic constraint makes training the operator more challenging. So not being able to step sideways, it complicates a lot of tasks when you want to combine manipulation with driving, which is currently, I think we're starting to work on. But mostly the controller handles that quite well, but how that system will behave is not necessarily obvious to the user. So it lengthens the time needed for training the operator. Latency in streaming of vision is a big challenge outside of the lab environment. And I think this is a big one. And I'm looking forward to some of the talks on 5G later today. But I think this is a big unsolved problem. And here we're following kind of a dual approach where we don't only do low latency streaming. We actually also look at like how can we start looking at doing post estimations and transferring frames and having kind of mirroring worlds and objects in them instead of actually looking to transfer the video because of bandwidth requirements. And then it's the long-term ergonomics of the operator in the real-world applications. And this is something we're seeing as a bigger and bigger challenge as we start to roll this out in the real world, that switching in and out of VR and working in a workflow where VR is key 8 hours every day is still not quite there when it comes to ergonomics. So big things on the future work. So although we do a lot for safety and the system's inertia is very, very low, weight still needs to be reduced quite a bit to achieve the safety goals we have. So like I said earlier, Eve is the platform that we're using to pilot these markets and to build the software. But of course, the real product that's meant to achieve proper manufacturing volume, that's currently what we're building now. And the next generation from HALODI Robotics there's both a wheel version and a biped, because we're seeing also an emerging market for bipeds. Although, of course, as long as we are ADA compliant, it's more efficient with wheels. But the weight here is currently coming in with a new system at actually less than half of the current system. And this enables us to build in a lot of passive safety. And my big dream here is to be able to build a robot that is passively safe around humans. So as long as you don't have any dangerous tools, you're not dangerous. You're still capable. You can still lift a lot of weight, but your impact energies are extremely low. Your weight is extremely low, and you are in general soft and compliant, both from like how the robot itself should be compliant as a shell, and how the joints are compliant from an inertia perspective. So that's a lot of exciting work going on that these days. And then building systems for efficient guidance outside of VR. So we're trying to move more and more of the system to not require VR. So anything that we can do to really guide the robot through whatever autonomy it's trying to achieve and not having to put on VR goggles is a big win. And here I'm, of course, hoping for large improvements in the ergonomy of either VR or AR. I think mixed reality and AR is a very exciting workflow. If you could have glasses where you generally work on a normal screen area, you're sitting with your screens in front of you, but you can get an overlay and step into VR without having to put on heavy hardware, that would be a big win from the actual rolling out applications point of view. Thank you. So that's really what I had on the, let's see if I can stop sharing here, presentation side. And of course, I welcome any questions if we have time in closing.
Yeah, thank you a lot, Bernd, for your presentation. Very, very interesting and very new, exciting advances going on in HALODI Robotics. So I don't know if any of the organizers or speakers, if you have any question from Bernd, because also we are a bit late with time.
So we have one question from anonymous question, so maybe you can ask that from the audience.
So yes. Daniele has one question.
Yeah, but absolutely, let's proceed with the audience first.
Yeah, so the question is, do you have any reliable criteria for how to design the compliance with respect to visually perceived target, object, or task?
Repeat the question once more.
Yeah, sure. So the question is, do you have any reliable criteria for how to design the compliance with respect to the visually perceived target or task?
No. The short answer is no, not currently. That's some really exciting work that I'd really like to put some research effort into. But I don't have a solution. Okay,
so imagine it's kind of like you have to tune for the task.
Yeah, it's a hand. It's done by hand, right? It's you try to open the door and you're like, okay, if I push the robot a bit while opening the door and I on purpose misbehave in VR and pull the controllers a bit fast out in the wrong direction, what happens? And you see like, okay, I'm actually able to pull the robot over, or the system doesn't actually achieve the goal of opening the door. Can I change my... And you tune your compliance and potentially the direction of your compliance until this task becomes a very reliable task. And then we're starting to do the same thing when you look at autonomous manipulation, where you also then, as part of your trajectories, you tune your compliance. But it's a very manual task, and I think it probably doesn't need to be a manual task. We haven't worked a lot on it yet, but it's exciting future work.
Yeah, thank you. So we do have some other questions, but I think we should move on to be on schedule.
Yes, I agree with you. Maybe we can have the questions in the panel discussion.
Yes, I will be in the panel. So thank you a lot for the opportunity to present. It was a pleasure.
Thank you again for your presentation. Very nice. Okay, so let me also introduce you to the next speaker. I'm very pleased to introduce Dr. Susumu Tachi. He's the pioneer of the existing field. He's the Professor Emeritus at the University of Tokyo, and he's the founding president of Virtual Reality Society of Japan. His works has been recognized well internationally, and he has won many prizes. Among them, he is the recipient of the 2007 IEEE Virtual Reality Career Award. Unfortunately, he couldn't attend the workshop online. He sent us a recording of his video, and he asked us to share with all of you. So here we are with the video. Please.
In this invited talk, I would like to overview 40 years of research on teleexistence, which I invented in 1980, and explain cutting-edge technologies of teleexistence. We will also discuss several problems to be solved to attain the teleexistence society and foresee the future that teleexistence will develop and create. Teleexistence is a concept that denotes an extension of human existence, wherein a person exists wholly in a location other than his or her actual current location and can perform tasks freely there. The term also refers to the system of science and technology that enables realization of the concept. The location that differs from the location where you physically exist can be a real space or a computer-generated virtual space, and the latter case, that is, teleexistence in a virtual space, is usually called virtual reality. Furthermore, by matching the real space with the virtual space, it is possible to teleexist in the real space through the virtual space, or to act by adding information from the virtual space to the real space. The realization of teleexistence is done by virtually creating a state in which a person enters a robot or wears a robot like a suit. The left figure in this slide shows a system called a power suit, or an exoskeleton human amplifier, in which a human wears a robot-like suit to expand his abilities and enable work in dangerous environments without losing human abilities, such as judgment from a broad viewpoint or dexterous eye-hand coordination. However, there are several drawbacks to this system. The first is that it is extremely difficult to operate a system automatically, as the robot's own movements will cause the human body to move as well, making it incompatible with AI-based automation. The second disadvantage is that the user suffers damage when the robot breaks down. And the third is that the robot cannot be used without going there. Teleexistence acts as a virtual exoskeleton human amplifier and eliminates those shortcomings. The user is in the center of the right figure in this slide. He is connected to several autonomously intelligent robots. One of the robots, the left robot, is used for teleexistence. Even though the user is remote, he puts on the robot as if it were a suit and realizes the state of being inside it. In this way, the advantages of exoskeleton human amplifier are retained, but its disadvantages are compensated for. In other words, people can get a new robotic body and use its functions to extend their own body functions. He can then let the remaining autonomous intelligent robots, the one on the right, but there can be more than one, work autonomously without being moved himself. Conversely, the robot on the left can be put into autonomous mode and he teleexists to the robot on the right. Thus, it is possible to use multiple robots by sequentially teleexisting them. Furthermore, even if the robot breaks down, the user is not harmed. And of course, there is no need to go to the site directly. Avatar robots are placed everywhere, in offices, stores, factories, hospitals, schools, libraries, museums, parks, stadiums, amusement parks, all over the world. And people can use these avatar robots as their own alter egos from their homes, offices, or public teleexistence sites. This allows, for example, children and elderly people who have been hospitalized for a long time and cannot leave the house to play with other children or return to their own families' homes. In principle, these robots are intelligent robots. Therefore, when they are not in use, they can autonomously perform their assigned tasks. Equipped with safety intelligence, they can avoid dangers that the user has overlooked. Furthermore, even if the user logs out of the robot in the middle of the day, it can autonomously return to its original location. Foreign workers can also work remotely, thus eliminating the immigration problem. Furthermore, by utilizing the time difference, a 24-hour workforce can be secured from multiple overseas locations, eliminating the need for night shifts. Both men and women can participate in the workforce while raising children, making it easier to raise children. It is also noteworthy that as the teleexistence work progresses, more and more data will be collected on how people work with their own bodies. This data will allow us to see where people are looking and what kind of force they are applying to their hands as they work, which was not possible with mere video data. Currently, there is no big data that can be used as training data to teach the flexible and skillful work of humans to intelligent robots, and deep learning has not been achieved. However, with teleexistence, as workers from all over the world perform such tasks, the necessary data will be collected, and it will be possible to replace them with intelligent robots. I came up with the idea of teleexistence in September 1980. Since then, I have been working on the realization of teleexistence with my laboratory members more than 40 years. This slide shows how we developed teleexistence technology. I would like to show a video of teleexistence from 1980 to 2012.
Teleexistence allows a person to experience a real-time sensation of being at a location other than their own and to interact remotely with real or virtual environments. In 1980, the concept of teleexistence was first proposed by Professor Susumu Tachi. Its feasibility was demonstrated through the construction of alter ego robot systems. It was first published in Japanese in 1982 and subsequently in English in 1984. Telepresence and teleexistence are similar concepts that were proposed independently in the USA and Japan, respectively. However, they differ in the aspect that telepresence does not include existence in a virtual environment, or existence in a real environment through virtual representation. In 1985, a method for mobile teleexistence was proposed, and its feasibility was evaluated by developing a tele-vehicle system that can be driven remotely, providing both auditory and visual existence sensations. In 1989, a teleexistence surrogate anthropomorphic robot called Telisa, the first prototype of a teleexistence master-slave system for performing remote manipulation experiments, was designed and developed, and a preliminary teleexistence evaluation experiment was conducted. In 2000, teleexistence in a humanoid biped robot was achieved by developing a teleexistence cockpit under the Humanoid Robot Project, HRP. Furthermore, the advantages of human-like motion were proved. In 2005, a mutual teleexistence master-slave system called Telisa 2 was constructed for the Eiichi World Exposition using retro-reflective projection technology, RPT. In addition to the conventional bidirectional verbal communication, simple gestures such as handshakes could be performed. In 2010, a mobile mutual teleexistence system called Telisa 4 was developed with master-slave manipulation capability. It was equipped with an immersive omnidirectional auto-stereoscopic 3D display called Twister with a 360-degree field of view. Using Telisa 4, local participants at the event were able to view the face and expressions of the remote participants in real time. In 2007, Telisa 3 was constructed, which can transfer visual information in a more natural and comfortable manner by accurately tracking the head motion of a person with 6 degrees of freedom. In 2011, Telisa 5 was developed with a conjunction of 53 degrees of freedom for performing full-body movements. The transmission of haptic sensation allows the operator to feel vertical and shearing forces exerted on fingertips. The operator can freely and independently move the robot's head, upper body, arms, and hands similar to his own, while maintaining the head to arm vector intact. The operator can feel tactile and thermal sensations when touching objects remotely.
We launched GST Axle Embodied Media project in 2014. In the project, we have developed a compact and integrated tactile sensation transmission module based on the principle of haptic primary colors. With Axle Embodied Media project, Telisa 6 was developed based on Telisa 5 system. Telisa 6 realized full embodiment with 67 degrees of freedom by adding legs and improving hand motor functions, and expanded haptic information transmission by integrating haptic primary color modules. Since the size and degrees of freedom of the human and robot bodies are different, even if the angles of each joint are identical, the robot will not be able to move as expected. What is important is to control the vector from the camera to the hand of the robot so that it matches the vector from the human eye to the hand. The same is true in controlling the fingers. Telisa 6 focuses on the vectors between the thumb and the other fingers, and devising and introducing a new control method to make them coincide in master and slave. A 6-axis force sensor, an acceleration sensor, and temperature sensors are embedded in all 10 fingers of the Avatar robot, Telisa 6. And by processing the acceleration sensor information, vibration information is obtained and sensed as haptic primary colors. Each human finger is displayed with a dihaptic module that presents vibration and temperature and a force display device. The force display device consists of a finger pad, a thread, a threader, and a small motor. The finger pad is pulled by the force of the motor, and the force sensation is first generated by the skin sensation caused by the deformation of the skin on the belly of the finger. When the finger pad is pulled with a larger force, the force is applied to the finger joint, and force sensation is generated by proprioception receptors such as the joint capsule. Since its conception in 1980, we have initiated many projects, accumulated technologies, and demonstrated the feasibility and effectiveness of teleexistence. And now, after 40 years, the times are rapidly catching up with us. In October 2016, the XPRIZE Foundation held its annual Visionaires Summit. The foundation held its Visionaires Summit to choose the next XPRIZE theme from among 9 candidates. Over a 2-day period, 9 teams presented their theme proposals, and the proposals were screened by a panel of around 300 mentors who included academics, CEOs, and venture capitalists. Team Avatar, one of the XPRIZE teams, asked me to come to the 2016 summit to demonstrate our Telesa 5, which they recognized to be the world's most advanced robot avatar. I agreed and presented the technologies over the 2 days with the help of the members of Tachi Laboratory. The panel was impressed with the demonstration, and they picked Team Avatars as the proposal for the next XPRIZE theme. The ANA Avatar XPRIZE was then launched in March 2018, with the finals scheduled for 2022. In response to this movement, startup companies such as Teleexistence Inc. have been born, aiming at the industrialization of Teleexistence Avatar. In addition, KDDI, Nippon Steel and Sumitomo Metal Solutions, NTT Docomo, and Toyota announced prototypes for teleexistence-oriented products with a sense of presence and workability. As can be seen in this series of events, the times are steadily moving toward the creation of a new industry field of virtual teleportation industry, or teleexistence avatar industry. In this context, social implementation is steadily beginning in industries such as convenience stores, which can be said to be the social infrastructure that supports society. A good example of this is the implementation of product display operations using teleexistence at the Lawson Tokyo Port City Takeshiba store, which opened on September 14, 2020. It is worthy of special mention that the robot was actually introduced and operated in the actual store.
Jump through space with unique innovation born in Japan.
How do you like a new body? A robot body.
Oh, nice.
Through teleexistence technology, you can go anywhere. Even if you are not there, it's like experiencing it firsthand. It's possible to be here and still do your work on a space station.
I believe that with this teleexistence innovation, we can change society as well as how we live and work.
So many young Japanese visionaries are determined to change the world. Passion driving technology for a better world. Find your Japan.
Influenced by the Avatar XPRIZE, Japan's science and technology policies are beginning to take Avatar into account. The first of the 6 goals of the Moonshot R&D program, which was launched in fiscal year 2020 under the auspices of the Cabinet Office's 115 billion yen fund, is to realize a society in which people are free from the constraints of body, brain, space, and time. We will challenge to realize a cybernetic avatar society and a cybernetic avatar life. In other words, the goal is to realize a teleexistence society. Owing to the creation of new industries such as tourism, travel, shopping, and leisure, it will greatly improve convenience and motivation in the lives of citizens, and it is anticipated that a healthy and pleasant lifestyle will be realized in a clean and energy-conserving society. With a view to the future, it will be possible to respond instantaneously from a safe place during disasters and emergencies. And this technology can also be used routinely to dispatch medical services, caregivers, physicians, and experts to remote areas. Furthermore, based on my 30-year cycle prediction, it is expected that a major step-up will occur again in the 2050s, and society will change drastically, and full-fledged teleexistence society will be realized at that time. With teleexistence giving people new augmented bodies and instantaneously transporting them virtually, it will empower humans to live more like human beings, greatly contributing to humankind in the years to come. Thank you for your attention.
Okay, I wish to thank again Dr. Tachi for his talk. Very, very interesting. And so with that, I would say we can go to the next speaker. I would like to invite the next speaker, Dr. Youhei Kakiuchi, to share his presentation with us. He's an associate professor of the University of Tokyo. He's a leading researcher in the field of humanoid robots and teleoperation system for real-world scenarios and applications. With this, I will leave the stage to you. Please, Dr. Kakiuchi. You are muted, Dr. Kakiuchi. We cannot hear you.
Okay, sorry. Can you hear me?
Yes.
Okay, I will start presentation. I'm from University Tokyo and JSK Labo. This is straight talk. We use some devices to operate a biped humanoid robot in the real world. So each device has a different input. So target task selection by the command and the non-real-time target pose command, or real-time pose command and post command. And the control method on the robot side is also different. For teleoperation, the planning and recognition can be done by the operator, but support software is required for the operator's planning and recognition. So I will talk about the humanoid teleoperation using graphical user interface. This was used for the DARPA Robotics Challenge Finals. It was a primitive operation method. I think at that time, we used a graphical user interface system and general input devices like that. So this method was a non-real-time command to the robot. Tasks are previously known and fixed. Because of limitation of communication, we can't adapt real-time feedback, such like operator changing behavior depend on vision and robot sensors. So we use a shared autonomy strategy for these tasks. What is our shared autonomy strategy? For each task, we adapt the method sharing, autonomous robot behavior, and manual operators adjustment. The figure shows how the configurable autonomy done. We divide the task execution into some phases, and object recognition, and standing position determination, and robot motion generation. The operator verified recognition result for each phase. If something was wrong, operator can modify them, and then command was sent to the real robot. This figure shows how to share autonomous task execution and manual modification. Our perception system adapts user suggestion. Here is a recognition, and this is a recognition result. After coming recognition and planning result, an operator can change the can correct recognition and planning result. After finishing operator's verification, robot starts moving. This movie shows how to work user suggestions. This example for detecting a handle foil. An operator suggests a rough position of a target on the camera image, like the left movie. So recognition node calculates a 3D position and a target size from the suggestion. This video shows the configurable recognition and motion generation. After getting the recognition result, user can modify recognition result. That's like the bulb size and position recognition by the model fitting. And the user can modify this result. And after the modifying the result, motion planning creates a robot motion. After verifying this motion by the operator, robot can move the motion. Next, I will explain about mannequin device for operating a humanoid robot. The method is using a small robot has the same joint configuration of large humanoid robot. It can sense its current joint angle, then sending the same joint angles to the large humanoid robot. It is suitable for making a motion of full body because it can directly change a concerned joint without inverse kinematics like that. It also can feedback robot's torque. The operator can feel torques the real robot produce. But it is difficult to operate mannequin quickly and correctly. Also difficult to operate many joints simultaneously. So this method is not suitable for real-time feedback. Then we use it for static balance motion. This is a demo movie for the using the mannequin device. It is a sitting robot moving the plate on the human figures, like that. Next, I will talk about making a humanoid whole body motion with virtual reality devices. Real-time but conventional studies about whole body master slave humanoid is not enough for dynamic motion. Many studies worked only on the arm or upper body of the robot. Or if some cases worked on the whole body, motion was limited to be quasi-static. Because mass parameters are different between robot and operator, and the other reasons, the robot can perform exactly the same motion as human doing. especially in the online real-time case. Pre-planning nor predict control approach cannot be applied. Furthermore, the robot can easily fall down with the operator's uncertain operations. So our main goal is to achieve valid and dynamic whole body teleoperation with bipedal humanoid robot. This is our whole body humanoid teleoperation system. Get position and orientation with VR system, and they are on the feet and hand, head, and human waist for moving a center of mass. And process those input trajectories with our proposed method in real time. Filtered reference human posture trajectory passed to inverse kinematic solvers and converted into robot reference joint angles. At the same time, the reference GMP position is also generated from reference center of mass trajectory. The HTC Vibe tracking system have sub-millimeter precision, and it can be updated with up to 19 Hz with head-mount display rendering. And when without rendering, we can get tracking data up to 1000 Hz. In the robot side, motion command from the operator should be constrained for the balancing at bipedal standing. Because future information is indefinite in real-time operation, we adopt the conservative strategies. The robot is controlled so that capture point is always constrained within the predicted support region. It is PSR. It guarantees that the center of mass movement will be stabilized with both feet in the next moment. Capture point is the condition for the stopping statically. For stability for the acceleration phase, convergent component of motion which paired with DCM. Theoretically, CCM is not used for the stability conditions, but we use it to guarantee a more conservative reference trajectory. And DCM, divergent component of motion, which is the same as capture point in 2D in the 2D plane. We achieve feasible acceleration and deacceleration phase. Our main idea is filtering good. Okay, we show some application. Okay. There is no possibility of operator. Advantage at the same time. Bipedal This is a Mistry.
Sorry, Youhei, I'm not sure if you're talking, but we cannot hear you very well while you're showing us the videos.
Sorry. This is a video for the landing timing and the trajectory suitable for the real humanoid robot. The robot can lifting the foot over the 60 centimeters. Next, I will talk about whole body exoskeleton bilateral device for a teleoperation system. This is just the force feedback to VR device system. This is our exoskeleton bilateral device. The operator seated on the robot. Force feedback with high back drivability was achieved by using outer rotor brushless DC motor. This video shows the performance of the other control tasks. First, the gravity compensation is working and weak convergence to the standby pose is also working. Next, virtual floor constraint task is working and it's also reproduce the interlock constraint of the both feet in the dual support phase. This figure shows this figure shows bipedal-oriented whole-body humanoid robot teleoperation. Red font indicates the difference from the VR device. Here is the force feedback to the exoskeleton devices from the robot. This video shows the basic motion performance. Next video shows the handling of sides. Using this device, we achieve continuous locomotion right movies. This video shows 3D locomotion on the large elevated planes. Here is just like the stairs. Robot can walk on the elevated plane with exoskeleton devices. This video shows teleoperating as a robot from remote room. Room distance is more than 150 meters, and the delay of the communication is 15 milliseconds. Operator can control the robot walking motion with this device. This is a demo movie in the same room, and operators directly see the target object handling. Robot can handle the object in the room and performing a task. We achieved by pipe stabilization and force feedback. But can a robot with this method perform all the tasks we expected? And no, there are many tasks the robot cannot perform. So we adapted task-oriented teleoperation. Task-oriented means change a mode depend on the task. So we developed the task-oriented mode for each task. This strategy is similar to GUI teleoperation. We need many software G which add constraints to robot motion. For example, fixing a relative pose of each hand, and the hand is horizontally fixed like that. This is basic modification of the bringing the heavy object. Next is autonomous pose control for teleoperated humanoid. Robot can correct the center of mass according to the object weight dictated by the hand host sensor. With this method, completed the motions and that operator cannot directly control. This is example video that robot operate heavy object with the dual arm. Robot controls the robot's center of mass while handling the heavy object. Next target, we plan to connect the planning system to expand the task object system. All body heavy object manipulation for multiple motion, the next target. Here is a enormous motion planning target. Here is a teleoperated generation by the task-oriented system. So next is a multi-contact motion. Robot controls by pushing the air side. This is a default bipedal robot. Depend on the closed constraint loop. So conclusions. I talked about a teleoperated piped humanoid robot in the real world with several methods. The expectation for moving a robot as when it is larger as following devices. Therefore, for a bipedal humanoid robot, there are some difficulties caused by many degree of freedom control and fundamental instability. So we adapted a task-oriented system for a mode depend on the task. It should be developed by integrating the other methods shared autonomous direct control of joint and software gene. Remaining many subjects who are bipedal humanoid robot teleoperation. Thank you for listening.
Thank you a lot, Dr. Kakiuchi, for your presentation. Very interesting results and new advances in your group. And we are very pleased to have you with us today. And okay, also I have, I don't know if there are any questions from audience or from other speakers or organizers.
We have one audience question.
Okay.
So the question is, can we extend this technology to teleoperation for people with amputation, so such as using brain signals, and what are the challenges?
Excuse me, I don't get your point.
So, yeah, so the question is if you can use this technology for people with amputation by using brain signals.
Brain signal. I don't know much about the brain signal, but so it is easy for using the every operator. This physical moving is easy understand for the operators. I think. Sorry, I don't know about the brain interface.
Okay, I think it's okay. It's normal. All of us, we are expert in some parts, and it's normal. So with this, I would like again thank all the speakers for presenting their work and sharing with us their experiences. Since we are delayed around 15 minutes, I had also one question, but I will probably keep it for the panel discussion. And probably also we can recover some of this delay during this break. So if you agree, we will start in 15 minutes at 10:30. And so in 15 minutes, we will join again the workshop. And from that moment, Rafael will moderate the workshop. Okay, thank you all.
So, Kourosh, we are still live, right? No.
I sent already. Okay.
Kourosh, will you hit me?
I believe yes, we are still live.
Okay.
Maybe it's better to show we start, yeah, in at 10:30.
Yeah, also I shared the picture with ICT. Probably they can also share it with, on YouTube.
I also make a public statement that I lost a bet with Kourosh because I told him that if we had more than 100 people watching, I would have paid a beer plus a pizza. So I officially lost this bet, and I have to now pay Kourosh a dinner.
Okay, that's good.
How many people are watching? Do you know?
Yeah, now 91. So if you go just on the YouTube, you see how many people are watching. So yeah, I did the wrong estimation because I should have said 20%. instead of 10% of the people who accept.
But I think this is a good batch to loss, so it's okay.
Yeah, it's good. You know, no, happiness equals reality minus expectations. So if you keep the second low, then you're happier in life. So that's yes. Yeah, now they're increasing again. I think we can also do statistics on the top of people watching. Yeah. And,
for the next couple of interesting talks. So our next speaker is Professor Michael Mistry. He received his bachelor degree in mechanical and electrical engineering from the University of Pennsylvania, his master's degree in cognitive and neural systems from Boston University, and his PhD degree in computer science from the University of Southern California. He was a researcher at the ATR Computational Neuroscience Laboratory in Kyoto, Japan, a postdoc at the Disney Research Laboratory at Carnegie Mellon University, and a senior lecturer at the University of Birmingham. He's currently a personal chair of robotics at the School of Informatics in the University of Edinburgh, as well as the director of the Center for Doctoral Training in Robotics and Autonomous Systems at the Edinburgh Center for Robotics. His research interests mainly focus on the principles behind dexterous movement and control of robots and humans, particularly in environmental contact. This work spans operational space control, redundancy resolution, stochastic optimal control, and legged model learning, and has been applied to compliant legged locomotion and manipulation for mining, offshore energy, and nuclear industries. And today, he will present to us a talk about fractal impedance control for dexterous telemanipulation. Please welcome Professor Michael Mistry.
Thank you very much for the nice introduction. And also thank you for the invitation to present at this workshop. It's quite an exciting workshop, and I'm glad to be part of it. So I'd like to tell you about our new method that we've been developing for impedance control, which we call the fractal impedance controller. And in today's talk, I'm going to focus on the telemanipulation application for this. I know this workshop is on legged robots, and we are interested in developing teleoperation for legged robots, and I will highlight some of the work towards the end of some of the work that we've done in that area. But for now, I'd like to focus on the sort of the non-legged, so fixed base robots, focusing on the manipulation problem, and maybe I'll highlight how we can extend this to legged robots towards the end. Okay, thank you. So our challenge is to create robots that can safely interact with the environment and with humans. And we do like the Cartesian impedance control framework as a very nice way to set up interaction for our robot. Because when we use impedance control, or particularly Cartesian impedance control, we can set up the behavior of the robot to act as a spring mass damper. And the nice thing about having the robot acting as a spring mass damper is that it's safe and predictable, right? And then ultimately the controller can be stable, right? And depending on the task, we may want to set the desired inertia, the desired damping, and the desired stiffness, depending on our task constraints. And if we can control those components, then we can set up an impedance interaction, and we can basically predict then how the robot will interact with the environment, and then we can keep stability. So I want to focus today on how we can actually create a variable stiffness profile, which can be state or time dependent. Okay, so particularly for some tasks, we may want to vary the amount of stiffness that the Cartesian impedance controller is applying. For example, here in this video, let's say we want to limit the workspace that this human is interacting with the robot. Let's say we want to bound the workspace to this red area. So ultimately, we would want to increase the stiffness as the robot's end effector approaches the boundary. Okay, so we actually have a state-dependent stiffness profile here that's saying bounding the workspace within this red box. Okay, and actually creating such a variable impedance profile is a challenge in control because actually we lose some of the nice guarantees of passivity and stability. Okay, when we have variable stiffness. And people have been working on this in the past on how we can actually guarantee, continue to guarantee passivity when we have variable stiffness. And a very popular approach has been the energy tank approach, Where in the energy tank approach, what is done is that the energy that's generated by the system is continuously monitored. Okay, here with this xt, which is this state of this energy tank. So it monitors the energy that's entering the system, and in order to guarantee passivity, then energy can be released through the system such that the total energy that comes out is never more than the total energy coming in, and thus we can guarantee passivity with such an energy tank approach. But the drawbacks to this tank approach is that you can potentially run out of energy. So if your task is dynamic, fast moving or whatnot, potentially you could run out of energy, and that would degrade the performance when you lose this energy storage. And a second drawback to this approach is that you have to monitor or estimate the non-conservative components of energy. This is particularly damping. Okay, so you must measure the amount of damping that the system is generating continuously. And the problem with measuring damping is that that's going to depend on your discretization or your bandwidth. So if you have limited bandwidth, for example, in a low bandwidth teleoperation scenario, your estimation of this energy component will be degraded, and then your performance will be degraded. So I'd like to introduce to you a new impedance controller that we've been working on in our group called the fractal impedance controller. And the advantages of this new controller is that we can guarantee passivity globally. Okay, so we can guarantee global stability and passivity, which does not depend on an energy tank method. So in a sense, we can never run out of energy like an energy tank method can. And second of all, the controller does not depend on damping at all. Okay, so actually we can set damping to 0 and we can still prove stability. And this also makes it robust to discretization and bandwidth. So this is particularly very useful for teleoperation where we have maybe a low bandwidth communications scenario. So the fractal impedance controller has two components. Okay, the first component is a tunable state-dependent stiffness profile, which I'll explain more in a second. And the second component is a fractal attractor. Okay. So let me talk about this variable stiffness profile. Okay, so it takes a shape like this, as you can see in this blue line here. Okay. Around the origin, we have a constant stiffness, so we have a linear stiffness profile near the origin. And then we can set a virtual boundary, let's call it XB, where the stiffness exponentially increases as we approach that virtual boundary. Okay. And this boundary is tunable. So for example, we can use this boundary to limit the workspace that we want the robot to operate in. Or if we're doing a tracking experiment and we want to reduce our tracking error, then we can tighten up the boundary, XB. But the stiffness will increase exponentially until we reach a maximum stiffness here. Okay, and this maximum stiffness point, let's call it K max, this can be set by the physical properties of our robot. So effectively, we set our maximum stiffness based on the maximum force that the robot can generate. Okay, so this will be dependent on what kind of robot you're operating on. And if you go beyond that virtual boundary, then we decay the stiffness profile. And the reason why this decay is important is because it keeps the maximum force at a constant. Okay, and this is important for our stability guarantee because then basically we limit the spring's potential energy as we move beyond this boundary, keeping force constant. Okay. So the second component of the fractal impedance controller is the fractal attractor. Okay, and let me explain how it works here with this diagram. So here we have the position, and in the vertical axis we have velocity of the state. And the attractor here is, say, at the origin. Okay, so the system is attracted to the origin. Now, if the system is perturbed, okay, so let's say it moves along this black arrow curved here, okay, up to a point, and let's say a human operator pushes it up to this kind of X max area, and then lets go, okay. At this point, what our fractal attractor will do is actually will measure the amount of energy that's stored in the system at this point where it's transitioning from divergence to convergence. And effectively what it's doing, it's going to change the set point to the middle point, okay, such that it has the spring, this virtual spring now has enough energy to perfectly accelerate, and then as soon as it crosses this midpoint, will then have exactly the amount of energy to decelerate such that it reaches its initial attractor perfectly. Okay, but however, if during the convergence phase, let's say it goes along the green and then it gets perturbed again, extra energy is added into the system. Okay, then at this point, when it crosses over into the next quadrant and to enter a new divergence phase, it will swing back, okay, back to a new convergence phase, okay? And when it enters the convergence phase again, we are going to then compute the amount of energy that we need to return it back to the original attractor. And effectively, that's resetting the set point again to this middle point here, such that it has the perfect amount of energy to restore back to its back to the origin. Okay. And effectively, because we're instituting this switch of impedance, so the switch of impedance, the circuit diagram looks like this here, okay, where we have a certain amount of impedance, let's say the desired impedance of our system. And then during divergence, the total impedance of the system is exactly KD. But then during convergence of the system, we actually add a new impedance in series, which effectively changes the total impedance of the system such that it has a perfect amount of energy in order to return to its original attraction point. And we call this a fractal attractor because it has a self-similar profile depending on the energy state. Okay, so as the system decreases in energy, the same similar pattern emerges, but it gets obviously smaller and smaller. Hence, we call it a fractal. Okay. So we've compared this fractal controller to a traditional impedance controller. So as you can see in this first video, here we have set up this virtual boundary. Now, the virtual boundary for a traditional impedance controller will create energy, extra energy. So again, we lose the passivity guarantee with a traditional impedance controller. And you can see here how the energy is amplified as it's bouncing against this virtual boundary. While on the fractal impedance controller, it maintains its stability. We're also stable to contact switching. So for example, here the robot is pushing down on this object. And if we have a sudden change in contact state, the robot can still maintain its stability. So we've implemented this in a teleoperation scenario, okay? And actually this work will be presented by my PhD student, Keihan, tomorrow in the ICRA main conference. And just to highlight some of this work, effectively we've set up a teleoperation system with a haptic device. This is a Sigma 7, where we run the fractal impedance in an admittance control mode, because this is a admittance device, while we have the Franca robot over here running in impedance mode, the fractal impedance controller. And here we can set up like this virtual boundaries, this variable stiffness to limit the workspace. Yeah, you can see how the demonstration of the sort of bandwidth, and also we do modify the bandwidth of the loop between the master and the replica robot, which I'll show some results in a second. So in this work, we show the transparency of the approach by interacting with certain different objects of different stiffness or different properties. And again, the one nice thing about using the fractal impedance controller is, since we do not need to rely on damping in order to maintain stability, we can show that we can have a higher level of transparency in a teleoperation task. We have various experiments here where we compare the fractal impedance control versus a traditional impedance controller. Here we show like trying to use the robot to open up a lid of a box. Here we're pushing some objects. Here we're trying to push a nail into some sand. Here we're trying to manipulate a sponge. And here also trying to push a button. Okay. And here we see the numbers of the time it takes for the operator to complete the task using the fractal impedance versus a traditional impedance. And typically, with the fractal impedance, the operator can complete the task quicker. And this is related again to the transparency of the approach. Oops. So if you compare, for example, the impulse response of the fractal impedance controller versus the impulse response of a traditional impedance controller, we see that the traditional impedance controller, because it has to rely on damping, has this underdamped behavior. And we also measure the overall bandwidth with object interaction. And the bandwidth of our system through the teleoperation system is wider for the fractal impedance. And again, mainly this is because we do not need to rely on damping. I mean, there's no free lunch in a sense, because what we do lose is we do have an anisotropic impedance profile given by the fractal attractor, meaning the impedance profile in one direction will be different than the impedance profile in the other direction. So given that sacrifice, but the fact that we do not have to rely on damping, which sort of reduces the overall bandwidth of the system, we're still able to achieve completion of these tasks in a better way than with the traditional impedance controller. And finally, I wanted to highlight one of the strongest arguments for the fractal impedance. And that is teleoperation with extremely low bandwidth or even high delays. So we ran experiments where we tried to have the operator using a visual camera. He's looking at the robot through a camera, trying to complete a task where he's pushing a number of buttons. And in here we have sort of an ideal situation where we have a kilohertz bandwidth between the master and the replica with 0 transmission delay. And here we degrade the performance. We have 100 hertz bandwidth with half a second transmission delay, and up to the extreme of 10 hertz bandwidth with the delay up to a second. Okay. And this is an expert operator. Actually, it's the PhD student. So the point is, the expert operator can learn, even with this kind of extreme delay and low bandwidth, can learn to complete the task. But the most important thing here is that the interaction, both at the replica area and in the haptic interface, can remain stable, since we have this global guarantee of stability. Okay, so I've focused here on the fractal impedance controller and focused on the telemanipulation problem. I do want to highlight some of the work that we've also been doing in teleoperation for legged robots. And actually, this is work we presented at ICRA last year. So here we have a quadruped robot, and we're using our haptic interface in order to get the robot to complete a task like pushing a button. Okay. Now the trick is, the complication as when you're doing teleoperation with a legged system is now you really have to be concerned about the legged system's balance and stability, right? So not just the stability of the controller or at the interface, but also the overall balance and postural stability of the legged system. So here we're showing how we can insert the leg into a pipe. So not only can you control the position of the end effector, but also the orientation to insert into some object like so. And here we're just highlighting the fact that the whole entire body of the robot is used to control the end effector. So as the end effector, the foot here needs to move down, the whole entire body goes down with it. Here is an experiment in a mine where we're using the robot to like teleoperate opening a gate and also like doing some exploration here of the environment. This is all joystick controlled at this point here. Like for example, the robot is exploring the wall of this mine, digging for gold or whatnot. I wanted to, before I conclude, I wanted to highlight in this video. Where is, here we go, yes. Sorry, I skipped this part. So here, see the robot here is now pushing against this surface, okay? And if you do not limit the amount of force interaction that this robot undertakes, so the robot's pushing harder and harder, the operator here is pushing, then at some point the robot will lose its stability. Right? So what we did in this work last year for ICRA, we measured the amount of force that the robot can exert at its end effector. Okay, so we create what's called a feasible force polytope. Okay, that respects the physical constraints of the robot, which is basically the friction cones at the points of contact of the robot. And then effectively what we can do is limit the amount of interaction that the operator is able to apply to the robot. Okay, and so basically we compute the maximum force allowed. And then when the operator is reaching that limit of the maximum allowable force, we then basically limit how much position that the operator can push, and that keeps the legged robot stable. So now what we're working on is actually integrating the fractal impedance controller, which I mentioned earlier, to this legged system, such that the fractal impedance controller, we can create this virtual boundary that I set, which has very nice properties about stability guarantees as well as low bandwidth robustness. And we're trying to combine the work with the fractal impedance with the legged system at this moment. Okay, I think I'm near my time, so I'll just conclude then. I'll just conclude by thanking my group. This is my team. I want to particularly thank Carlo Teseo, who is a postdoc working on the fractal impedance controller, and also my PhD student Keihan. And actually, both Keihan and Carlo will have presentations later on in ICRA using the fractal impedance controller. Keihan's presentation will focus on the telemanipulation, which I mentioned, and Carlos also on mobile robotics. And with that, I would like to thank you, and I'm open to answering any questions you may have. Thank you.
I forgot to mute. Thank you so much, Michael, for the presentation. So I think that we have maybe just time for one quick question. So there is a question from the audience that is what about the delay in communication? I think that what about the delay in communication? So I guess that it refers to the last videos that you showed about the mobile animal.
Yeah.
Did you have any delay in communication in those experiments, or where have you tested that?
Yeah, so with the animal experiments, we have not put any delay in. So at the moment, I mean, so the experiments you saw in the video is in an ideal situation with minimal delay. But one thing that we're investigating is actually seeing what we can do with a legged system with delay and also low bandwidth. And that's actually why we want to use the fractal impedance controller with the legged system.
Thank you very much, Michael. So I think that there is another interesting question, but maybe that will be reserved for the panel discussion in order not to delay more the session. Thank you very much for your presentation.
Thank you very much. It was a pleasure. Okay, so I will stop sharing my screen somehow.
The same button that you press to share contents. Yes, exactly that one.
Good. Thanks.
So our next speaker is Professor Ryo Kikuuwe from Hiroshima University in Japan.
Yes.
Wait a second. Let me introduce you. So he received his bachelor, master's, and PhD in engineering degrees in mechanical engineering from Kyoto University in Japan. From 2003 to 2007, he was endowed chair research associate at Nagoya Institute of Technology. From 2007 to 2017, he was an associate professor at Kyushu University, also in Japan. And from 2014 to 2015, he was a visiting researcher at INRIA in France. As mentioned previously, he is currently a professor at Hiroshima University. His research interests mainly include force control of robot manipulators, real-time simulation for physics-based animation, and engineering applications of non-smooth system theory. Today, he will present to us an interactive simulator-based study on the teleoperation of bipedal robots through inexpensive haptic devices. Please welcome Professor Ryo Kikuuwe.
Okay, thank you very much for your kind introduction. And thank you very much for inviting me for this interesting workshop. And I am Ryo Kikuuwe from Hiroshima University. The title is, well, it's like that. And it is, it is based on simulator. And we are dealing with teleoperation of bipedal robot. Okay, and this is the the whole picture of my research work. My research area ranges from the control to the computation. And so the control is mainly for fixed grounded manipulators, and computation is for interactive simulation. And the third part, this central part, is the theory and the theoretical foundations common to both areas. And many projects are related to non-smooth system theory, which are related to Coulomb friction, unilateral contact, and sliding modes. And well, today's topic is this area, and it's in the middle between the robot control and the interactive simulation, and it is a bit away from non-smooth system theory, but I use some techniques from non-smooth system theory in this project. Okay, let me talk about a little about my work related to robot control, and especially about teleoperation. Some of most cited papers of mine are about the position controller named proxy-based sliding mode control. And it can be extended into a controller like this, and which is a unilateral teleoperation. And a good point of this controller is that we can impose arbitrary limit on torque and velocity in joint and task spaces without sacrificing the accuracy of normal operation, normal position control, and position control in normal situations under saturation. And in this video, the position is sent unilaterally from the haptic device to the robot, and the robot is basically tries to follow the commanded position, but because there is a limitation in the velocity and torque, the robot usually behaves. Robot is always safe, so we can touch the robot under the control like this. And this controller is realized by a kind of differential algebraic combination of sliding mode controller and a PID controller. Okay, and we use similar techniques for both simulation and control of bipedal robot. Okay, and this is another series of my project, and I'm also working on real-time interactive simulation. And some of the techniques are based on non-smooth system theory. For example, well, those including friction and well, the modeling of hydraulic actuators. Okay, and in most of these research projects, we work with haptic devices. Okay, and this is about my work on bipedal robots, which is the main topic of this talk in this workshop. And we are using this kind of setup with a pair of commercially available haptic devices. And I have to be clear that currently it is purely simulation based. So honestly, perhaps I am feeling a little out of place in this workshop. Okay, and there are 2 points. One is that it is interactive simulation based, and the other point is that it is unilateral teleoperation, which allows us to use this well inexpensive and easy to use devices. And in our operation scheme, the robot leg motion is commanded from the operator on a kind of step-by-step basis. And we expect that this scheme is suited for working on a heavily unpredictable rough terrain. It may be inefficient for smooth places, but it would be well useful for situations where the terrain is the ground conditions are highly unpredictable. And we are also improving the simulator itself. Okay, and I have to emphasize that this research, this series of the projects, has been mainly run by students. I have provided only initial, well, preliminary idea of this kind of setup, and yes, and after. The building a simulator was easy, but after building a simulator, it was quite difficult to make the robot work, realizing the teleoperation and balancing simultaneously. And after many trial and error, finally, and Tomohiro Watari, he well found a way to stably realize working. After that, many improvements have been made by these students. And I have been lucky to have very creative and autonomous students. And I would like to say that it is a good side of the simulation-based study. They worked separately, individually and independently. And well, they exerted their own creativity. Well, because they had their own interactive simulation setup. And they were able to continue research even under the pandemic, even during the stay-home period. Okay, so let's move on to some details about our setup and the operation scheme. Okay, here let me present some details of the setup. Actually, we have some sets of this configuration because more than one student is always working on this topic. And we are using a pair of haptic devices, Novint Falcon haptic devices. As you might know, the price is around $500 US each. And yes, it is quite reasonable. But I am quite a heavy user of Falcons, so many of my research topics are depending on them. So, but unfortunately, as you might know, well, this one is already out of production. Its production is already discontinued. So I have stocked many of them so that I can continue using them for next many years. Okay, for one set of this biped project, we use 2 Falcons like this, and each has 3 DOFs and 4 push buttons. And the simulator is developed with Microsoft Visual C++, and the sampling cycle is 1 millisecond. And well, the time step size in the simulator, it's 0.1 less than 0.1 millisecond. And we run more than 10 time steps per sampling cycle of Falcon. And the simulator engine is built by ourselves. We built it by ourselves, except the articulate. Well, the multi-body mechanics part, it is, we borrowed the source code of Corionoid from AIST, and we appreciate it very much. And except that part, especially about the contact handling, we built everything by ourselves. Okay, and this is a kind of overview. Quick summary of our way of dealing with friction and contact, and yes, it is basically penalty based, and yes, then well, theoretically speaking, when a rigid body is in contact with a rigid ground, the relation between force and position and velocity are written in this way by using this kind of non-smooth discontinuous set-valued functions. And it cannot be implemented in simulator. But what our way is to relax that into this by putting virtual imaginary spring damper system. And well, using spring damper system is, well, it's kind of a normal conventional way, but our point is that we rigorously consider the force balance between the spring damper system and the rigid frictional contact forces. And so, well, now we have differential algebraic relation between the displacement and force, and it is discretized by using implicit Euler, and we get the analytical solution, closed form solution to get the forces. And well, it is closed form, so it's computationally cheap. And well, by using that, we can stably deal with the contact of friction. And without that, perhaps there might be chattering in the static friction or some unnatural sticking force due to the damping force. Okay, and well, then in our simulator, the contact is handled at each pair of point on the surface, so it is extendable in many ways. Okay, and this is how to operate the robot in our simulator. And in the double support phase, the robot does not react to the device, but when the device is raised, the robot tries to lift the foot. And to do that, the robot center of mass is moved. When the left device is lifted, raised, and then the center of mass is moved to the right, and after that, the left foot is raised. And after after the left foot is raised, the position becomes operable by the interface device. So, well, the point is that falcon position is translated into the foot position. Foot position, the lifted foot position relative to the supporting foot position. And push buttons, by push buttons, we manipulate the ankle, the yaw angle of the ankle, and the roll pitch angles are set compliant to external forces. And yes, then our operation scheme is, well, every single step teleoperation. And well, again, it would be suited for heavily uncertain terrains, which cannot be handled by automatic gate planners. And it is unilateral teleoperation. And so, well, yes, of course, it's not very immersive, but there is no haptic feedback, but it's free from, well, feedback stability issues. And the interface devices can be very, well, simple one, inexpensive and easy to use, and it is non-restraining. We don't have to attach anything on our body. And well, we expect that there might be some domain of applications where, well, this, well, operation scheme is more beneficial than bilateral scheme. And the technical problem is that it must be, the robot must be responsible to the real-time command from the operator. But in the same time, it must maintain the balance. And the robot must move as the operator intends in normal situations, but it must not fall even with erroneous or unskilled operator commands. And there are some variations. And well, please look at this. There, it can be even manipulated by a gamepad or even by a single gamepad. Because at one time, only one leg is manipulated. So it has two falcons, but at one time, only one falcon is used. So, well, we don't need so many channels to realize working. So that's why it can be manipulated. It can be operated on even with a gamepad. And we are also trying to do some simple experiment by connecting this program with a real device. Okay, and well, okay, let me talk about some technical matters regarding the control techniques. And this is a, well, overall control architecture, and all joints are angle controlled. And so that we assume that the joints are, well, controlled by stiff angle joint controllers. And well, from the Falcon reference, the block reference position generator, it is a, well, state machine that receives the command. And due to this mode, this provides the command velocity, reference velocity of the torso and also and command to center of mass, and the swing foot, and both linear and translational velocities. And these velocity commands are well converted into joint angles based on using the prioritized inverse kinematics. Okay, and there are some techniques we have developed. One point is that it's the inverse kinematics is it's kind of a prioritized version, and it is necessary. We found it is necessary to expand the range of motion of the lifted foot to make a long stride. And the joint velocity is basically obtained from the inverse kinematics, and well, what to say? The center of mass must be kept above the supporting foot. So, well, so there are many constraints. But to extend the leg, we have to, well, set the priority of these components lower. Center of mass position, yes, so the robot must be allowed to lower its body, and also the torso angular velocity. Yes, the torso can be lifted to realize long stride. So, well, we can see the effect of this prioritized inverse kinematics from these videos. To extend the leg, well, the robot, well, tilt its torso like this, and it also considers the joint range of motion of each joint. And by using yes, and this framework is not our original, but it is well, very conventional or historical one proposed by Professor Nakamura in the 20th century. Okay, and another point feature of our controller is a dynamic center of pressure shifting to realize quick reaction to the user's command. And well, yes, well, as I said, when one interface device is lifted, the robot must first move its center of pressure to one direction, and then well, we have to. The operator must wait for the robot move its center of pressure to well, to one direction, and it is a little bit frustrating. So. Sorry, it's well, let me. Sorry. My LibreOffice is freezed. Okay, I can. Okay. So, so the important thing is that the ZMP should be temporarily moved to the opposite direction of its original direction to allow for the quick movement. And yes, and it is realized by using the framework of auxiliary ZMP framework of Dr. Kajita. And okay, and we also use our sliding technique to handle some saturation. Perhaps I should. Oh, okay, and well. Then we use some variant of this one, proxy-based sliding control, to deal with the to realize the bounded acceleration of the body. And well, we haven't analyzed that well theoretically, but empirically we are having result that it makes well stable behavior. It results in stable behaviors. Okay, and there are some other techniques, and well, the robot can, for example, well, this one, the robot can stand up by using their arm. The arm is manually manipulated by the Falcons, and we can switch the arm control mode and leg control mode by using push buttons. And I guess this kind of development would be impossible with conventional offline simulator. It can be done only by interactive simulator. Okay, and there are some discussions. Okay, and our operation scheme, it's I'm repeating that it's well suited for heavily uncertain terrains, and unilateral operation is it's very easy to use. And the open problem might be, yes, it must be combined with semi-automatic planners. And we have to guarantee that well, it must not fall even under any situations or even under any unskilled operation commands. And well, the interactive simulation. So I think that it is it may be controversial, but okay, this is a common benefit of offline simulators. But well, one good point of interactive simulator is that the fluctuation of hard command, it works as a natural disturbance to the virtual environment, and trial. And we usually do trial and error to develop controllers, but this kind of fluctuation or perturbation imposed by hand command produces similar effects like those in real experiment. And well, yes, the offline. Yes, the bad thing of offline simulator is that the planned motion and the planned prescribed disturbance would often result in over-optimization of the controllers. Such thing would not happen in interactive simulation. And I want to emphasize that it might be rather enjoyable than offline simulation study. And this is well, a part of TV program. And well, he is a TV comedian, and he visited our laboratory, and he operated our simulator. And I guess that, well, the TV wouldn't be interested if it was an offline simulator. Okay, so and I guess that it is good for education and outreach purposes. Okay, and let me skip this. Okay, and okay, that's it. This is the concluding of our presentation. Okay, and we introduced this kind of setup, and it is unilateral, and it is interactive simulator based. And of course, we are so we are calling for collaborations, especially those having real hardware. Okay, and that's it. Thank you very much.
Thank you very much, Professor Kikuuwe. So I think that we just have time for a very quick question. So this might be, have you thought about extending this system to have a bilateral manipulation using feedback on the using Falcon?
Using Falcon, I guess it wouldn't be. It would be difficult because of the resolution of the Falcon device. Its capacity of force feedback is not very good. So if we consider bilateral feedback with bilateral control, well, we have to use a better, more expensive haptic device.
Okay. Thank you very much for your presentation, and we hope you join the panel discussion also.
Okay.
Thank you very much. Thank you. Let me now present our next speaker. So our next speaker is Dr. Abderrahmane Kheddar from Cisneros. So he received the bachelor degree in computer science from the National Institute of Informatics in Algeria, and the master's and PhD degrees in robotics from the University of Paris 6. He's currently the co-director of CNRS IIST Joint Robotics Laboratory in Japan. He's a founding member of the IEEE RAS chapter on haptics, the co-chair and founding member of the IEEE RAS Technical Committee on Model-Based Optimization, a member of the steering committee in charge of the IEEE RAS liaison of the IEEE Brain Initiative, a founding member of the IEEE's Transactions on Haptics, a member of the editorial board of several robotics journals, a titular full member of the National Academy of Technology of France, and a Knight of the National Order of Merit of France. His research interests include mainly haptics, humanoids, and thought-based control using brain-machine interfaces. Today, he will give us a talk about teleoperation, telepresence, and embodiment of humanoid robots. Please welcome Dr. Abderrahmane Kheddar.
So thank you very much, Rafa. Is everybody listening? I mean, is my voice okay and you can see me and the presentation as well?
Yes, it's not yet in full screen mode. So I see the slides, but not in full.
In my computer, it's full screen.
Probably you share the other part of the screen, maybe.
Yes, yes, you may share all your screen in order to so that what you see also we can see.
Yes.
So okay, I don't know what to do exactly now.
So you now stop sharing if possible. Then if you start sharing again, then you can select like a screen 1 or a screen 2 if you have two screens.
Yes, when you share, you can select which screen.
Okay, then I am. And how about now?
Is the same one, the same one.
So now I will make it full screen.
Okay.
And now?
Not yet. It's the same as before.
My two screens, it's full screen. So
okay, so what you can do, sorry, what you can do now, if you again stop sharing, but you keep it full screen, and then you can try to share the one of the full screen.
Okay, so how about now? Because I pushed on a button, I don't know what he did. Is it okay now or not?
Not yet.
So because I have two screens, so maybe I have
to switch. Yes.
Yeah, you can.
When you share, you can select which screen you share. So
yeah, I share only the I share the application. So
yeah, instead of the application, you can share not the application but the screen.
But the screen.
On the one that you are going to have the full.
For that, I will make it again. So just wait for the things to come.
Yes.
I can switch off. I didn't know that it will have a problem, but.
No problem.
Okay, I will start again sharing. So you want me to share the screen first, right?
Yes. It's better if you start the presentation and yes. Now there is we can see your screen. So if you start the presentation, maybe it will appear in that window when you start the presentation mode.
Okay, I need to find what is this. Now I started. How about it?
Maybe there is a little.
No.
And not yet.
Now I have the two. Okay, so what I will do is very simple. I will switch off one of the screens. That will be much more convenient for you, I guess.
Yes.
And I will do it. I will share it again.
Okay.
Okay. Now I switch off one of the screens and just wait for the menu to bring back. Okay. So I will stop sharing.
Yes.
And then I will share again. Okay, now I share this one. And if it doesn't work now, it means I cannot do anything else, huh? Because now I switched my screen.
And yeah, now start the.
Okay. Is it okay now?
Let's see.
If the large of the PowerPoint is not high, maybe you can send it to us. We can share the screen and you can talk on top of that.
The problem is that it's too heavy and
okay.
And there are many things that I cannot. Yeah. So if it doesn't work now, let me know.
Because what I'm afraid what you're doing is you're trying to sharing your window instead of a screen, so that's why you cannot see. We cannot see your when you go to the
my PowerPoint only. So if I click now, I have like 4 windows that appears, 5. So one of them is the screen, the whole screen. The other one is the workshop. I don't know why I have to do, yes, it's the Teams. The third one is the PowerPoint, and the other one are the web browsers.
So, yeah, it should be the first one. Let's say where is written a screen 1 or a screen only.
But I don't know why he.
Sounds good.
It's okay. Now it's showing.
Okay,
perfect.
So sorry for that. Yeah, for the inconvenience. So I had to switch off the other screen. So thanks a lot for the invitation for the organizers of this fantastic workshop. It's very timely, and I don't think I would disappoint you a little bit because I don't have many new things to share with you. Not any breakthrough. So, but you will be surprised that that there are many things that are a bit oldish. In fact, because of this Avatar XPRIZE, I have tried to look into the literature and see what has been done since long time ago. And surprisingly, I'm stuck in the same problems I have seen in the 1995, 96. So, so then you would be probably surprised to see some of the things that has been already done. And I would share with you my thought about some problems that we are, that probably are interesting for the community to know about humanoid robots. So first of all, a bit of historical background, because I guess that it's important to know where this teleoperation started. Okay, it dates to the 18s, the early 1845, 40s, let's say, where Goetz was trying to do master-slave systems that were mechanically fully coupled, okay, to operate on nuclear contaminated objects, and to protect, of course, the operators from being contaminated in nuclear power plants. The first system on the left, up left, was fully mechanically coupled, in the sense that what is interesting in telerobotics is to, of course, is to control a robot at a distance, but then to be able to replicate the constraints of the motions and also the experienced forces at the contact at the master side. The revolution came when this mechanical coupling was turned into a mechano-electronical coupling, so where everything was mechanically and electronically surveyed. So basically, this mechanical linkage was replaced by actuators controlled analogically at the beginning. And in fact, this whole mechanical coupling between the master and slave system was replaced by servoing. Okay? And then this was really the revolution of telerobotics, because at that moment, the master and the slave were not necessarily thought to be identical. And in fact, we started to try to operate robots of different shapes with masters' devices of different shapes. Okay, and this is what you could see. So this is what I call the second revolution of telerobotics, is when the robot started to move. And this is basically what humanoid teleoperation is about. You have a robot for which you don't really have a master that is identical, except, of course, some of the colleagues that are developing like master devices that are kind of a super exoskeleton that you wear in order to control this robot. But you will see that it's not that easy. And then the other part is that you could also move, okay, which is interesting. Then, because of this revolution, there has been a lot of. The first, of course, is from the analogical coupling of the mechanical system replacement of analogy servoing was transformed into digital control. And since the computer was integrated basically to control the robot, then several other aspects has appeared in terms of assistance. And then obviously there is the dissimilarity that I spoke about, and then you have new applications that went far beyond the domain of nuclear power plants. But this you know already. So what is interesting to sum up is, in my opinion, this is what I wrote in the early paper on this because this was part of my thesis that was published in 2001 concerning the what are the different strategies. So U is the control input of your master or slave system. So M stands for master and S stands for slave. And then basically you have the P is the states of your system that you feed back through a mapping F. Okay, and basically the first one is probably what you know as bilateral coupling. The three others are what we call, probably the two others, sorry, is following up what we call the shared autonomy, where some part were left to be done by the user itself, and some part of the task is done by the user, or some complementary aspects of the task are done autonomously by the robot. And then there is this fully supervision control, where in fact you control the robot in a full supervision mode. You don't have really a bilateral coupling. And in whatever you decide of what is the best control scheme for your robot, there are three aspects that are important because these aspects are generally, antagonistic. Okay, so the usability, so how much is your system usable, which stands more for ergonomic studies. How much is your system transparent? It means that you are how much you feed back the information with high quality without being necessarily hindered. But in fact, the transparency, the ideal transparency, if you write it on theoretical aspect, it cannot be reached. It's impossible to have an identity because of you have already, you can try to reach, of course, this ideal transparency, but the ultimate transparency is that you don't have a master-slave system. It means that the dynamics of both the master and the robot are the identity, and this is just impossible to reach because of the physics, of your systems. Then what you can try is to be as close as possible to this identity. The third, of course, is the important aspect is the stability, and the stability of the system is the stability in general. In the bilateral coupling, it's always more difficult to achieve than in the shared autonomy, than of course in the supervision control. So it depends of what system you use, or a control strategy you use. You have to be dealing with stability. So I say that these three things are antagonistic because, in fact, sometimes in order to have high stability, you are obliged to lower the transparency. If you increase the transparency, then you jeopardize the stability, and etc. You can have different things, but at the end, you see that one of the previous talk was about this. I think it's Michael who has this nice fractal impedance. My opinion is that if you don't have the damping of the control, then it's the user who will put it. Okay, you have it somehow. Okay, in the user, but you cannot just get rid of it totally. For the next. This is the early work I did on Untitled Robotics was in fact to try to remove the master station and to even remove the robots from the feedback. It was a joint work already between my lab that was at that time in Paris and the other lab at IST, which was the mechanical engineering lab. At that time I was supervised by Philippe Coiffé and Kazuo Tanier, and both of them of course are Tanier has passed away, and Philippe now is retired. And the idea was to get to remove, in fact, the master to control the robot as using virtual reality environment to get rid of this intermediary system, which is called the master, and try to make a task in a more natural way and induce the operation, the teleoperation actions. Okay, from the task that you are doing in the virtual environment. So the feedback is localized, and then you can send, the commands to the robot. You still have the feedback to the object you manipulate. And that was at that time, of course, something interesting because I can use this to operate robot at a long distance between Paris and Cuba, but we could do this on multiple robots, and then many extensions of this has been done. So basically on the right, on the up, left on the up left of the right, sorry, of the image, you have the similar concept that was applied by DLR to operate the Rotex. If you remember where was the first operation or teleoperation of robot in space by that time Gerd Helsinger. So mobile robot teleoperation date to 1988. Okay, if you don't know these things, so the question was that most of the mobile robot was operated quasi unilaterally, okay, in terms of the control. And people was trying to see what kind of, whether we could apply the bilateral control, okay, coupling to the mobile robots, which have a totally different dissimilarity in terms of functionality, in terms of motions, in terms of constraints between the master and the slave. Okay, this is part of the image that is at the nuclear authority in France, that is one of the schools of Jean Vertu at that time, who is the father of direct drive force feedback devices, the ME23. And the question at that time was, what do I feedback? Okay, if I control a mobile robot, so the forward mapping might be easy. It's like if I move, then the robot has to move at some direction with a given speed. But what do I need to feedback as force feedback? Okay, so then there was a lot of approaches. I will not have the time to deal into all of them, of course, but some were using a bit of a combination between joint limits, balance margins, which is important for the humanoid, for instance, applied torques on the robot, so inertia force wrenches. So how can you feedback in terms of force the inertia that is operated on your robot, slip detection, amplitude, contact, and the conclusion was it was not a trivial choice, okay, on the feedback. Then for a European project that we had in which we were working together with TUM, it's Martin Boost group. We were at the early, I don't remember, but it was probably 2005 or 6, we started to work on this in the frame of this Robot at Collaborative Working Environment EU project, in which we were interested to know how humanoids were used, okay, on working, on manufacturing at that time. It was building, but how we could control them, okay, as I saw in some of the applications. So we have the robot, which is the humanoid. We wanted even to do better. We wanted to have the humanoid to operate collaborative work, okay, with humans at a distance, and that are controlled in another part. And we had discussed a lot about what coupling, for instance, if you start to couple only classically between the terminal points, so you might induce or reach something which has a totally dissimilar aspect, okay, where the human operator is completely not in a good attitude and positioning with respect to the humanoid robot. Now that wasn't good, okay, to do. The other, we tried to see other postures like controlling also simply the attitude, but then the master operator was immersed, and that was a bit of a problem. Then we tried to do both, basically, to have a control of the attitude plus, okay, the bilateral coupling of what you experience at the contact. And at the end, we came up with this video, okay, where you could see the first
telemanipulation task.
This was in 2008.
In this experiment, the force position control architecture has been implemented, whereby forces are sent from master to slave and positions from slave to master. Haptic, visual, and auditory feedback from the teleoperator make the operator feel present in the remote environment. This experiment is very innovative since the task is carried out in a cooperative way, whereby the human operator located at the teleoperator's side, the humanoid robot HRP2 is used. The robot arms have 6 degrees of freedom and are equipped with 1 degree of freedom grippers.
With 2 arms,
with its 2 degrees of freedom, the robot's head can pan and tilt. The video stream of the stereo camera is transmitted to the operator's side.
Then we increased this, and that was the work of Paul, one of my PhD students, okay, to include walking, because at the beginning we were just having a robot that is standing at one position, so it wasn't interesting, of course. You can go dig into the details, but basically we were still using, we started to use at that time task-based approaches where we were having our stack of tasks, that is the control in the task space of the whole robot, that we simply apply to our case here. And you could see that in this video, which dates to 2009. You have so this is the normal where you operate the robot through contact interaction, and then of course you have this mobility. It's very slow. I agree with you, but at that time you see how the head-mounted displays were. They were more expensive than what you could buy now. And you have this mobile platform that was used as a master-slave to control the robot for this particular task. Later on, because of the another project, this humanoid project, we tried also to see whether we can control a humanoid robot in multi-contact setting. This is extremely difficult because then the feedback was completely not even envisionable. How do you do what kind of master system? But the application we had here was more modest in the sense that what we wanted to do is to have a person that is doing a task in a real setting, when we get his motion basically, and then we try to copy the multi-contact aspects, because with Airbus we wanted to enter into very narrow spaces, and we were at that time trying to see if we can teach the robot by using teleoperation to plan multi-contact motion inside some industrial settings. And there was the retargeting, and the problem was not just retargeting the motion, but it is retargeting the motion with the contacts. It means that we don't only do the monitoring of the motion of the robot in free space, of the person in free space, but the monitoring of the motion in a multi-contact setting of the person, and try to replicate this with the robot. Of course, we can go into details for the paper on 2016. Since then, we didn't do much. I think it's one of the most challenging aspects to do in teleoperation of humanoid robot. And you shouldn't worry a lot about the master side, because basically the master is the environment in where you will operate. So what could play the master is your environment, in fact. Then for teleoperating humanoids, obviously the problem will be that when you start working, everything will become much complicated. If you want to have a bilateral coupling for humanoid while walking, for me, this problem is still open, and it's really interesting because you have to redesign basically your working pattern so that it is tunable both in time steps and step lengths. And then you have also to design an observer that is taking into, that is capable of guessing whatever is your situation, whether you are in, you are standing still at the same position, or you are in a trade mail. So how can you guess what is your step timing and length observer and step lengths? So the preliminary work of this was done by Daniele, one of the former PhD students I had with Pierre Brice-Gilbert and Bernard Espio. But it wasn't really tried on the real humanoid robot, and we are reconsidering this aspect with a new PhD student, Antonin Dallard, for which I can show you some of the work later on. Then, of course, you can have also the problem of large field of view that can easily be, in my opinion, enhanced using SLAM. And you still have some commonality problem with mobile robots, but like how to feed back critical features such as balance, joint limits, etc., dealing with kinematic dynamic dissimilarities. Some of the previous talks and maybe upcoming ones will speak about this, but it's theoretically very difficult to have a full bilateral coupling, in my opinion. So dealing with perception mismatch is also one of the problem to deal with. Like if you are tall and you're operating another size, a different size humanoid robot, you might have to deal with the perception mismatch. You could call into rescue SLAM for some of the problems, but you cannot solve all of them. So for me, the really breakthrough in humanoid and interoperation would be the embodiment science. It means for the moment we have dealt only with the transparency, stability, but there is something which goes beyond the telepresence, and it's not really well understood in robotics, is the embodiment. Beyond telepresence is what maybe Tachi has mentioned about teleexistence, but it's not clear what that really means, exist in another world. I would prefer the term that you own another body. okay, and what is the mechanism by which beyond the telepresence you are not like having high fidelity feedback from the environment that you are touching with your sensory stimulations, but really reaching the point where you break the mental the mental construction of your body that the robot that you are operating at a distance is in fact yourself. It's your body. It's not different from your body. So this is the science that we started later on. But just to show you, for instance, what we are doing with this full humanoid with Anton and Dalar's work, okay, about how you could design maybe stand-in motion. Okay, for the moment here, he's using joysticks. Okay, but we are always interested by having teleoperation where the person is touching, okay, another person or interacting with another person. And this is for me what normally Avatar XPRIZE is about. Okay, not only manipulating the object, but also being able to interact, okay, with the objects, with the person at a distance. And now Antonin is feeling basically through the force sensing. You can replicate some vibrations on these joysticks that you are using with the head-mounted displays, and you can feel at what moment it's touching. Since also the robot is embedded with the capacitive sensing, you could probably also make the robot aware of the presence of the person, okay, and do like full body interaction. I'm not sure how much I am far from my talk. You should tell me if I am overpassing or not, because I don't have another screen, so I don't have the watch. I would probably speak just a little bit more about these embodiment issues, okay, in which probably one of the most important experiment in terms of the fundamentals is this rubber hand illusion, okay, where the people think you have basically someone stimulating the hand, and then you have another person like having his hand, you have two hands, one which is fake and the other one is yours. And there is another person who is stimulating similarly the two hands basically at the point until which you think that this hand, which is a rubber hand, is yours or is part of your body. And understanding this is important, and maybe one of the most challenging aspects is to not use a master system at all, and you are embodied in a robot body, and then by thinking, okay, you might be able to control your robot by yourself. And so I will skip these details. I think you can see part of the video of what we did in 2011, okay, with using brain-computer interface to operate a humanoid robot. Obviously here,
robots are no longer the stuff of science fiction.
the idea is not bilateral coupling at all, because you cannot do this by bilateral coupling. The only aspect, the only control that is possible here is a pure supervisory control, where basically you try to be immersed of what the robot is perceiving and try to guess the intention of the task from using any of the brain-computer interface features. Then I skip this one. So we did also experiment with real patients that were embedded with ECOGs, okay, to do exactly the same thing. So getting the person to think about what glass he has to take, for instance, and then make the robot take it. The problem here is, of course, there is no feedback. So then how you can embody something in which you cannot have like classical feedback as we think. In fact, what is important is that your robot really does the task in the way that is expecting your brain to perceive it, okay? Because you can go with this glass with different motions, okay, but there is probably a subset of motion for which you think that you are under the control of the motion. And if you think that you are under control of the motion and the motion is really made in the way you expect it to be, then you have a high chances that the embodiment would occur. This is, for instance, a special case of what you could do with embodiment that you cannot do with any classical robotic system. Is this person who is seated on the chair, Damien, is trying to control this robot using brain-computer interface, but the robot will manipulate this. It manipulates, in fact, the self. So, and this you cannot use classical master systems because Obviously, if you want to manipulate yourself and control the robot at the same time, you cannot. Okay, you just cannot. So the only way to do such an experiment is by having a thought control where the robot is controlled by thought, and then you are controlling the robot to manipulate your body. It means to manipulate yourself. So here, the humanoid robot is under control, okay, but it is also manipulating the object by the control of the person. And what is manipulating is yourself. And this is very interesting also in terms of scientific aspects of telerobotics, of how you could get into a system that is capable of controlling your avatar to manipulate your own self. And of course, you have a lot of applications for people who are in need of assistance for such systems. And we have done some basic research thanks to Laura Emery, French, which wasn't a roboticist, who came to our lab, and she wanted to see whether this embodiment, okay, is something that we can model. It's something that is occurring even if if the shape of your system is not the same. Okay, so for instance, we try to do the rubber hand illusion, okay, but caressing the arm of the robot, where of course Laura is completely embedded, okay, in the robotic system. So basically, what the conclusion of this study was that the shape, okay, doesn't really matter to get embodied into a robotic system. We tried also to replicate some of the things that was found mostly in neuroscience, such as the otoscopic reproduction. I would not speak about it. I just ask you to go into the paper if you are interested to see that it's possible to replicate, okay, things that are found, phenomena that are found on neuroscience, where here, in fact, the robot is controlled to see, you are seeing yourself through the mirror when you are embodied in this robot. And the question is whether, when we ask the people, is whether they are seeing themselves, they recognize themselves as a self, or they recognize themselves in the robot. So that was very interesting things to do. More and final ones is the possibility that by embodiment you perceive touch even without feedback of touch and without touching something else. So here you see that the persons are not wearing any haptic devices. Okay, and we asked them to embody a humanoid robot to touch curtains, as you could see here in the video. And then we asked them whether they felt something on their hands, and surprisingly, people felt tickling, okay, on their hands, as if they were touching something, and obviously there were no feedback, okay, provided to them. So this concludes my talk. So my personal impression is that there is not much rediscovering of teleoperation from what I see in the current work. The basics and theory, there is, in my opinion, no real breakthrough for the moment. Okay, except that the prices of the HMD are more affordable from when I was doing my PhD. It costs really very expensive at that time. I remember it was nearly about more than 10 euros to get HMD. And it's still hard to conceive haptic feedback systems that are not bulky with high transparency. The thought-based robotics is something that is interesting. It's extremely complex to achieve in real time in bilateral coupling, and it's more suitable to supervisory control. And in my opinion, if there is something to be done, which is really important and which is really a breakthrough, would be this going beyond the telepresence by embodiment. For me, it's a science to start. And the question I have now in my mind is whether we are capable of building a kind of an embodiment sensor. Thank you very much for listening. And this is just to tell you that we are participating to the Avatar XPRIZE. I think Rafa is one of the leaders for that. And for our team called Janice, please visit our website, and that's all.
Thank you very much, Dr. Kheddar, for the nice talk. So if you agree, we can give you the questions during the panel discussion, just yes. To keep going with the next presenter. So thank you very much again, and see you soon. Okay. So our next speaker is Dr. Marco Hutter. He's an assistant professor for robotic systems at ETH Zurich and the co-founder of Anibotics AG, a Zurich-based company developing legged robots for industrial applications. He is part of the National Center of Competence in Research, NCCR, robotics, NCCR digital fabrication, and principal investigator in various international projects like EU Think and challenges like DARPA SUBT. His research interests are mainly related to the development of novel machines and actuation concepts, together with the underlying control, planning, and learning algorithms for locomotion and manipulation. His works find application from electrically actuated quadrupeds like Animal to large-scale autonomous excavators used for digital fabrication and disaster mitigation. Today, he will give us a talk on the teleoperation of a heavy-duty legged mobile manipulator for disaster mitigation. Please welcome Dr. Marco Hutter.
Thanks a lot for a nice introduction. Let me share my screen. So please, you can't see it, otherwise I'll continue. As was mentioned in the introduction, so I'm working a lot on animal robots, so you see this on my shirt, but today I'm going to talk about something completely different, namely these very large-scale excavator machines and how we're using them in a teleoperated fashion for disaster mitigation. So how we can bring these really to real-world applications. So for those of you who don't know these machines, I want to give a very quick introduction what we're talking about here. So these are walking excavators, so other people call it spider excavators. I would say it's like the most versatile multi-purpose machines that one can find out there. And like they're essentially used whenever it comes to scenarios where it's hard to reach. So in the mountains, in riverbeds, after landslide, rock slides. They were also, some of them used after Fukushima disaster for cleanup. They're often used in forestry and so on and so forth. So this machine that we are using is a Menzimuk M545. It's like an 8-ton, a 12-ton machine with like 8-ton payloads and 9-meter reach. So you can imagine of a large-scale mobile manipulator, and you can do a lot of fun things with that. Now today's machine, they are fully human controlled. They have like 28 joints, so 4 per leg, and then in the arm and at the end effector. And the human sits in the machine and really coordinates with like his 2 joysticks and another 4 thumb joysticks on each of them to complete machine. It takes them roughly 4 years until they're really good at, but if they're really good at, they can do all kinds of crazy maneuvers. Now the question is, how could you use something like this in a teleoperated or remote control fashion? And that's actually something that is already done today. If you look at existing solutions, you're going to face only solutions like this. Remote controlled, so you have human operators that are standing relatively close by. They have a couple of hand joysticks, which they use in order to move everything, a joint of that, and they visually observe in how the machine is moving, use that to get kind of an internal state estimation of that and control it in line of sight. So we have limited distance, very limited perception because you really can't see what you have to work with, and it can be uncomfortable and dangerous depending on where you have to stand. The problem is that when getting the operator out of the machine, you lose a lot of sensory information. So there's no motion feedback anymore. And when we talk to the drivers, they typically say like most of the stability comes from my ass sensor because I'm feeling how the machine is moving and I use that in order to control it, but we completely lose this. We have limited acoustics and all of that makes it very hard to control. Now, making it hard to control means that we have to find other ways in how we can assist them such that they can still teleoperate them and achieve a similar level of skills or agility while not being in the machine. So what we came up with is a solution that essentially combines a teleoperation platform, which is an operator stand, where you get like motion feedback, visual feedback, acoustic feedback, and where you have the machine control interface. And then you can, from that, over different networks, whether it's 4G, 5G, or you can also build up your local Wi-Fi system, control the machine. And a machine is not a native machine as you would buy it off the shelf, but it's a semi-automated one where we have simplified operations, where we can like actively control its stability, so the operator doesn't have to worry about the machine tipping over or falling over. And you can increase the safety, for example, by having collision avoidance with itself, giving additional hints in how it's supposed to be moving, and so on and so forth. And we did a variety of tests with these machines over long distances within Switzerland, also across countries, and I'm going to show you this at the very end of my talk. Now let's dive a little further into the approach we are taking here. So the approach is, in essence, that you have on the operator side, you have this moving platform, which gives you motion feedback, and you have visual feedback that comes in through monitors that display whatever the machine perceives on the other side. On the machine itself, we have a camera and a laser sensor setup that sits on top of the machine, where we do all the video compression as quickly as possible on the machine, and then send this over Wi-Fi, 4G, 5G network to the operator side. Plus, additionally, have this semi-controlled excavator machine. I'm going to dive first a little bit into the machine side and give you some details in how we make this semi-autonomous. So here are two excavators that we have at hand. First step was that we had to overcome the current limitations of like off-the-shelf hydraulics. If you buy such an excavator, they have like multi-staged hydraulics with large overlaps. They're meant for flow control by human inputs, but they're really bad at like doing feedback control on it. So we customized this. We also went deeper into how we can optimally control these hydraulics. We have included pressure-based feedback such that we get a sense of the interaction, and we use this in order to determine and adapt stability. Plus, we have full position feedback from all joints that we have like a continuous estimation of how the system is standing and moving. Then included sensing equipment with like high resolution cameras, forward-looking cameras, sideward-looking cameras, and backward-looking cameras. We include 3D perception through LiDAR sensors, GNSS in order to precisely locate the machine, IMUs and joint sensors to estimate its motion, plus, as I said before, the different communication channels that we have. I don't have time to dive too much into the details in how we automated the machine, but I would like to show you only two videos for that. The first thing was we made the machine such that it autonomously adapts to the ground. Now, we are here in the workshop of dynamic legged robots, so most people of you might ask me, why the hell do you call this dynamic? And the reason is primarily because of the fact and how it is controlled. So the controller that runs on this machine is pretty much the same one that we're running on a walking quadruped. It continuously adapts the interaction forces based on optimization and how the machine is standing and supposed to be moving. And by that, creates a very dynamic interaction with the environment, where, for example, here on uneven ground, you can still keep the machine level and just move across it as if there was no unevenness in the ground. And that, of course, if you have a machine that can move autonomously and you don't have to worry about how to coordinate these individual joints in order to make the system adapt to the ground, simplifies operation a lot. So all of a sudden, like this part of the human cognition that is necessary in order to make the machine move safely and stably is gone and solved. The second thing we added here is that we want to achieve high precision and effective control in an automated fashion. So that would allow you to essentially have a much higher level human operator input. So instead of coordinating individual joints to achieve an end effector motion, you could directly operate the machine in the end effector space, and by that, like make horizontal lines, pick up an object, or execute tasks in a much more intuitive fashion. If you're more interested in these details, and if you want to hear a little more in how we were using also machine learning in this context in order to improve the performance, there is an ICRA talk on Wednesday by Pascal who will detail out this a little further. Now, the second part of our approach is on the operator side. So the way in how we're giving motion feedback and the way in how we're giving visual feedback to the operator. There's different things that we investigated here. The two primary and completely different concepts are on one side, on the left-hand side, kind of a stationary screen setup. So 4 gaming screens where we have high resolution and very low latency for displaying the visual information. On the right-hand side, you see a setup where we had essentially a stereo camera setup in the machine with a pan tilt head that is fed back to an operator with a VR headset. All motion synchronized, also like delay compensated, such that you will not get motion sickness if you're moving at the same time your body and your head. And we evaluated both of them against each other for various different performance indices. And it turned out that actually what you see on the right-hand side, although it looks a lot nicer and fancier, that there were quite a number of problems and limitations. I listed them here, probably not complete, but certainly some aspects are in the current VR headsets that we have today. So even if you take the best VR headset one can buy, they have still insufficient resolution for many aspects. Even like with 4K or 8K, we are close to where we are getting, but we should not where we're supposed to go, but we are not yet where a human eye would require it. We had limited field of view, so you had a hard time to recognize what is happening on the side. And then the last element, and this was really the most important one for us, when we did long-term operation tests, also with, let's say, unexperienced roboticists, but really the operators that are using the whole setup in the field, it turned out to be pretty inconvenient for them. So if I say long-term, we mean like we had them for week-long tested by certain operators, particularly the setup on the left-hand side, and get like collected feedback in how they appreciated the solution or not and where the bottlenecks are. On the left-hand side, which was preferred by the operators, you have a setup which is relatively simple, but at the same time, it allows you to display various additional information that is hard to bring into your headset. So for example, you could show them 3D point clouds of the environment. You could show them a complete setup of the state of the current machine and how it's standing in the environment. And all of that together allows the operator, while looking at the screen, collect a lot of information and interpret that information internally the way that he or she needs it for operation. Turned out that there was a pretty rapid learning curve until operators were ready to deploy this in reality. Biggest challenge today is that we still have to somehow find ways in how we optimally recover depth perception, particularly if there's like bad lighting conditions. This is things that we're working on right at the moment. Then we had a motion feedback device, which essentially can replicate the exact same motion as what one sees in the excavator itself. That means 45 roll and pitch and 360-degree yaw motion, so full rotation. It's supposed to be 360 here. This is something we had to build ourselves because like off-the-shelf simulators, they were not able to achieve this level of roll and pitch while having the ability to permanently rotate. And what we do in this thing is that we replicate how the machine is standing, and it gives the operator a sense of how you are with respect to your environment. Then for the control interface, also here we tested various different setups. First one was the exact same excavator joystick, but additionally with some haptic feedback that allows you to do classic control, which is important that an experienced operator who is typically sitting in the real machine can just sit in this operator stand and start from zero with like almost no training time. Haptic feedback and vibration feedback was then used, for example, to indicate whether the shovel is close to the machine, and by that to show them if there is hazards or something like this. We also tested end effector task space control, both with like just motion feedback and also with certain haptic feedback. It turned out that the students who did the studies and some external people who did the studies, they were able to learn a lot faster. And also the performance was quickly good. But at the same time, if you gave this to the operators who are using that in the field at the very end, they were not so happy. All of them preferred to just go with the classic joystick setup because they're used to that since many, many years for operating machines. And then the last one, and this is more for the gaming generation, like our PhD students, most of them like to sit in the machine and just use the gamepad and control the end effector in task space. But that's something that will take a lot more time until we bring this to the field, to the operators that are actually using that on a daily basis. Then for the image processing and networking, I will not spend a lot of time on this. If there's detailed questions, we can discuss this also later. So what we do here is we have cameras with high resolution PCI cameras to have a fast image acquisition. Then we do GPAs, the compression and all the exposure control and auto white balancing and stuff like that on the machine itself. Compress it, send it over the network, and display it on the operator side. I see that time is getting short, so I'm speeding through this. We did tests over 4G, 5G, and Wi-Fi with different setups of machine-to-machine communication, VPN communication, to give you just a rough order of magnitude of where we are today. We're talking roughly about, let's say, in the ballpark number of 50 milliseconds delays, if you're talking glass to glass, so both network and image compression and image display, you will stay below this 100 milliseconds delay, which people tell you this is more or less what you can still very well cope with, and there's no big issue for having, for being able to still operate the machine. Important is that there is a great image quality, that there is no artifact. So you see here in this video, and I hope this plays also well on your side, you see here over 5G network, public network, so there's also other people accessing the whole setup, that we do like compress the data depending on the current load of the network, adapt this accordingly, such that we still get a good perception at any point in time. Now with this, we have a solution ready that can be used for different types of applications. We tested this in different POCs. Here was a test case set up where there was essentially like a car collision with an explosion, and we had the excavator being teleoperated in order to remove cars from a blocked road. And it shows a little bit on where we can go with excavators that have like many tons payload. It's just like picking this car as if it was nothing. Second use case, this is a demonstration of an earth slide. It's a place in Switzerland where there is rock falls relatively frequently at the Axenstrasse, and it's also at the same time an important road. Whenever there's a rock slide, they have to block everything, both railway and roads. And the idea was here to have a solution that can very quickly access the environment and clean it up. So without waiting first until a geologist tests if there's something else coming down, we want to rapidly deploy the excavator. So we had, with the boat, brought the excavator to the starting site and then had it going up this riverbed. So we had like a largely uneven ground where this active chassis was autonomously controlled, and the operator was then distance away, sitting in this motion cabin that you can see here, safely controlling the machine out in the field. And then the last use case, just to complete here the session, is for explosive environments. Also, this is a situation where you very often don't want to have operators sitting in a machine. It's not necessarily because the explosion is dangerous in terms of destroying or killing you directly, but also because of the shock waves that you get from the explosion. So what you did here was cleaning up an old ammunition deposit in Switzerland, or we started with the first test case there. People are expecting about 3,500 tons of unexploded ammunition lying around, and you want to have excavators that are able to be safely operated from far distance, going there and cleaning this out. These exercises that we were doing here are not only like dry runs, but really we were able to dig out ammunition and explosives. That shows you like how close this really is in order to be deployed in the real world under realistic conditions. The operators were always operators that never drove this excavator before. They came for the first time, and after like relatively short adaptation time, they were able to get a pretty decent performance. Of course, not yet as quick as they would be within the machine, but getting close to that. Very briefly, this is the team of people that are involved in that. And with this, I'm coming to the end of this talk. I want to just close with these two videos for people that might be interested, and then opening up for questions where these machines can be used even further in the near future without teleoperation, but fully autonomous operation for like landscaping, for stone aggregating, for building up things, just to give you a little bit of an indication of where our roadmap is going. With this, thank you very much for the attendance and opening up for Q&A session. Thanks a lot.
Thank you very much, Marco Hutter. So now the time is a little bit constrained. So if you don't mind, we can continue to the panel discussion and bring the questions right there. Is it okay for you?
Sure. You're the boss. Tell me what.
Okay, so with this, we finish the part of the speakers, and right now we are going to switch to the panel discussion, for which the moderator will be Eiichi Yoshida. Please.
Eiichi, you have to unmute the microphone.
Excuse me. Thank you for Rafael. And I'd like to first thank all the speakers who gave a great talk. So this is a panel discussion, and it's supposed to be until 7:50 in Japan, so 10:50, 30 minutes. I think we have several particular questions to each speakers from the audience and also from the organizers. So we start with this kind of particular questions, and then maybe we can address one or two general questions. So I will share the screen about the question. Or is it better like that, without that?
I can't see any shared screen at the moment.
Okay, I will share the screen. Excuse me. And so these are the questions we came up with. So actually, there's a lot. So I'd like to start with HALODI. So did you try to apply your system to the bipedal robot?
No, the short answer is no, not in reality, because the hardware is not done yet. So only software simulations on that sense. It is running the same, a lot of the same models and constraints. So it's using a support polygon for doing balance. It uses, it used to use an ICP approach, but now it's using a model predictive approach that takes more of the whole model into account. It supports multiple contact points and dynamic switching of contact points. So we have been doing tasks where we, for example, rest on an elbow while reaching forward and have multiple support points as if it would be on two legs, but the physical platform only has one leg. So then usually it's the support point could be, for example, a hand and the knee, if you're sitting on your knees, leaning on one hand, and these kind of motions, but not specific to two legs.
Yeah, but I think since you are dealing with inverted pendulum, so I think your basic technology can be applied to the biped robot also. So we hope to see you apply your very nice system to the biped robot.
Yes, thank you. And we have been doing some simulations of that as we go into designing bipedal robots. And like I said, there is very little difference really, because we're already thinking about the center of mass just as suspended in world due to the contact points, and whether that's hands or elbows or knees or the wheels doesn't really matter seen from the controller's perspective.
So I think Professor Kakiuchi and Professor Kikuuwe, they showed very nice especially the system for teleoperation for a bipedal robot. So some questions about what do you think about bipedal, the unilateral and the bilateral teleoperation? Professor Kikuuwe and Kakiuchi for the bipedal teleoperation.
May I answer first?
Yeah.
Okay. About the yes, it depends on application, and I know many researchers are working on bilateral control, and they think well, being immersive and well, the haptic or many perception feedback is important, but well, in some applications, easier solutions would be preferred, and so there must be such applications. So I guess the unilateral teleoperation should be investigated. So my direction is my focus is on unilateral teleoperation.
Yeah. So Professor Kakiuchi, so I think your whole is Kakiuchi Sensei there? Yeah. So your whole body bipedal teleoperation system is great. So can the operator feel the stability of bipedal walking, or can the operator correct, for example, if try to avoid falling with your interface?
Operator actually don't know about the instability. So stability should be concerned in the robot side.
I see.
It's also the autonomous walking. So and real-time feedback for the walking is very difficult for the operator. So in the teleoperation, now setting teleoperation device, operator should search the conventional and safety walking pattern suitable for the real robot.
I see. So so there was a question from the Francesco Ferro in the YouTube. Connection loss. So who can answer this question? For example, maybe I can ask this question to, for example, Marco. If you lost the connection, how do you deal with this kind of situation?
So in these setups that I presented today, in particular, when we have these field trials, we have a check whether the connection is there, and if there's no connection or we could lose connection, we have to stop the machine. It's just for safety reasons, so we cannot continue to operate. I think if you would have other applications where it's maybe less safety critical, and you would have just a high level aspect that's coming from a human teleoperator, then it would be a different situation.
Okay, thank you. So maybe this can bring to the question about autonomy. So maybe we can address later. So there are also questions to Abder. from Serena. Maybe you can ask questions, Serena.
Yeah. So the question was because in one of your slides you were mentioning that we have to work on the improving the retargeting and the experience for walking, and so. And this is mostly based on our experience with ICAP. We don't think so. In our experience, it was not really nice to retarget footstep or walking on a robot that is so different, like kinematically and dynamically speaking, from the operator. So I don't know if in your experience you still think that it's better to retarget each footstep and have like a synchronized walking, or if you can just find a way to, let's say, modulate or tune the walking of the robot, but synchronized, not synchronized from what the operator is doing. I don't know if it's clear. I'm mute.
I'm there. You muted.
Sorry, thanks a lot, Serena. So our experience by operating HIP4 is that if the walking is not synchronized, you have like cyber sickness really quickly. Basically, the robot is not really matching what the user is walking in the way that you're transferring your mass, your ZMP from one feet on the other, and then it just goes in a different way. So synchronizing the footstep doesn't mean retargeting, because it can be done by just rewriting the walking pattern so that the time steps, okay, are synchronized. It means if you are using the joystick, of course, you don't need this at all. But if you do with the joystick, then the robot is moving and you have these images going right and left. And you don't feel really high embodied in the robot. However, if you like to walk, okay, if you like to go into more of a bilateral coupling by having like a walking which is done by the robot. So if you want to increase the embodiment aspect, so you need to walk basically so that the robot walk. And here you have to synchronize really the walking, okay, the time steps, okay, of the human with the robot. Whether it is having the same size or not, I think it's not difficult to synchronize, okay, the time steps so that when you step down with your legs, the robot also step down, and then this shakiness a little bit of the image is well perceived by the person. I mean, you feel more embodied in your robot because you have this exact same feeling happening at the same moment. So what Antonin is doing now is even better, is trying to guess very quickly what would be the time steps just after lifting your feet, and what would be the timing and also the step lengths if you want to walk, and anticipate really on the landing phase, so that the impact are also perceived. We believe that this would increase a lot the transparency, but in fact it also the feelingness that you are embodied, okay, with your robot. So you don't need to retarget, okay, you don't need to retarget exactly the whole motion, but you need to synchronize the steps. It's exactly the same thing. If you synchronize also, if you want to grasp something with your robot, so you better grasp it at the same time at which you are perceiving that you are grasping it. So if you control your robot to grasp the bottle, for instance, so then you don't want the bottle to be grasped after, okay, but you would like to anticipate on it. And if you anticipate and you grasp at the moment where you expect the bottle to be grasped, okay, this is what I call a little bit of shared autonomy, but it is shared autonomy which goes along with your bilateral coupling. Then you have an increased feeling of embodiment. For us, it's important to work on this aspect because they are somehow new and they are not really well understood. So how we can break the mental, okay, construction that this body that you are teleoperating is in fact yourself.
Okay, thank you. So I had another question from the audience about the for Michael. So how do you demonstrate the stability with your switch behavior in fractal impedance control? This is a question from the audience to Michael.
Hi, yes. Yeah, thanks for the question. Yeah, so I mean, in order to prove stability, we make a few assumptions. So first of all, we assume that there's no desired velocity or desired acceleration. So the system is, regardless of switching behavior, is always being attracted to a stable fixed point. Secondly, all the elements are conservative, so we don't rely on any non-conservative part in order to prove passivity or damping, such as damping. And in the paper, we do have we use a piecewise Lyapunov method in order to prove stability. So the details are in the
okay.
Yeah.
So we are invited to read the paper, attend the presentation, and read the paper.
Yes.
Okay.
Thank you.
So also there's some question to Marco. First.
Yes. I had actually one question exactly from Marco regarding the you mentioned about the perception of depths in the visual feedback. So while also we are doing the teleoperation, it's one of the limitations at the moment for us, and I wanted to know if how you are trying to compensate that, or your approaches for it. Thank you.
Yes, so indeed, it's like one of the limitations and big challenges. So there's two things we're doing. First is give an extremely good image, and that already helps a lot because people have a good understanding of the machine. They can interpret shadows and scale, so they get already a decent thing. However, you will not be able to achieve this all the time. So depending on the lighting condition, if you have a hole in front of you, it might be a bit gradient. And what we're doing there, or what we're aiming at, and partially it's done, but not always in the application, is that we combine the 3D perception that we have from our onboard lidars together with the camera in order to get like assistive information on top of your image. So this can be distance measures, this can be 3D topology measures, and by that, not the same way as we get that, but by the combination of certain aspects that we have from 3D perception plus the image, humans are extremely good in then doing this merge and interpretation of how the situation is, and that showed to be pretty okay.
Okay, thank you.
Okay. So also there.
Yes, I wanted to ask a question to Mike. Very nice talk, Mike. Michael, thank you very much for this interesting work. I have just curiosity, a few questions before reading your papers, so that I read them already with the clear point of where to have to look for. So you see damping, you said that your controller doesn't require damping. Well, if you do bilateral coupling with force feedback, so if you don't do damping, basically the damping is made by the user. So you are not obliged to make a damping in controller if you do it like this scattering theory or whatsoever, because the damping is not like what allows you in fact to shape your impedance. If you go back, of course, to the physics, okay, of high frequency lines, so you know that you need to shape your impedance so that you don't have these reflecting waves. Okay, and if you take the work of Spong and Nemier before, I mean, stabilizing by adding this damping just simply doesn't let the person to do it itself. But if you remove the damping from the scattering theory or whatsoever, you can put it 0, of course. Then the user will put it. Basically, you stabilize yourself so that you don't. So where is the trick basically by using this fractal impedance shaping? So, like, how can you guarantee that it's not put by the user, in fact, or you are not shifting this from the control to put it on the user?
Yeah. So maybe I was too harsh in my talk. Like, I'm not against using damping. So damping is definitely important as it it dissipates energy, right? And that's a key component of stability, is to dissipate energy. The thing about the fractal impedance is that we're trying to show that we can prove stability of the system even without a damping component there. So one thing we were looking into when we were looking at like the energy tank methods is that they always have to measure the amount of energy flow going into and out of the system. So they have to estimate this energy flow. And that of course involves damping. So if you have a poor discretization or low bandwidth, the estimation of that energy may be incorrect, and that could impede your performance. So as a counter to that, we were just trying to come up with a method in order to say, can we still have this passivity proof so that we can show the energy coming in is not greater than the energy coming out, or the other way around, sorry. So can we have this passivity proof without relying on this damping component? So that's what the fractal impedance gives us. But still, you can then run a fractal impedance on your robot and still put damping in there to actually maintain even, say, a more safe interaction.
Okay.
Yeah. Does that answer your question?
Yeah, I will read more carefully your paper, certainly, to get the trick. I understood that, in fact, the damping is not like you are not considering it, just you are not considering in the proof. But exactly there, some in a way or the other. Otherwise, I do not see how you could match the impedances if they are different, because it's all what it is about. I mean, the idea is that stability or the oscillations are created because of this mismatch on the impedances. And the way you stabilize this, especially for when you have delays, when you have large lags, is to add dampings. If you don't add them in the control, then the user will add them by itself, because he will tend to go slower, basically, to do the task.
Yeah. I mean, the user will add it, and also, I mean, the robot also has its own inertia to sort of take into the energy. So,
okay,
yeah.
Great.
Yeah.
Maybe Kikuuwe sensei, you have some comment on the control.
Yes, about the control, Dr. Mistry, you used the torque command-based control, and also Dr. Bornish from HALODI, you use torque command-based, but the other speakers, all of them used angle command-based. You use angle control for all joints. So there are two ways, and I prefer torque control. But I also think that it is sometimes difficult to deal with. It's not safe sometimes, especially when the sampling interval is not short enough. So, my question is, what do you think about the future of torque command-based methods?
For teleoperation, especially.
Yes.
Yeah.
So, for example, Dr. Mistry, what do you think about that?
Yeah, so I definitely prefer torque-controlled robots. It's a question of impedance control versus admittance control. So, I mean, there are pros and cons. I get it. With an admittance control device, you can have higher stiffnesses and whatnot. But the impedance control devices, if you can do proper joint torque control, I mean, they give you certain advantages. Since working in the force domain, you don't have to, double integrate position and whatnot in order to get your force command. Also, you don't have to rely on force sensing. So that means interaction. I mean, force sensing at the point of contact. So that means you can interact with the robot anywhere. Like if you have a manipulator, you can interact with it at the elbow or whatnot. And so for close cooperation with humans, that's an important factor. But at least the robots that we use in our labs, they do give us nice torque control. Like the Franco Pandas give us a kilohertz loop, which is pretty nice. For industrial robots and things, maybe torque control is not there yet. But yeah, I'm not such an expert in industrial manipulators, but maybe the technology will come.
Thank you.
I think that this debate between position control or high speed control and torque control is somehow more a matter of the application context or something else. At the end, all the robots are torque control. At the end. Okay.
At the end, no.
You are sending your actuator, desired or desired function, and it will be controlling torques in any way. So, but I don't think that. I mean, there are some applications where, you can do torque control by having a feed-forward PD, low gains with the PD, and then have a feed-forward term. And I think the real problem is whether you have back-drivable robots or not. Okay, so it's not about how you're controlling this. Of course, if you add torque sensors, and frankly speaking, torque has also, now that you are using Panda, if you want to do high impacts, I think that torque control robot will not make it. We cannot do exactly impacts at contacts that are the same with the torque control and with the, but it's just a matter of the sensors that we are using that are more fragile, probably.
So I have a comment with regard to that, because I think it's not only about torque control. Like you say, in the end, they're all torque control. It's a matter of how high gains do you need on your positions and velocity to achieve whatever you're trying to do. And there's a lot of value in being able to have a high dynamic range there. So you can say, if you have a fully backdrivable transparent transmission and you come up with a torque trajectory over time and your positions and velocities are spot on, you have like a perfect system. This becomes incredibly powerful. But I think it's more actually, the more we work with this and the more we play with also different robots like the Franca, for example, it's a lot about getting the reflected inertia down. Because all of these torque control robots that use the joint torque sensors, they're trying to mask their own inertia by having some quite high frequency torque control. But you still have like the phase delays in your sensing. You still need a very high frequency controller. You have to modulate whatever the stiffness of your spring is. I mean, like it's come a long way. If you start to compare, like, I'd say the Franca is still series elastic. It's not the same as the Baxter was, because that had a very soft spring. And now when you're starting to just use your basically transmission shaft as a spring, because your frequency and resolution on your torque sensors are good enough, you're still modulating a spring system. And at some point, you don't have the frequency to actually damp your impact. And then you see your reflected inertia. And that's a huge problem. And it's a problem from a safety perspective, mostly from our sense. Also from a reliability perspective, because like if you're playing with robots in unstructured environments, and especially in teleoperation, things go wrong all the time. And you need to have your system survive that. But also if you're interacting with humans, then I think it's a lot more about, the reflected inertia than really the accuracy of the torque control. Because to be honest, the accuracy of the torque control of our robot is not nearly as good as some of, like the Franca, for example, has a much more accurate torque control in absolute torque. But the resulting system, I feel, is a lot more suited to do teleoperation, because you care more about the impact energy and how soft you can go on your impedance.
Well, about the Dr. Bonish robot, I'm a little bit surprised that your robot is a bit kinematically complicated. But well, my understanding is that solving such a complicated kinematics in a very short sampling period might be a little bit difficult. So I'm curious, how do you deal with that?
So I'll give you the hand-wavy answer and then delegate to our controls engineers, because I'm mostly on the mechanical design side and actuators. But I do know roughly how it works. So we're running a whole body controller currently that's doing single time step, and that's running at a kilohertz. So and that solves for all 24 degrees of freedom. It solves for multiple objectives, and it works really, really well. And then we have a model predictive controller that's actually feeding that. Well, right now I think it's actually linear and angular momentum that you're optimizing for, and then that runs at 250 hertz. And we're seeing really, and they were playing a lot with the frequency because the time horizon is a really big thing here. So if we're doing a time horizon of like a second, then for example, the non-holonomic constraint on the base is no longer an issue. If you're doing time, but as your frequency goes down, you get into different problems. So it's really a balance between the two, and we're going more and more in a hierarchical direction where there's an infinite time horizon MPC going at a very slow frequency that does like long-term planning, handing off to multiple layers. But in the end, we actually have a whole body controller that runs at a kilohertz, and that is very stable and works independently. So in worst case, when things go wrong, we just shut off everything else, and the robot still works based on the whole body controller, and that makes for quite safe behavior. But I don't feel that the number of degrees of freedom is really limiting. I mean, of course, if we had 6 degrees of freedom, we could do a model predictive control without a template model and go for a long time horizon, and the problem would become simple. But you can still do a lot with template models. Some of the bigger challenges becomes how do you make template models that are independent of contact points. So like I said earlier, right, if the robot sits down on its knees and is leaning on one hand, then the model predictive controller you made that did like an Anchorman steering non-holonomic constraint is completely irrelevant. And either you have to start switching template models, which you can do, but that could give you potential instabilities in the switching points, or you need to make like very high level abstractions that work for most of your cases. And generally we've been going in the last direction where we try to make abstractions that work for the general system and not have to hand graft controllers. But in some cases we do end up hand grafting controllers. But the switching of controllers is still scary.
Okay, so I appreciate your discussion, and but we are over the time of this panel discussion. So it was supposed to be until 3 minutes ago. So I'd like to conclude by asking each speakers for the future plan briefly about what the open program, your open program, and your next step to close this panel discussion. So maybe we can start from the last speaker, Marco.
So I think future teleoperated systems have to have a lot more autonomy than what we have today. So our direction is clearly towards this. So as much as we can outsource to the machine and as little as possible to the human operator.
So just one small question. So are you going to apply your teleoperation system for the leg? Not leg like animal. Maybe Michael did already, but
yeah, I mean we're also working together with Bernd's group on an Avatar competition, so it's going in this direction. Yes.
I see. So so maybe next up there. You're muted.
Yeah, I would like to thank all of you because it was really nice to see you after a long period. I didn't see many of you in person and even visually. So yes, I think it's really challenging. I have the impression that I have came back to my PhD studies with teleoperation. I thought that this was completely like not a la mode say topic, but I think it's very useful to develop this technology because the reason why we are still pushing in Sansokan to do it with CNRS is because we see a lot of potential for human skill transfer later. It could be an extraordinary technology to get the data we need for learning and for also transferring human skills to the robots. So that's why I think that it's still good to have this technology because there is this perspective of human skill transfer that could be interesting.
Thank you. So, Professor Kikuuwe.
Yes, my next step would be to completely prevent falling of my well simulators robot. So I must do that. Well, in the future, well, I would hope someone can implement our controller to their robot. Okay, it was very nice to seeing you all.
So maybe, yeah, of course, this workshop, maybe you can go the next step. Maybe you can start collaborating with one of those. I think we have a very complementary research. So, I'm starting from the last. So next, Professor Kakiuchi. Oh no, it was Michael. Sorry.
Oh, okay. Yeah, I think, so thank you for a very nice workshop. It was a very interesting set of talks. I learned a lot today. I think in the future for teleoperation, it's not just focusing on what the human can tell the robot what to do, but also there has to be the feedback of what the robot, telling the human what it can do. So there has to be this bilateral communication, and of course that's going to involve more autonomy, as Marco says. Like the robot has to be more capable to be autonomous and make decisions on its own, and not fall when it's a legged system, and then impart those constraints to the human operator, so the human operator knows what the capabilities of the system are, and that's going to be even more critical when there's low bandwidth, huge delays, like the robot is on Mars and whatnot. So so thanks again for this workshop.
Thank you, Professor Kakiuchi.
Okay, I plan to the multi-contact motion for the piped robot for the real task in the real disaster site. We want the teleoperation was an operation for the generating the motion for the robot on site. We don't program the robot on site, so we can operate the robot in the on site for the without programming.
So this is very highly autonomous humanoid.
And no, autonomous is very difficult. So we plan to operate the robot on site. So so we develop the teleoperation research.
Okay, thank you very much. So we're looking forward to seeing this this development. So Bernd, lastly, Bernd.
Yes. Was that me?
Yeah.
Yes. Thank you. So thank you for getting to present here. It's a very interesting crowd, and I think for us it's now a lot about finishing the next generation design, both the wheeled version and the biped, and then moving that into volume manufacturing. So that's a very exciting journey to really go into volume manufacturing, and there's a lot going on that part these days. So on and when we go back to the control side, I fully agree we need more autonomy. And the big thing for me there going forward, I think super exciting problem is balance in the presence of humans. Since we have a system which is very lightweight and compliant, is it okay to lean on a human? Like how close to human can you go? How should you fall if you see that you can't drive because you'll drive over someone's foot? And like how do you put all these constraints in? Because in general, if you have a lot of space around the robot, you can't tip it. It's very, very stable. But if you start to constrain the environment, the problem becomes very, very hard. And I think that's some interesting research areas, how to traversable terrain, basically, with humans involved.
Yeah, thank you. So maybe last comment from the Kourosh to close.
Yes.
The first session.
Okay. Yes. Yeah.
So thank you for your tremendous work for arranging everything, and also I'd like to thank all the organizers. So, Kourosh, please.
Yes, thank you all again for accepting and joining us at the workshop. I think by now we can close the first session. Then in the afternoon, we will start again the workshop at 14:20, so around 1 hour and 20 minutes. And by that, Joao will moderate the workshop. Thank you again all.
Thank you. Thank you for everyone.
Thank you, everyone.
Hello, Claudio.
Hi, Joao. Good to see you.
Yeah, good to see you too. How are you doing?
Good, good.
All right, let's see. I just... All right, so let's get started. So welcome back, everyone. So this is the start of our afternoon, for some of you, section of our workshop today. And we have some very exciting speakers today. So let's just get started. It's my very pleasure to introduce Claudio Semini. So Claudio is the head of the Dynamic Leg Systems Lab since 2012 at the Italian Institute of Technology. So his group develops high-performance hydraulic robots, including HiQ, HiQ2 Max, and HiQ Rio. He holds a master's degree from ETH Zurich and a PhD and a postdoc from IIT, in which he worked on the development of and control of the quadruped robot HiQ. Claudio is the author of more than 100 peer-reviewed publications in international journals and conferences, and he's the co-founder of the Technical Committee of Mechanisms and Designs of the IEEE RAS Society, and the coordinator and partner of several EU-funded national industrial projects. His research includes construction and control of highly dynamic robots and versatile leg robots for real-world field applications. So with this, help me welcome Claudio, and please, Claudio, take it away. It's all yours.
Thanks, Joao. Can you hear me well on screen?
Yes.
Okay, great. So thanks again, Joao, for the introduction. Sorry that my bio is quite long. My name is Claudio Semini, and it's a pleasure that I'm the first speaker in the second session. So I hope everyone has had a good time having a breakfast, lunch, or dinner. Today I'm going to talk about the IIT ENILE Teleoperation project, quadrupedal telemanipulation in hazardous environments. And for those that don't know me well, I've been working at IIT for over 14 years now, first with my PhD developing several versions of this hydraulically powered quadruped robot. In the meantime, throughout the years, we're doing actually mainly research in control, algorithms, planning to make these quadruped robots walk over rough terrain. So today in the talk, we will mainly hear about HiQ Real and a little bit about the HiQ robot. But this talk is more about the teleoperation, of course. So I'm here representing the Robot Teleoperativo project. This is a project between IIT and ENILE. It's a collaboration that involves several teams inside IIT, the Advanced Robotics research line led by Darwin Caldwell, then Humanoids and Human-Centered Mechatronics led by Nikos Tsagarakis, and my own Dynamic Legged Systems Lab. The project manager is Nikhil Deshpande, and the project has started in September 2017, so it had just finished its first phase in the end of last year, and we're now in phase 2 for the next 3 years. So on the ENILE side, there's Carlo De Petris and Sara Anastasi that are following and collaborating with us. So the motivation here is, and maybe I need to explain what is ENILE. ENILE is the National Insurance for Against Accidents at Work. And of course, ENILE is interested to protect the workers in daily tasks, both in hazardous and non-hazardous environments. But here, especially in hazardous environments, we have elevated risk for the human operator. So not even not just in emergency cases, but also in routine tasks, these workers get exposed to higher risk. So one of the applications that you saw was disaster response. So we went to the Italian firefighters, the Vigili del Fuoco, and had several meetings with them. They're now our partners in this project. And we defined what the collaborative robotic teleoperation system should be able to do. And basically, we want to separate the human worker from the hazardous environment. We want to bring that operator into the teleoperator seat away from danger and project as much as possible the capabilities of the humans into the robot avatar that goes out there and does the work for him. But important is also that that particular person that would have done the work in the hazardous environment actually gets to do the work as a teleoperator. So the whole skills, the situational awareness and experience of that person goes in there to operate the robot avatar. That's an early concept, and After the 3 years, we've come up with these two systems. On one hand, on the left is the field robot. This is the hydraulic quadruped that I showed before with a novel lightweight electric arm. Then on the right side, you see the pilot station. Here there's an operator that has a hand exoskeleton and arm put on his right hand, and he's wearing a visor for the virtual reality and augmented reality interface. And today in the talk, I will go through these 4 subsystems and explain you a little bit what we've done in the last 3 years. So I mentioned these 4 teams inside IIT. Everyone was in charge of one particular aspect of the system, and then with several integration sessions, we're putting everything together, and you will see this complete system towards the end of my talk. So let's have a look first at the navigation platform that my team is providing. A little bit of background here. We've been working on these quadruped robots here to work on rough terrain for several years now. You see in the bottom random obstacles on a treadmill. You see in the bottom right some objects outside, loose rocks that are quite challenging to keep the balance, especially here the robot is completely blind and it's just feeling through the torque controlled legs. On the top left you see how the hydraulics with these servo valves can do very high performance torque control that can then be used for impedance control and so on. Other examples are these reflexes there on the top left, but then also overcoming different obstacles with a crawl gate. And here before we saw a lot of trotting gates. This is a crawl gate. Depending on the situation and then on the difficulty of the terrain, the robot can change the gate into the more suitable gate. And maybe later we have a little bit of time to discuss this, but here we see the mixed autonomy. So the operator of the quadruped robot should only tell the robot what is the speed, the heading and the direction, and should not worry about where is the robot's foot going to go next. So this is really something that should be autonomously done by the robot. And all these different efforts here that you see in the videos, in these slides, are creating this complicated software framework that brings high robustness and stability in different kinds of terrains. So one particular example I wanted to highlight, this is how we use convolutional neural network to actually look ahead, just right in front of the foot. When the foot swings to go to the next footstep, it is normally touching down there in the red spot. But in this case here, because there's a gap, the neural network can very quickly evaluate a better foothold and then spit out the solution and say, it's much better if you put the foot here on the green one. And in simulation, you can see this works very well. You see the foot sometimes steps over two gaps and then steps twice on the same point again, just to avoid stepping into these gaps. In experiment, this works as well. Of course, here 0.5 meter per second trot. It's a quite fast gait, and the robot can nicely overcome these gaps. And also here, when Victor is trying to pull the robot to the gaps, it is smart enough to avoid the gaps and make these very fast corrections in the last 100 milliseconds during the swing phase, basically. So coming back to the hardware, around 2019, we've presented for the first time the Ryo robot. This is a strong, heavy robot, 140 kilos. It contains everything on board. There's 2 hydraulic pump units, there's batteries, navigation, sensing, everything. And we're using this platform to then carry the arm and the other sensors for this particular for this Teleoperativo project. Here in the video you see one of the first experiments that we did with the new machine. It doesn't have all the nice covers on yet, and it's getting the hydraulic power externally, but you see the same software modules work very nicely here as well on this particular robot. And shortly after, we tried to train the robot in pulling heavy loads. So you can see here in the lab, the feet are actually slipping a little bit on this plastic floor, but we're measuring with a dynamometer what is the maximum force here. Here you see in the back of the building how we attach the robot to a car. We have to pull the handbrake with several clicks so that we can create enough traction force here. This goes up to 500 Newton of pulling force. And all this was a preparation to bring the robot to to the airport of Genoa 2 years ago, where we then successfully managed to pull this 3.3-ton airplane for 10 meters. Maybe some of you have already seen these videos, so I'm moving forward. But the robot obviously doesn't need to pull airplanes. This was just a demonstration of strength of the power. The robot is made for rough terrain, like we're demonstrating here with the stairs, the rubble going under some narrow passages or climbing up a ramp. Then in October 2019, we brought the robot together with the other subsystem to the Makers Fair in Rome, and we had a lot of audience coming for 3 days, including dogs that got really excited to see the quadruped, the metal quadruped friend. So we then integrated the arm onto the system. The arm is located here in the front. The front location provides a maximum workspace in the front. We will see this a little bit later. But to do locomotion experiments, we stow the arm to the back of the robot. So you can see that the arm is nicely fit here. This is a stair climbing with rubble. The robot is sometimes slipping here. This is the robot is capable in coping with these slippages. Here the robot is stepping backwards, and you can see sometimes it's slipping on a loose wood, but it's basically always keeping the balance. And on the right side, you can see the robot with a slower crawl gait going here through these rubbles in the back of the building again. So if you're interested in quadruped robots, then we also have a talk of my former PhD student, Romeo Orsolino. He's going to talk about the feasible region, which is a new concept that we've introduced last year. And then on Friday, I'm going to have a talk in the workshop on legged robotics, if you're interested. Also, I'm a guest editor in a special issue for state estimation for mobile robotics. If you're interested, then visit the website or send me an email, please. Okay, let's move on to the manipulation part. That is work by the team of Nikos Tsagarakis. Here the arm was custom designed for the application. It needs to be lightweight, and needs to have optimized robotic arm modules and a very robust and dexterous hand end effector, and of course the whole software that makes this arm operate properly. And we're going to have a look now at the features. So the 5 degrees of freedom arm, it has 8 kilo of weight and then a payload of 5 kilos. This excludes the hand. The hand alone is 2 kilos. So then that leaves with the hand 3 kilos of payload. The arm workspace was optimized in the sense that we can mount it in the front of the robot and it can reach down and pick up objects from the ground, but at the same time also operate mainly in the workspace in front of the robot to open doors and close valves and do other operations, and then also stow it back on the trunk as we saw before. This is the hand, the hairy hand. I think it's hairy hand 2. And this 4-fingered anthropomorphic hand is very robust and powerful. It has one active degree of freedom, 1 motor per finger, and can nicely close around with these tendon systems. It has integrated pressure sensing. So this is about the software. Here Arturo, Enrico, and their team member are using Cartesio and OpenSOT that they have developed to make the arm here move in Cartesian control. And on the right side, you see that the guys are playing around with the stack of tasks. Here, the end effector needs to keep its orientation and position in space, and they're adding external loads to disturb the robot, and you can see that the arm stays there with the highest priority. Here we see 2 videos. On the left, it's nicely active impedance controlled as well. The arm, it is fully torque controlled. This one has electric actuation, if I haven't mentioned it yet. And on the right side, we can see here already a glimpse into the pilot station that then operates the arm here to do some fine manipulation tasks with these objects that are lying on the ground here. And on the left side, you will see how Nikos and Enrico put the arm into zero gravity mode, and you can see how they can nicely play around with this arm in this video. Okay, let's move on to the haptic interface. This is the team of Yannis Sarakoglu. He's a member, he's leading a team inside Nikos Tsagarakis, a bigger group. And we're going to have a look now at the remote arm device and the HexoTrack Plus hand exoskeleton in a bit more detail. The HexoTrack hand exoskeleton has underactuated kinematics with 6 degrees of freedom per digit. They are fully sensorized, so there's 6 encoders, as we will see later. It has 1 active degree of freedom per finger, 5 passive ones. It fits to almost all the hands with this nice finger. How can I say, the fingertips are going into those caps, and then it can apply forces to the finger, both in flexion and extension. And it has these integrated 6 degree of freedom tracking of the fingers with position and orientation. Is suitable for rehabilitation, haptics, and teleoperation, as we will soon see. Here about the workspace, it has a very large workspace. So if you compare the human hand workspace here and the Hexatrack workspace, we can see that we can do all the motions freely with the fingers. And we can see here how it measures the 6 DOF position of all the fingers. Here in a teleoperation application on the left, Anna is very intuitively using this hand exoskeleton to operate here a KUKA arm attached to a PISA IIT soft hand, and you can see how she very intuitively picks up stuff and puts them there. Of course, here there's a clear line of sight, but this was a proof of a concept how this hand exoskeleton teleoperation is working very nicely. On the right side, you see virtual reality. You can mimic the forces. You can give force feedback, the haptic feedback, and I've played with this. It's really nice how you can interact with the virtual world there. So then Hexatrack Plus is the evolution. It has 10 Newton per finger that can be displayed and was developed here as part of the SoftPro EU project. And we can see in the bottom how the exoskeleton is used for rehabilitation purposes. Now the remote arm device is actually a device that attaches the Hexatrack hand exoskeleton, and this device has 6 degrees of freedom to measure the position orientation of the operator's hand, and then also to give up to 20 Newton force feedback in XYZ for the device itself. So this is the master, the pilot station here, and we can see how the guys during the Makers Fair are playing around here. On the left, you see Yanis is trying to get that tennis ball into the cup, plastic cup, and on the right side, you see how the guys are playing around and throwing the ball. And out of these 3 trials in the video, 2 of them were successful to actually catch the ball that is thrown into the cup. Good. Let's go to the last subsystem. This is the Vicario group from Nikhil Deshpande as part of the Advanced Robotics research line in IIT, and this is about the user interface. This is the pilot station that has a VR-based 3D immersive user interface. Basically, the main 3 pillars here are remote sensing and computing framework, low latency communication architecture, and immersive visualization using mixed reality, virtual and augmented reality, as we will see very soon. So on the robot, there's in terms of remote sensing and computation, on the robot, on the remote environment, there's a Jetson Xavier located here in the front of the HALODI robot. There's LiDAR sensor, RGBD sensors, and there's several software modules that make this communication between the operator and the remote station work. In terms of low latency communication, we need to stream audio-visual feedback. We want to do this in a very compressed way, so we do some filtering first, remove outliers, and then have a good compression to then broadcast this over the network, stream it over the network. And here, the remote teleoperation using virtual reality, we can see in the bottom left how virtual reality teleporting, we can go to a different location, and then with the motion controller there, the person can, Jalil is very nicely controlling this hand attached to a UR arm, and when he changes the point of view, also automatically gets mapped to the new point of view of the operator. And on the right, we can see how this a ball is being grabbed by using just this interface with the VR interface and the motion controller. Okay, I will go faster. This is a video where we show augmented reality. So this is the interface that the operator can can have different camera views. We will see that a little bit more soon. This is how to see when picking up objects from the base of the arm, and then here this is the camera of the hand itself, and this is the point cloud that displays in 3D the interesting region. So the overall specs of the system are displayed here very quickly. I would like to use the last minute to show you a video of how everything works together here with the teleoperator in the back. This is a plastic for a hose, a fire hose, and here the plastic has to be first broken in, and then they extract the, take away the plastic glass to extract then with fine manipulation this hose in here. You see on the right, this is the camera view from the hand. And the next motion is to grab the nozzle and start using the tool. This is a task where the door gets opened in teleoperation mode. You see the different camera angles. The bottom left is actually the camera of the robot that is normally used for locomotion to see the obstacles and 3D terrain. And this last scene here is how we're retrieving objects. And this could be a task for the firemen that go into earthquake-struck buildings, houses where people can't get back in to get their valuables out. And that could be one of these dangerous tasks that the Vigili needs to do. So at this point, a credit slide. Many people are involved here. And if we have time, then I take a few questions.
Thank you so much for the talk, Claudio. Very, very interesting work that you're doing. We'll save some questions for the discussion session later on, but I do have one thing that I would like you to give a comment if you can. So can you comment briefly on maybe some of the challenges of what make it especially challenging to teleoperating a light robot? So maybe having to deal with stability, or maybe having to deal with the fact that the human is not actually a quadruped robot. So what are some of the changes of mapping that motion?
So the base is treated like an omnidirectional platform, so the operator can actually operate that like an omnidirectional wheeled platform and bring the robot into the correct position. So one of the nice things of the legged robots is, of course, that we can actually move the base to extend the workspace of the arm. So you can imagine the base can be moved in 6 degrees of freedom. So that is certainly a nice advantage.
Yeah, I agree. So I think being able to move around is also a benefit and also an advantage, because now if you want to apply a lot of force, you also got to deal with the fact that you got to balance yourself when you do that. All right. Thank you so much, Claudio. I hope you stick around for the panel discussion later on.
Okay, it was a pleasure.
Great to have you. All right. So, and thanks for keeping track of time. Really appreciate that. All right. So our second speaker today is my good friend Avik Day. So thank you, Avik, for being here and accepting the invitation. It's always a great pleasure to see your stuff. So Avik will talk to us about his work at his company. So Avik is a co-founder and CTO of Ghost Robotics, which is a startup company commercializing legged robots for industry and research from Philadelphia. Previously, he completed a postdoc in Harvard with Professor Rob Wood, and he studied the design of micro-scale flapping robots. He got a PhD in 2017 from the Grass Lab from UPenn with Professor Dan Kodicek. And I think that the main thread that unifies all his work is a bio-inspired design and control that is strongly anchored from empirical robotics. So his research has focused on modular and hierarchical control strategies, as well as demonstrating efficient and effective control of dynamic leg robots that generalizes across platforms and behaviors. All right, thank you so much, Avik, again for being here, and please take it away.
Thank you, Joao. Can you hear me and see the slides?
Yes, sir.
Okay, excellent. So thank you again for inviting me. So this, I will say we're very much beginners in the area of kind of the science of teleoperation. But I wanted to kind of give my perspective on, what we're learning about how users want to use our robots and, how to help them use our robots. So I'll just give some beginning perspectives on that. So yeah, just a little bit of background on myself. I've worked on many different kinds of robots, a lot of them in graduate school, including at Penn. I worked on this tailed bipedal hopping robot, this a kind of sagittal plane quadrupedal robot called Minotaur, which is really what led to the start of Ghost Robotics. I also worked on very small flapping robots, which was quite a different experience from the rest of my work, but it was similar in a lot of ways in terms of bio-inspired control and kind of embracing the challenges that comes with as compared to using wheels or propellers, as the case may be. Yeah, so most of my talk will be about what we've learned from the company Ghost Robotics, which I started while in graduate school. The company has kind of two products, one kind of meant for kind of commercial deployments, a larger robot called Vision, and a smaller robot called Spirit, more for research and development. And I'll talk a little bit more about that now. So the company has about 20 people based in Philadelphia. Here you can see our offices are actually right next to Penn. So this is the Pennovation campus, where we find lots of nice space to develop our robots, as also have a good source of employees as they graduate from Penn. So the robot that you're looking at now is the Vision 60 robot, which was kind of sized approximately to be able to comfortably go up and down stairs. In terms of how we design these robots, our priorities are usually to have common components. So they're very kind of standard drivetrain components, standard motors, so that the cost can be reduced by not having kind of exotic components that can't be really driven down in cost. We also try to make our robots, at least the Vision, be weatherproof so that it can be used in kind of rain and swamps, and actually trying for an IP67 rating. And the other thing that we focus on is really efficiency for the design, both mechanical and computational. The limitations of the design are, of course, that it's not got a huge amount of payload. We advertise about 20 pounds. So the applications that the robot's being kind of used for today are mostly, I would say, in the category of mobile sensing. So one of the applications that we're actually working on right now is kind of doing security in a large area, like an Air Force base. So the robot kind of just goes around the Air Force base, kind of taking pictures and videos just for doing security. So we think this will be a kind of a common type of theme for mobile sensing application, where the robot's mostly just carrying around sensors in environments where it would be kind of difficult to put static sensors because the area is very large, and also difficult to use wheeled robots because the terrain is unstructured. Another area is kind of construction and mapping. So basically using, again, kind of just sensors to go around and take more detailed information and constructing maps. And similarly also in the industry of mining. And for applications tomorrow, we really see that we can do some mobile manipulation, and we're really not making too much. We're not investing too much time into this yet, but we can see that it will be an interesting area to focus on in the future, and I'll give a little bit of perspective on this as well as it relates to teleoperation. And we're also looking forward to kind of having much more autonomy on the robot, and I'll talk a little bit about the kind we have at the moment. And of course, our dreams are that the robot will be able to be in consumer applications, used in consumer applications. But we definitely understand that will take a long time for now. So we're really focusing on applications where the robot's in kind of not close to people, just kind of in an industrial or outdoor settings. So here's kind of the main way that that people interact with our robots. It's this kind of operated control unit, which is composed of kind of off-the-shelf tablet controller and a custom enclosure with kind of buttons and joysticks and stuff. So we're actively developing this, and obviously since it's mostly custom, we can easily change the layout and add different kind of interface features for things like remote e-stops or whatever might be needed by a specific application. So that's kind of an advantage. So I'll point to one thing. So there's a contextual kind of menu at the bottom where kind of the different types of things that the robot can do can come up. And we're really kind of actively working on figuring out how to present all the different things that a legged robot can do to the user. So this is, as you can see, it can get quite dense and, bordering on really information overload for the user. But you can imagine, like, compared to piloting a wheeled robot or a drone, legged robot has a lot of options, as in, different gates and different operation modes, much more so than other kinds of traditional robots that people are used to kind of driving around with the remote control. So we're, kind of trying to figure out how to present all this information to the user. And the other thing that they have access to is kind of different ways of getting information back, whether it be kind of just visualizing what the joints are doing, different camera views, and maybe a high-level mission screen where they can see kind of like Google Maps, they can kind of see where the robot's going in a kind of a larger deployment. So the kind of information flow for this teleoperation is that obviously there's the robot on the right, and on the one hand, it's accepting commands from the user. And as I mentioned, we really need to work on kind of simplifying this. And the way we really think about this is that as the robot gets more autonomy, as we get more adept at the robot, writing robot control strategies and autonomy strategies such that it can kind of automatically understand its environment and select appropriate locomotion modes, that will automatically kind of simplify this for the user. But as we're developing it, it definitely just presents the user with a lot of options at the moment. And on the other direction, kind of information back to the user, that's also something that we're really trying to actively figure out. So, for instance, there are a bunch of ways that in which this kind of information interface can present information to the user. So there's audio information, including kind of basic things like, battery low for the robot or for the tablet, and when you've connected or disconnected, kind of basic things as you can imagine. Slightly more advanced is that we, for now present a bunch of warning text for when we detect a sensor issue or an actuator issue or a software issue of some kind. For example, maybe the GPS isn't working well, or one of the joints seems to be misbehaving. We, add in some diagnostic software and present that information to the user. Kind of even less, kind of more abstract, I guess, is trying to provide guidance to the user. So, for instance, if there's some way in which we can help the user understand which way to kind of navigate the robot, which way to use the robot, we try to provide some visual cues, and this is really under active development. And the other thing we can do is, again, to kind of guide the user in using the robot, is to provide them some haptic information about, ways that the robot is comfortable and it's not comfortable. So I'll talk a little bit about these, but these are all, again, really kind of beginning steps for us. So this is kind of what semi-autonomous operation looks like. People get kind of a Google Maps-like view and are able to drop a bunch of waypoints and then, send the robot off, and the robot kind of goes around these waypoints. So they get kind of warnings if the GPS is losing its position when the covariance gets too large. It kind of aborts the mission and stops if the GPS malfunctions based on that information. But if the tablet disconnects, if the operator control unit disconnects, but the robot's okay to keep going on its mission, obviously it keeps going, which is part of autonomous operation. Another kind of interesting area is that when you get to really challenging terrain, so this is in kind of desert land in Arizona, where one of our employees lives. He was testing the robot, so there's a specific hill mode we've made, which has a lot of interesting features, like trying to keep traction by re-swinging the legs, kind of breaking the specific gait pattern that it's been initialized with. In this kind of a very challenging terrain where it's really hard to get traction, we really kind of see the need to try to provide the user with some more guidance. So one thing that actually one of our customers has suggested is that let's say the robot's kind of having a tough time, it would kind of really be useful to give the operator who isn't familiar with these robots some idea of kind of a red, green, yellow of which directions, based on the robot's visual sensing of the environment, which directions it's kind of more promising for the robot to be driven in if it's being teleoperated. So we're thinking about this. We don't quite know how to do this yet, but perhaps some kind of machine learning of environments that the robot's being successfully driven on could be able to present this kind of information to the user. So this was kind of helpful feedback we got, and we're kind of thinking about trying to incorporate into a teleoperation interface. Obviously, another kind of area of like challenging challenging locomotion events for the robot are, unsuspected contact. So, we obviously try to work on these recovery behaviors to make sure the robot stays upright. But, the kicking here is just kind of symbolic of, all sorts of perturbations the robot's going to be subjected to just kind of naturally based on being, driven in tough environments. So one thing that we are thinking about doing in these kinds of things is that, let's say the robot is really kind of slipping or things like that, or it's, hit a tree or something like that in autonomous or in semi-autonomous operation, to give kind of haptic feedback to the user to kind of as a symbolic representation of, unexpected forces that are acting on the robot, and also when the robot's toes are slipping. So that's kind of another area we're thinking about presenting information to the user. Just as if similarly, the robot has all sorts of kind of sensing and recovery behaviors for losing contact as well as kind of unexpected contact. So this is the robot's recovery behavior when it's kind of picked up instead of flailing its legs. And similarly, when legs kind of slip around line long time ago. So understand how to time to the user we're interface. The last kind of thing that I'll show you is, this is again a kind of really beginning area for us. We, are just kind of looking at third-party arm integrations, not kind of a final sort of manipulation interface. But so the interesting challenge that this poses to us actually, Joao kind of alluded to this in his question to Claudio just a little bit ago. So when this kind of really non-back drivable arm is kind of paired with our robot, which has pretty low impedance characteristics, it can really exert kind of unbounded forces on the robot body, and you can see kind of at the end of this video when the cone is touching the ground, it's really kind of just lifting the robot up because of how much force it's exerting. And while we have these kind of third-party arms, what we're doing right now actually is, again, kind of using this haptic interface to kind of try and understand when the forces are very large and, give some warning to the user to back off. And also we're, at the same time working on, our own arms and things like that. But this is another way we're thinking about just communicating to the user when the robot's getting a lot of unexpected forces. So I'll, kind of at the end here, so I'll summarize. So the main challenge I think that we're, learning is that, we don't have experience. We've driven, various members of the team have flown pod rotors, driven remote controlled cars, but there are just so many more options with a legged robot that we're, not quite sure of good user interface paradigms to communicate both the abilities of the robot as well as the challenges that it might have. As I kind of indicated by, all of the abilities obviously have to be simplified, and coming up with ways to communicate the kind of unique challenges that a legged robot might face in the environments that it's being used in. So this is actually one area where I think we see a lot of opportunities for machine learning, both for sort of simplifying the abilities, like I mentioned before, with more autonomy, and also for sort of recognizing different types of environments automatically and communicating which parts might be challenging to the user. So again, this is definitely a beginning area for us, and definitely welcome any feedback if any of you have any, and thank you for listening to my talk.
All right, thank you, Avik. It's always good to have like a nice perspective from someone who likes locomotion, trying to do that for industry. So one thing that I was curious is, so what do you think are challenges that you didn't foresee that you think are, this would be definitely nice to have from an industry perspective. This would be very nice to have like a human controlling the robot, and this other application would be very nice to have the robot being autonomous. So what do you think are the use cases of each one?
Yeah, I mean, so I think for really making a good business case for the robot, it's really useful to have autonomy, because the more what we're trying to do is not have humans tied up in kind of tasks like security patrols, like I mentioned. So if a human has to teleoperate it, obviously we don't get that benefit. So we really need the robot to be autonomous, and that brings up all sorts of things that I never worried about when I was in graduate school, like state estimation and things like that. That are quite important for the robot to be autonomous and self-sufficient. And in terms of situations in which teleoperation is useful, so we've actually found that in industries like EOD, like bomb disposal, users are actually very, very reluctant to have any kind of autonomy. They don't even like having the end effector be controlled directly. They'd rather control an arm with joint by joint position control, because that's what they're used to, and that's what they really trust. So that's been kind of interesting to learn about the preferences of experts in different industries.
Yeah, it's always funny, like when we're in academia, we're always thinking about these challenges, but we don't foresee the simple things like what you just said about they prefer to do joint level control than task-based control. All right, thank you so much, Avik. I hope you stay around for our discussion later on.
Thank you.
Always great to have you. All right, so our third speaker, is Ludovic here yet? Oh, yes, there you go. Hey, Ludovic, how are you doing? Thanks for joining us.
Thank you for having me. Let me try to share my screen.
Yeah, if you want to share your screen, I'll introduce you.
Yeah.
Nope. I think he clicked the leave button. All right, let's give him a sec.
Hey, sorry,
don't leave yet.
My computer crashed. My Microsoft Team just crashed. Okay, let's give it a try again.
All right.
Okay, do you see my screen?
I see your screen. All right, let me.
All right, and you can see me and my screen. Everything is fine, and you can hear me.
That's right.
All right, great. Thank you so much.
All right, so it's my great pleasure to welcome Ludovic Righetti. He's an associate professor in the electrical and computer engineering department and the mechanical and aerospace engineering department at the NIU, and a senior researcher at the Max Planck Institute for Intelligent Systems in Germany. He holds an engineering diploma for computer science and a doctorate in science from PFL. So prior to joining NYU, he was a postdoctoral fellow at the University of Southern California and a research group leader at the Max Planck Institute. His research focuses on planning, learning, and control of movements for autonomous robots, with a special emphasis in leg locomotion and manipulation. Thank you, Ludovic, for being here. It's a great pleasure. Please take it away.
Hi, yeah, thank you so much for having me today, and thanks for the nice introduction. So today I'd like to talk to you a little bit about the work we've been doing over the past 1.5 to 2 years about how we can use wireless So can you hear me?
Yes. Okay, you're back.
Sorry, I seem to have a wireless issue. Okay. I think I'm going to collect all the problems that you can have in a talk today.
It's ironic that you have a wireless issue.
So, a terrible wireless for a wireless talk. It's great. All right. So why do we need 5G? I wanted to make my case because the Wi-Fi doesn't work. Okay. So we'll look into that because so one happens that I have a lot of colleagues at NYU actually who are specialists in 5G, and they told me all about this. And we started to look into if you want to add increased autonomy in your robot, basically, we have two limiting factors, right? Which is the weight and the size of the robot and the amount of energy that we can actually carry on a mobile platform. And at the same time, the more we want robot to be more autonomous and capable, the more computation we need. And what do I mean by that? That if you take, for example, a whole body controller, so this is an example of a whole body controller. So it's a hierarchical inverse dynamics controller that we did many years ago. And it's great. You can close a 1 kilohertz control loop with feedback on this, and it does a lot of very cool things. The problem when you start doing that is that you quickly use an entire core of an i7. So basically 100% of the core is dedicated to actually solving basically a series of quadratic programs to close the kilohertz control loop. So with more capabilities, basically comes more need for computation. This has not changed, right? So this is a work we're going to present this week at ICRA. This is a full model predictive control and the full body dynamics of this manipulator. So we do differential dynamic programming, which is great because now you can have robots that are very reactive. They can adapt their behavior on the fly. They're very compliant. So you can do a lot of very cool things with that. This also comes at a cost, right? Is that basically you burn your entire CPU when you start doing that, because everything is extremely computationally intense. No matter how fancy your algorithm is, you still have a lot of computation to do, right? So with more flexibility and autonomy, basically we have this issue is that we need more computation. So now if you look quickly at how much computation costs, right? If you look at an NVIDIA Titan X, you basically burn 250 watts of power. With an i7, you burn between 70 and 120 watts of power. It depends how much load you put on the CPU. Now, if you look at, so I took data from a paper, and I don't know if Marco is here, but you can correct me if I'm wrong, but the animal robot, at least the 2016 version that I was describing in the paper, carries roughly 650 watt-hour of energy, which gives at the time, give them roughly 2 hours of operation, right? The Tiago robot from Pratt Robotics carries 720 watt-hour of energy. So basically what you see is that if you use a high-end GPU, if you use an i7, you're going to eat a significant part of the battery life. So one question that comes in is, can we actually move all the computation and everything that costs us offline? Can we move, not offline, but can we move it basically in the cloud? So people have been looking into cloud robotics for a lot of time, right? There's nothing new here. The problem is that up to now, it was not really possible to do anything real time, right? Most of the things that you could do, if you had time critical computations you want to do, you cannot do it offline really in the cloud. So the question is that can we offload real-time computation, and can we, and when I mean real-time, it means that I want to be able to close loops that have between 1 and 5 milliseconds of delay most of the time, and I want to do multimodal sensing that can transmit a lot of data to the network edge. And up to today, it was not really possible. But if you look at new wireless technology that our colleagues in other fields are actually developing, it's quite exciting because, so for example, the 5th generation of wireless actually allows to hit the kind of latencies and that I was talking about, a few milliseconds, in order to close force control loops. And you can actually have the data rates that you need to start transmitting video in real time, right? So this becomes potentially possible. And maybe before I go into how we can use that to do whole body control, I just want to give you a little bit of an overview of what basically the 5G technology is and what it can do. And since I'm not a specialist, I'm going to keep it very high level. But basically, there's two core technologies, right? One is the physical layer, so how they transmit information. And they use a much higher frequency spectrum, which is called millimeter wave. By doing that, what is great is that you can increase the data rates that you have, like massively compared to what you would have with other wireless. The other thing is that you can decrease the latency of the Airlink down to 1 to 2 milliseconds. So that becomes very close to the kind of specs that we like when we do feedback control. The other thing is the completely redesign of the network architecture. And basically, in order to basically really bring computing close to the edge, and then you start to have edge computing with latencies of the order of also 1 to 2 milliseconds, which was not really possible before. So that's quite exciting, because now we start to see specs that actually talk to me as a roboticist. I care about a few milliseconds. If it's much more than that, then I know I cannot close the loop. So low latency, high bandwidth, and basically gives a hope that maybe we can do a lot of operations that are not tethered. The problem is that when you use millimeter wave transmission, the transmission is directional. So basically, you will have a transmission that it sends a beam, and it's not basically sent all around the place. So you really need to track the users and know where they are and send the data directly to them. So that causes a lot of challenges. And the other thing is that the signal dissipates very quickly when it enters obstacles. So it can be blocked by a lot of material, including people walking. So you can have a lot of blockage happening intermittently. So what you have is that a very low latency, and suddenly you have a spike because you're losing communication. You have to fall back to another network, and then you go back to the very low latency. So you need to be able to predict that and deal with it when it happens. So if you just basically remove everything, the whole force control on the network edge, and then you just do control your robot this way, this is not going to work really well, right? So we quickly verified that, right? So if you do a force control task, you apply a force, and you have a 1 millisecond delay. So this works well if everything is perfect, right? 1-2 millisecond delay, it's going to be fine. Now, if you start to have delays that are more realistic because you have blockage and things like that, everything goes unstable and nothing goes, right? So we cannot just move our controllers on the edge, but we actually need to do something else. So what we started to look into, and this is preliminary work, so there's a lot more to say still, but the idea is that can we mitigate any delay or kind of realistic blockage we can have with local control. So we studied the problem with a whole body controller. So it could be any type of whole body controller, but basically most whole body controllers that you see today in leg robots, at the end of the day, what they do is that they solve one or several quality programs at each control cycle. So the question is, can we look at the structure of the quality program and do something about it such that I can use a previous solution of the QP locally on my robot to do something if I'm not receiving new solutions from the remote server. So if you look at the structure of a QP solution, so you have a quality cost, you have a linear constraints. It could be equality or inequality constraints. And when you solve basically this generic QP, so it could be a force control, it could be acceleration based, it could be whatever you like, right? At the end, when you find the optimum, what you see is that you have two sets of constraints. You have the constraints that are active. It means the constraints where the solution is on the constraint set, right? And then you have equalities that you need to solve, and you have inactive constraints, which means the inequalities that we are not touching at the solution, and these ones you can ignore. And what it tells you is that once you found the active set, that's actually the complicated part of resolving a QP, right? The only thing that you need to know to do is to solve this KKT system. So basically, you need to invert a matrix, and what you find is you can find Y star, which is going to be the control that you want to apply, and lambda star is going to be the Lagrange multipliers. So what does it mean concretely when you do that? So H typically is going to be composed of the Jacobians of your task space problem. So that's the Jacobian of your problem. And this is not going to change very quickly, right? So most of the time, this is not actually going to change. The active set, which is defined by A bar, is not going to change very often. So basically, the big matrix that you have is pretty much constant or close to constant at a very close control cycle. On the other hand, the minus G basically is going to be the sensory feedback. That's where you close the loop. That's where you basically say, this is what I want the robot to do, and this is how it should close the loop with the sensory information that I have. So this is going to change much faster, and that's what we care about. So the idea here was going to say, let's basically try to approximate this KKT matrix, so the inverse of it, right? And basically just keep this constant. Just assume it's a linear operator. That's a gain, basically. So you can assume this is a gain. And then the only thing that we want to update locally if we are not receiving data is to update this G that basically is the feedback control. And G is very cheap to compute because it's just forward kinematics pretty much. So it's a simple matrix vector multiplications when you compute G. And then you can do local control at a very, very low cost, right? N square matrix vector multiplication. And it will approximately enforce all constraints. So this is what we do, right? We solve the QP on the remote controller. We send a solution to the robot that is both the solution to the torque or the whatever command that the robot needs to apply, and at the same time we give it the actual KDD system that we computed, so such that it knows the gain that it needs to apply if suddenly it loses communication with the remote. And locally, what we do is that we either apply what the remote has sent, or if we do not receive data, we basically multiply k by the state of by this matrix G that I talked about before, that basically does the feedback control. So this is locally approximately optimal, right? So then we did a simulation in a realistic environment with a full model that includes basically wave propagation for the millimeter wave. So this was done by my colleagues at NYU. So the whole 5G level. And when you do that, right, basically, if you just do the remote control naively and you don't know what's going on, and you don't care about the delays and about the blockage, basically your robot is going to fall. Now, if you have as a backup this local control scheme that I described that is kind of very simple, you're able to deal with any type of blockage that you can find in a realistic environment. So here we simulated different types of environment, basically the kind of blockage that you have in the realistic scenarios. And what you can see, they can drastically reduce the center of mass tracking in this case. So on the PR means the purely remote, and LR is basically our local control law that we propose. And you can reduce the amount of constraint violations quite a lot. So at the end of the day, you can basically walk. More metrics, basically what you see is that for different tasks, you can actually make the system robust to actually to realistic blockages and to realistic transmission signals, such that the robot is able to work, and you can do the whole body control completely offline. And at the same time, you can reduce a lot the actual computation burden that you have on the local controller, because most of the computation is done remotely. So the last thing, just to quickly conclude, so that's one step. So obviously that's not enough. The other thing that we would like to do is to anticipate when are we going to lose connectivity. So if we have a model of transmission of the signal, we can do model predictive control and basically anticipate when we're going to lose signal, and we can maybe replan to make sure that we do not lose signal. So for example, if someone is going to cross the path where we have basically direct communication with the transmitter, we can try to go around and mitigate that. So in order to do that, we need models. So that and we need basically ways to do filtering with those models. And the other thing we're starting to look at quickly is that can we basically find the transmitter from where we're getting information from sensing? Because what is interesting, since if we have a directional connection, basically we get a sensor from the 5G network that tells us what is the direction from which we receive the signal, and we can use that to do filtering. So I won't go too much into the details, but what we're doing now is that with my colleagues at NYU Wireless, they basically are building models of propagation of the signal, given realistic maps of environments, and we want to use that to start to do planning. And we're integrating that into a full system that includes vision. So here we're doing simulation in order to basically have maps to compute propagation and basically start to see where we lose signals, where we have good signals, and how we do planning with that, and what is the best way to do planning with that. One of the first thing that we've been doing is to start to see, can we basically recover where is the transmitter from the signals that we're receiving, and basically with some simple filtering, you can actually start discovering where the transmitter is by looking at the direction of the signals, and then you can start also at the same time start to plan to find where the transmitter is, and also try to make sure you don't lose connectivity while you do that. This is interesting for two reasons. You can use this to basically improve the remote control. The second thing is that if you imagine that you put a transmitter on someone, you can start to do search and rescue scenarios when you want to find someone that maybe is lost by just looking at the signal that is coming out of his backpack or something like this. So there's two types of use cases that we're interested in right now. So this is ongoing work. Obviously, we have not published yet on those things, but this is kind of the things we're excited about, is to really start to do planning by anticipating connectivity and using the 5G sensor to basically do that and merging it with vision. So yeah, so I tried to show you how we can use a new novel wireless technologies to increase mobility, to move basically computation to the network edge. I tried to show you how we could develop some simple strategies to do that for very high frequency control, and we can hopefully do that for much more things, including perception. The directionality of the 5G sensor is interesting because it gives you a new sensor that you can use to anticipate connectivity loss, but also to find an emitter and create new type of applications by using these kind of sensors. Typically, we're interested in the search and rescue scenario when we try to find someone that is emitting the signal. And the hope is that basically that we can remove the wires on our tiny robots that cannot really carry heavy computation. So we really need to do things wirelessly. And that's the thing we hope that will happen soon. A lot of the work I presented today is not done by me, it's done by my team. It's also done, all of the 5G and everything that is related to the sensing and to the modeling is done by my collaborators, Sandeep, Siddharth, and Elsa, and the students in their lab at NYU. Thank you very much for your time.
All right, thank you so much, Ludovic. Very interesting talk. I think it's very different from what everybody's been talking so far. So it's great to see like a new perspective. So something that I was curious is that, so you're talking about, removing all this computational burden from the robot to the cloud or something off board, right? So, but on the other hand, you now need to care about, not losing the signal, need to care about delays and all the stabilizations. So you gain some other computational burden on the other hand. So from what you learn, what are the trade-offs, and when should we think about actually moving this computation off board, or actually just thinking about just deal with the fact that we need a better computer in a robot?
That's an excellent question. So so there's a lot of issues, right? So what I was showing is we were mostly asking the question: could we do that? This whole body control over this 5G link is just to start looking into the problem. Probably you don't want to do, if depending on the application that you have, it's too risky to really move everything out. And so that's one thing. So probably we need smarter techniques than what I described today. Today was really like we started to look into the problem and say, what are the limits, right? What is the most extreme thing we can do? Then we can do more. There's another thing I didn't discuss, that when you start transmitting, there's a cost, right? It's actually energy. It costs energy to transmit data, right? So the question is, what is the right trade-off between what I do locally and what I do remotely? I don't know. I think it's an interesting problem. I think that it makes a lot of sense to move a lot of computation out. What is the right balance? I really don't know. I actually would be interested in thinking of that. There probably might be optimal way of partitioning the computation, right? Such that you can decide what is the amount of things you should do locally, depending on your compute budget, right? So if you start to think about the actual computation budget and the energy budget that we're given, then we can start to think about those. These are things we don't really think so much, right, in robotics these days. I think we would be interested to include those constraints in our designs, but I will not know how to do that today. I just think these are interesting questions to start looking into.
Yeah, it's pretty interesting. Maybe you got something to do with the fact that if the signal, the wireless signal is very strong, maybe you want to do everything wireless, but the moment that it gets cut off, you want to change that. So that's a very good point. I look forward for you to find out for us.
Thank you.
All right, thanks so much, Ludovic. I hope you stay for our discussion later on. All right, cool. So now we have two presentations from contributed papers for the workshop. So the first one will be from Otaran. He's a PhD student at the School of Electronic Engineering and Computer Science at Queen Mary, University of London. And he's going to talk to us about a seated foot-driven interface for teleoperation of like robots. So thank you very much, Atta, for contributing to the workshop, and please take it away.
Hello, can you see my screen and hear me?
I can hear you. Let's see about the screen. I can see your screen. Thank you.
All right, thank you very much. So I'm Atta, and I'm a PhD student at Queen Mary University of London, and I'll be presenting our seated foot-driven interface for teleoperation of legged robots. Using joysticks inputs for robot locomotion is a widely used technique. However, for telepresence systems, where you can use onboard cameras of the robots to feel like you are in the robot's environment, using body-based inputs for locomotion provides higher sense of embodiment and increases the awareness of the robot's movements for the user. And we have developed a seated interface that is driven by foot tapping movements. Our interface can capture every step of the user and create a high-level walking reference for the humanoid robots. And the interface provides a stable upper body and sets the hands free for use of manual interfaces. And our interface is a simple 1 degree of freedom actuated ankle platform that is impedance controlled around horizontal level. The foot tapping movements deflect the platform from horizontal, and the platform angle data is used to compute the reference for locomotion controller. We are also investigating changing the impedance of the platform to provide terrain-related haptic feedback. So during the foot tapping movements, we get an oscillatory platform angle signal, and our algorithm recognizes each steps and computes desired step phase parameter rather than desired forward velocity for the robot to match the user's stepping movements with the robot's stepping movements. So the step phase parameter is computed to continuously tell the robot this is where you should be in your gait cycle. The algorithm discretizes the. Can you see my? Let me use a laser pointer. So the algorithm discretizes the signal into 6 regions at every step, using the platform angular velocity and acceleration data, and every transition between regions updates the expected step phase parameter as seen in the figure P. And we first smooth the data by linearly interpolating between regions, and then further smooth it using a Kalman filter-based estimator to compute the resulting step phase. As a preliminary experiment, we asked 11 novice users to move a virtual robot avatar in VR for a certain distance for 10 trials on 3 different days. And these box plots show the speed values of their average speed values of the virtual robot avatar at each trial. The users initially struggled and then improved their performance. And at some point they stabilized, and they were able to retain their skill a week later. In another experiment, we had the task of following a leading robot with 1 to 3 meter distance. And this robot was walking at this speed profile. And we used a slider. We placed a slider in the virtual scene to indicate the user that if they are in the required range behind the robot or not. And we had 8 participants for this. And here you can see the plots of the leader and the follower, the positions and the distances between these robots. The green lines show the desired range that the follower should be behind the leader. And you can see that some of the users had a poor performance in the fast walking regions, but in general, users performed 5 to 25% error during these trials. And so we present a novel interface to control robot locomotion. The gestures are easy to learn. The device is hands-free and seated, providing a stable upper body and ability to use handheld and also desktop-based manual interfaces. It is easy to control the robot locomotion speed, and these claims are also supported by TLX and system users surveys that we also provide in the workshop paper. And we also have a humanoids conference paper that will be presented this year. Our feature works include, of course, testing the device and the algorithm with a real robot, exploring, giving haptic feedback for more information about the terrain or obstacles, and studying the cognitive load of the teleoperation task, locomotion task. Thank you very much. I'll be happy to answer your questions.
Thank you so much, Hata. Very, very interesting work. I thought it was nice that you guys, instead of making a complicated there you go.
Something is happening there.
Yeah. So instead of making a very complicated interface, you guys decided to just take the human ink flags to do the stepping and use that for teleoperation. So can you just briefly mention about the pros and cons of using a simplified interface?
The cons can be the learning time. It's not much, but it took some while for the users to understand the movement, because it's just a single platform. It's not a double platform. So the movements of the individual feet should not neglect or negate each other. That was a bit tough at first. But other than that, like for computationally, it was pretty advantageous, because we are trying to estimate a single step phase, and we only have a single variable to work with, so it was pretty straightforward. And the system is quite attainable, which is good for.
All right. Thank you so much for your contribution.
Thank you for having me. Thank you.
All right. So now we go to our next contributor paper. So is Eloise here? Oh, hello.
Hello.
All right. Let's see if you can share your screen. All right.
Can you see everything?
All right, there you go. Okay, so thank you so much, Eloise, for being here. So Eloise Dalin is a R&D engineer in INRIA in France, and she's going to tell us about some preliminary results on the whole body teleoperation of the Telos humanoid robot. Thank you, Eloise, and please take it away.
Thanks. So yes, I'm going to present to you our work on whole body teleoperation of the Telos humanoid robot, and those are preliminary results that have been tested on simulation. So we have a human performing motion. The human is wearing an Exsense motion suit, and our goal is to track the human absolute hands Cartesian position and orientation with the Telos humanoid robot. So the problem is to find the correct joint angles, despite the fact of having two different morphologies. And we are going to use whole body control for this. So whole body control is a multi-objective control formulation, and in our framework we are going to find optimal torques and acceleration that satisfies the best some tasks. In our framework, the tasks are on the same level and their priority are defined by its weights. This minimization problem is subject to some constraints, which can be, for example, joint position limit constraints. So once we have an optimal acceleration, we integrate it twice to have to control the Telos in position. So here is a list of tasks, contacts, and constraints that we use for teleoperation. And into tasks, we have tasks on the gripper of the Telos and on the head. And we are going to compute the Cartesian position and orientation of the human being at some time. And we are going to send it as a reference to tasks. And the whole body controller is going to give us the joint position to apply. So there can be some problem. For example, we are doing absolute teleoperation. So you can see in the left image that at initialization, the human being has the hands really close to Talos' body. And if we want to avoid collision, we had to implement some repulsion task in the whole body controller. So you can see in the right image here, we are defining in green some repulsion points. And our goal is to keep the grippers as far away as possible from those repulsion points. So in order to do so, we have designed an attractor function, and we are going to keep the gripper frame far from the repulsion points. And once we are outside of the repulsion zone, everything goes back to normal. So this attractor function, it's possible to use it inside the all body control task with the formulation below here. So in this video, you can see that at the beginning, the collision is avoided. And at the middle here, the human is going to cross its hands, and the same, the Talos won't follow it, and there will be no collision. So there is another problem that can occur is that if the motion is too dynamic, the robot can fall. So we have implemented 4 stabilization strategies from the paper below here. 2 strategies are center of mass, ankle, foot force difference, and ZMP distributor admittance control. And if you look at this, on the left image, there is no stabilization and the robot will fall. And with the 4 stabilization strategies, it manages to compensate, and the center of mass position will be in a more stable position. You can see this on the graph also. The blue and red curves are the stabilized position of the center of mass. So to conclude, we have implemented the whole body control teleoperation framework for Talos, and we had to implement a repulsion task and a stabilization strategies in order to make it work. Thank you for listening.
All right, thank you, Eloise. Very, very interesting work. One quick question that I have for you is, so are you guys, do you think it would be helpful at any point, maybe include some sort of feedback to the operator as well? Maybe vibration or some sort of kinesthetic feedback, would that be useful?
Yes, it will be nice especially for grasping or other applications. So for now, we are focusing on testing our work on the real robot, and we hope to test that soon. And then, yes, maybe we will add haptic feedback.
All right, looking forward to see it. All right, with that, I would like to thank all the speakers and the authors of the papers who contributed to the workshop. We'll have a quick break now until 4 p.m. European time, so about 20 minutes, and then we'll be back to with the last section of our workshop. So thank you very much, and come back soon.
All right, so welcome back to the workshop. Now our next speaker is from Avatar XPRIZE. The competition was launched in March 2018 and it seeks to incentivize teams to integrate a range of diverse cutting-edge technologies to create a physical robotic avatar system that will transport an operator's senses, actions, and presence to a remote location in real time. It is a pleasure to have with us the technical advisor of Avatar XPRIZE, Dr. Jackie Mori. Please welcome.
Good morning, everybody. I'm going to go right into sharing my presentation here. Takes a second. All righty. I think we are set. Well, good morning, and thank you very much, Kourosh and team, for inviting XPRIZE to give a little presentation during ICRA. We are really happy to be here. Certainly, this is a great dynamic group of people, and we're excited that some of our teams are actually part of this workshop. So first, a quick introduction to XPRIZE, and I won't spend too much time on this because most of you know. XPRIZE works to inspire new solutions that can address some of the world's grand challenges and positively impact our world. And we do this by organizing grand global competitions where new approaches to the world's problems can come from anyone and anywhere. The goal is to incentivize truly radical breakthroughs for the benefit of humanity. We have launched 17 prizes and awarded 11 in the last 20 years, and you can see more details about all of the many active prizes we have at the xprize.org website, including a brand new $100 million carbon removal prize sponsored by Elon Musk that was just announced a couple weeks ago. And of course, one of these prizes is the ANA Avatar XPRIZE, which was, as Luigi said, launched in 2018 at South by Southwest Festival in Austin, Texas. And this was an audacious idea proposed by the Japanese airline company All Nippon Airways, or ANA. Now, ANA was founded way back in 1952 with 2 helicopters. And it's become the largest airline in Japan, as well as one of the most significant airlines in Asia. In its essence, though, ANA was thinking about a future that would have more efficient ways to surpass the boundaries of distance, time, and even culture. It was a way to disrupt the tried and true business models of airplane travel, which in many ways was reaching the limits of its sustainability. So ANA and XPRIZE realized that our ability to physically experience another geographic location or to provide on-the-ground assistance where needed is currently limited by both distance and time. It just takes a lot of time to travel somewhere. So the question was, what technology could change the way we travel, the way we interact with each other, and enable us to share our expertise in remote and in challenging environments? What about a robotic avatar system, a robot that somebody could actually inhabit? This is a disruption that could just work to overcome the limitations of distance and time, and so the ANA Avatar XPRIZE was launched. It is a 4-year, $10 million US dollar prize that challenges teams to create a physical remotely operated robotic avatar system. This avatar system will enable a human operator to embody a robot at a distant location and feel as if they're truly present where the robot is. The operator will be able to see, hear, feel, and interact with a distant environment. And at its core, this is about transporting a human's presence and physicality to a remote location, from visiting attractions like the Eiffel Tower or the pyramids of Egypt to having a presence at a currently unreachable destination like the moon or the deep sea. Avatars will allow us to transcend our own physical limits, to explore the world in outer space and access nearly any experience imaginable. We can use such avatars to connect humans to humans at a remote location or to connect humans to a need. As I mentioned, the prize was launched 3 years ago. So where are we now on the competition timeline? We've just recently announced the semifinalist teams that have made it through the first rounds and will be going on to compete in the semifinals in September of this year. We still have 1 day for late registration. So if any of your teams have not joined us, let us know. We still have a few hours to get you in. Our teams have been working diligently to create both new technologies and to integrate many technologies that were needed to work together to make these functional robotic avatars. And we are really pleased that we have almost 40 amazing teams that are moving forward in the competition. The competition is an interesting global breakdown. So we have about 13 teams from the Americas, 13 teams from Asia, and 12 teams from Europe. And if I'm not perfect on the numbers, it's because of that late registration. We still have a few teams coming in even this week. And it should be noted that, of course, as we all know, this last year was tremendously unique and difficult for many people, not the least of which were our teams trying to put together these robotic avatars. But in spite of that, many teams were able to move ahead in the competition. They found a way to persevere and to make progress. So here's a list of the teams that we announced on April 5th, so about a little over a month ago, and we congratulate every one of them for making it to this milestone. The announcement included a little video that highlights a little bit of what the teams are doing, and I'm going to play that video next.
Human beings are social creatures. We want to explore and connect with other humans around the world. But travel is inaccessible for many. And currently we are limited to go where we want, when we want. Avatar XPRIZE is challenging teams to create robotic avatars that reimagine human connection.
Our team wants to help solve this grand challenge, to develop a great avatar system and lead to a more connected world.
Our vision is to realize the true potential of robotics.
I'm going to contribute to helping your new body.
Nice to meet you.
Thank you, Robin.
I'm happy. This is amazing.
Aiming to translate all the degrees of freedom of the human body onto our avatar body.
Anybody, any place, anytime.
So that's a little glimpse of the teams and some of the really exciting work that they are doing. So what's next for these teams? Our semifinals testing event is scheduled for September of this year, given, we hope that the COVID situation globally can allow us to all meet in person and to have these teams come together for this testing. But I'll talk a little bit about what this testing will look like. We have come up with a number of scenarios along with our esteemed judges and experts. These scenarios are designed to show connection and span a variety of domains. In these testing scenarios, one judge serves as an operator who is controlling the avatar robot in a separate location. One judge serves as a recipient who is at the remote location interacting with the avatar that the operator is inhabiting. And we have settled on 3 final scenarios for the semifinals testing. These need to be doable by most of the avatars being developed and be doable in a reasonable amount of time, given how many teams we are going to be testing. We don't want to be on the ground for 2 months to get everybody through. So we made the scenarios a short and 6 discrete tasks that we can test the avatar on. And here's a quick overview of what scenarios the teams are working towards. So a semifinal scenario is presented as a set of tasks, 6 discrete tasks that have the operator avatar. So the operator's in one room, the avatar's in another. The recipient is in the room with the avatar, and they are doing simple tasks like this cooperative interaction puzzle task where they put a puzzle together. And our judges will be speaking lines as part of these tasks. So remember, a team has to get the judge trained up so that they can actually go through these steps. Another scenario is the business interaction. And this is, again, a connection kind of test. And that's what we see these avatars as being good for. They're going to stand in for a person who cannot physically go to that other location. And this one even has a little celebration where they're closing a business deal and they do a little toast at the end. And then finally, we have a little cultural scenario where you visit a distant museum of antiquities. And this particular one has a few haptics tests in it. As well, the teams get to define a scenario for themselves. So say we're not testing some really unique capabilities of a team system. The team-defined scenario gives them a way to showcase these particular capabilities that their avatar system has. And the team will create a video, much like the scenarios that I just showed you, and that video will actually be part of their scoring. So that's about all I have to say. I wonder if there are any questions that people might have, and I'm going to stop my sharing so that I can see if there are questions, and I'll let Luigi and Serena field those.
Yeah, thank you very much for your presentation. Yeah, I think this ANA Avatar XPRIZE competition fits perfectly. The time is the perfect competition at the right time, given the travel restrictions we are facing due to the pandemic. Do you think that if the finals will show enough possible room of improvements, there's a possibility of a follow-up project, or it's too early to talk about that?
For the finals?
Yeah, if the finals show that there is a lot of room of improvement in Avatar robots, do you think there's gonna be a possible follow-up competition, or you think that's it?
No, so you're really talking about the exciting stuff. We're so excited to see what's going to happen in September, and we really need these systems in place to actually do the kind of testing that the avatar systems will enable us to have this future that we expect to be able to use them. The finals, we've been talking about when the finals are going to happen. Certainly they'll be after the semifinals, but maybe delayed a little bit to give people a little more time because of the global situation. But you've kind of tapped into what we've been excited about, which is what's the follow-on? You know, this is a beginning. So everything that teams are doing is just your pointers to where we could go to perfect this technology to make it truly useful for the world. So we hope there will be a follow-on challenge after this one is completed, because now we'll know the direction. We'll have a lot of great technology that's been developed. We'll see what kinds of solutions seem to work better. And then we'll just push that technology so that maybe in 5 years, we're all inhabiting these avatar robots.
Yeah. So far, have you seen something that surprised you positively from the video selections, or more or it's too early to talk about that?
Oh, there was so much that was just so intriguing. The multiple kinds of solutions, the real inventiveness that the teams have shown us, point to the fact that we could have different kinds of solutions for different kinds of activities. Certainly what's interesting to me is the way the teams have enabled a face so that we can have emotions, because it's really, if you're talking about that connection between people, you want to be able to kind of know what the other person is feeling or thinking, and a face is one of our biggest clues to that. So the number of different kinds of ways teams are showing emotion, showing their interaction, that's been really cool to see different solutions there.
Yeah. Oh, thank you very much. I don't have any other question, but if the audience has other questions, please feel free to ask.
Yeah, but I think we have to move to the next, otherwise we will be late. We will take questions for the panel discussion.
All right. Yeah, you're invited.
Always send questions into us at avatar@xprize.org. So, yeah, look, follow us. We've got a lot of social media coming out. We just announced our new judging panel. So we now have 23 judges, some people here included. So we have a most amazing selection of experts now serving as judges who will get to be inhabiting these avatars and testing the system. So thank you for the time. Really, thank you for the invitation, and thank everybody for listening.
Thank you very much.
Thank you.
So now we have live demonstrations from the Dynamic Interaction Control Lab.
Yeah, guys, do you hear me?
Yes.
Cool. So probably if we can, so what we were thinking here is that basically we enabled our camera, and now you should see basically Kourosh in my background, but there should be also another camera of Kourosh. So I don't know if everybody can stop sharing and shut down the cameras.
Jackie, you need to stop sharing. Jackie, you need to stop sharing.
It's right next to the share and next to the leave button. Yeah. Thanks.
Yeah. Okay. So if probably everybody also shut down the camera, you should see basically, you should be able to see only me and and the robot. So first of all, let me explain what you will see. Let me first present some of my collaborators. So behind the robot there is Stefano Da Farra, who is the technical lead for the Avatar XPRIZE of the ICRA team, and then there is Kourosh Darvish inside this big machine, which is basically teleoperating the robot. Then behind the consoles there are Lorenzo Rapetti and then Giulio Rumaldi. So two of PhD students with the University of Manchester. So what will you see here? So in my background, in my back, there is Kourosh, who is basically wearing some wearable sensors. So we have developed these wearable sensors, which we call iFeel, and which basically are a network of nodes. And inside there are IMUs, temperature sensors, haptic feedback system. And from this sense, the information coming from these sensors and the information coming from the model, we can basically reconstruct online the human motion and retarget onto the robot. So probably we can start the visualization of the human reconstruction. Yeah, so here on my right here, and also on Stefano, you see the online reconstruction of the human motion retargeted onto the robot. This is important. So basically we have this 2.45 gigahertz network which is communicating data, and by integrating the human model, so we know basically the anthropometric values of Kourosh, we run online inverse kinematics in order to reconstruct the human motion. Then Kourosh is also inside the virtualizer, which is basically a platform for. Oh, I cut Kourosh head. So it's basically a platform used in virtual reality. So what we have been trying to do is to use the virtual reality platform in order to somehow allow the user to walk in place as if it were the avatar system. So the idea is to take the human, monitor it, and also retarget its motion onto the robot. So in this specific demo, you will see a scaled down version of what has been shown to the Avatar XPRIZE, because we, as the ICRA team, are among the semi-finalists. That I didn't say this. I should have said this in the beginning, probably. But anyways, we are among the semi-finalists of the Avatar XPRIZE. So this is a scaled down version of that demonstration. So yeah, probably I think we can start. So we have had some last minute problems with the robot. So the forearms of the robot are not working out. So we are currently yes, and this is the beauty of live demos, people passing by. So you will see the arms of the robot not moving because we have the forearms of the robot not moving because we had some late problems with the forearms. Okay, so probably I think that you can walk, yeah. So basically now Kourosh started walking, and the robot moves accordingly. So here we have the entire infrastructure working. Oops, the entire infrastructure working, and yeah, here we got some unexpected issues concerning the robot. But anyways, what happens is that you probably can run them again. Yeah. What happens is that the motion of Kourosh is taken, and then we have the online NPC-based controllers for the robot, which generate automatically the footstep locations, and they take into account also the human motion. So I apologize because the robot had some unexpected hardware issues this morning, and unfortunately we were not to fix them all. So you will see some of these weird behaviors due to these unexpected hardware issues, mostly related to the forearm and to the FT sensors, which are used in order to close the loop. So let's see if the demo this time goes better. Yeah. Yeah. So yes, this is basically the demonstration that we had in mind, given the current hardware problems that we are experiencing today. And so I don't know if there is any question coming from the audience, and
maybe I have one. Like,
yeah.
we could see that Kourosh was walking on the virtualizer, but in a way that seems disconnected from the footsteps of ICAB. So ICAB is walking with his own central pattern generator or footstep generator, and then there is a synchronization between the two.
Yes, so basically the generation of the footsteps is not mapped one-to-one yet onto the robot. So the footstep generation comes from a simplified model of the robot, which uses the kinematics unicycle model, and then basically while walking, the controller of the walking takes the joint postures of Kourosh and tries to mimic the internal joint posture, not the external.
Okay, so the video of Kourosh is frozen.
Yeah, Kourosh is frozen. This is yet another harder problem, but is a laptop problem. So this is a kind of unexpected over the expected. Yeah.
And so while he's walking, he's seeing what the robot is seeing. So he has the projection of the camera, or is he in a virtual world?
No, he basically is what the robot sees, and he has also a representation of the robot itself inside the cameras. Yeah, this is something. Yeah. So basically, he sees what the robot sees, and it has a representation of the robot.
Okay.
Me have just a curiosity.
Yeah.
So if I got it right, the I feel chip you're using it on Kourosh is wearing it?
Yes.
Is wearing multiple of these, or?
Yes, they right now they are 4 plus 7. Yes, 7. They are 7, and plus there is the IMU used in the head, I guess. Yes. So there are 7 sensors plus the IMU inside the head. And the nice thing is that having this system, you can plug and unplug sensors where you need them. So because we basically designed it, and if you use other kinds of wearable sensors that have their specific number to be used, it's also a little bit uncomfortable to wear them.
Yeah, so that's the main reason you decided to develop yours, for comfort.
Yeah, exactly, for comfort, but also for extending it, because these have also, for instance, transducers, so they can vibrate, and they provide feedback to the robot, to the user.
Okay, so they also provide haptic feedback.
Yes, the haptic feedback system.
That's interesting. So you have all in one. You have both the haptic and the motion capture all together. And that's very nice.
Yes.
Congratulations.
If it is vibrating, you cannot use it for EMU signal.
For?
So if you have the EMU, if it's vibrating, then how, like, do you, like,
yeah, I mean, the vibration is separate from the IMU location.
Okay.
It's not on the same board.
Okay, seems there is a question on YouTube.
Yes, they say, could work. How about manipulation tasks? Would that work? And what about other senses like olfactory? Regards from Germany.
So yes, Andy. So yeah, manipulation tasks do work. We have also integrated some haptic gloves into the entire system that we are not showing today for the retargeting of the hands of the robot. And so also manipulation tasks do work. Necessary conditions for manipulation tasks to work is that the robot arms work, which is not the case today. But yes, manipulation tasks do work.
We appreciate the braveness of giving a live demonstration.
Yeah.
Yeah, I mean, it's not easy to make live demos.
Yeah, no.
The robot is still moving.
Yeah, it's alive.
Mm. So Kourosh, maybe we try to can you? So you don't have a visualization of the of what Kourosh sees in his Oculus.
Right now, no, because in the last minute problems that we got, we somehow lost some pieces along the way.
Okay.
This was somehow the setup.
I mean, is it easy to walk in this virtualizer?
So the nice thing, probably Kourosh, we can run the demo again, and we can show how the virtualizer works.
Just to walk a little bit.
Yeah. So you see that the virtualizer basically bends a little bit, and it basically works by sliding. And, clearly, it's not the same thing as doing a walk inside the, I don't know, on the street. But it's a nice step towards the retargeting of locomotion tasks. Yeah, at a certain point, so you somehow feel comfortable in walking inside it.
Okay. So if there are no more questions, maybe we can, I don't know if Jari is available for the next presentation. It would be nice if we keep the timing and if we're not too late.
Yeah. Okay, great. Yeah, I can get started. Let me share my screen here.
Okay.
Yeah.
Thank you to the Dynamics Interaction Control Lab for the live demonstration.
Thank you.
So now it is my very pleasure to introduce Dr. Jerry Pratt. Jerry Pratt leads a research group at IHMC that concentrates around the understanding and modeling of human gait and the applications of that understanding in the fields of robotics, human-assistive devices, and man-machine interfaces. His approach of maximizing speed, agility, and biological similarity through the understanding of biological counterparts is helping to remove the stereotype of robots as being clerky, jerky moving machines. And Jerry was the team leader for Team IHMC in the DARPA Robotics Challenge, where he won 2nd place, and is now a judge in the ongoing NAA Avatar XPRIZE Challenge. Today's talk is towards humanoid teleoperation of multi-contact maneuvers in constrained spaces. Please welcome Dr. Jerry Pratt.
All right, thanks for the introduction. Can you hear me okay?
Yeah.
Okay, great. Yes, and besides being at IHMC, I've also started a new company called Boardwalk Robotics, where we hope to commercialize humanoid robots. We'll see if there's a market. I attempted this 20 years ago with a company called Robotics, and we determined there wasn't. And hopefully this time, maybe there will be. Yeah, so I'm going to be talking about humanoid teleoperation with a bit of a focus on multi-contact. As usual, we're not as far along as we had hoped to be by this point, but I'll show at least some problems we're working on and some approaches we're taking. I've got a great team. I'm going to focus on 3 individuals here whose work will be highlighted in this presentation: Stephen McQuarrie, Duncan Calvert, and Bhavyansh Mishra. At IHMC, we've just started a PhD program about a couple years ago with the University of West Florida, and they're 3 of our first students who will be working on humanoid robots. Stephen, we focusing on multi-contact, Duncan on behavior architectures, and Bavianch is real-time perception. So you see some of their work, original early work in this presentation. Like to thank our funders, Office of Naval Research, NASA, DITRA, and Army. And we've got a lot of different partners and suppliers that we work with. I've been working with Claudio's group a bit, sharing information since we use a lot of hydraulic components. Moog has been providing actuators and robot we're building, and HALODI's providing some motors. I won't talk too much about our hardware in this presentation, existing robots. So I'll be talking a bit about work we've done with the NASA Valkyrie and Boston Dynamics Atlas from the Darker Robotics Challenge. That robot's 7 years old, but it's still operating pretty nicely. And then our upcoming robot is called Nadia. This is a CAD model. We have the lower body built and starting to do some tests on it. And we hope to apply all the work we're showing here to that robot in the coming year. All right, so this is a video of John Karff operating Atlas using operator interface with a virtual reality headset. We have several different modes of operation that he can choose from. So walking up to this door, he was just joystick walking, saying, you know, walk in this direction, and it was determining its own footsteps. Now he's going into the pure teleoperation mode where he's purely teleoperating the arms. I don't know why I jumped back there. In order to move debris away from the door. So you can see kind of the ghost image of where the robot's going to go as he moves his arms, and then when he, since there's a little bit of delay from the slow arms catching up to him. Oh, why does it keep resetting there? Something weird with the video. Okay, and so he'll clear the debris from in front of the door, just one at a time. And then once the debris is clear, you'll place a couple footsteps on the ground manually to get closer to some more debris. Pick that up, and then use a autonomous door opening behavior where you'll say, okay, there's a door in front of you, go through it. Right now you can see there's a QR code on the door. We are currently working on door perception. And then we have autonomous behavior that's fairly scripted at this point that knows how to get through doors. Okay. So in that video, you saw some different modes. We had joystick walking, desired waypoints where you can just say walk over there and they'll plan a path over rough terrain, pure teleoperation, so far of just the arms, and being able to select some semi-autonomous behaviors and interact with them. So one of the biggest challenges we find, especially in trying to have different modes of operation, is allowing the operator to interact at various levels. So it'd be nice if during some high-level autonomous behavior, the operator could say, okay, I see that you're doing this and I'm getting feedback and I see you're going to step over here, but that one little footstep, change it before you take it, or and have it, you know, be able to select those things while the robot's operating, rather than having to stop it, change some parameters or whatever, and then say, okay, restart that behavior, just to seamlessly have the operator jump from level to level. We've achieved this to some degree on some things, but it's just a very challenging software engineering challenge, actually, to figure out all the hooks and everything, and how do you come up with a behavior architecture that allows you to author behaviors and allow it to have flexibility with the operator. In doing all this, we always try to think about what we call coactive design, where we're constantly asking ourselves, what's the robot doing? What's it going to do next? And how can I change what it's going to do? That's observability, predictability, and directability. And you know, instead of trying to say, okay, have the robot be fully autonomous or fully teleoperated, it's more about making sure the operator has all the information they need to get the job done. And sometimes we find it's best to just give them extra, you know, even if you think it might be overloaded, they're just going to ignore stuff they don't need until they need it. Allow them to have a sense of what the robot's going to be able to do, and to avoid the frustration that always comes with robotics of how do I get it to actually do what I'm trying to do. And of course, those are all challenging. So this is showing Atlas walking over cinder blocks. We finally got real-time perception working. Before this year, we would typically require about 20 seconds for the LiDAR to spin and capture terrain and find planar regions and plan. Now we can do it essentially real-time. You know, faster than Atlas can currently walk, but that's not terribly fast, only about 1/4 meters per second. So you see here the what it's sensing directly in front of it, and the plans it's taking. And you notice that Stephen had moved some stuff as the robot was walking. So we're psyched to have real-time perception working now. A lot of this is running on GPU. This is a lot of Babianch's work, and you know, you should, with today's technologies, achieving about 10 frames a second of perception all the way through footstep planning is achievable. So that's great. Okay, so when we did the teleoperation of the arms that I showed, it was it's pretty straightforward to do that because you have a almost direct kinematic mapping from the human to the robot if all you're doing is moving the arms. And all you really need is a couple, you know, $300 headset with some hand controls. We're only doing standing balance, and as long as you're doing small interactive loads, the balance can be easily corrected. As you saw in previous talks, if you have heavy loads, then you got to account for it. And but just pure teleoperation of arms is pretty straightforward. If you want to start doing more complex things like, you know, teleoperate walking around while you're doing something. So, you know, imagine like, I don't know, carrying boxes and putting them on shelves as you're walking by without, you know, that becomes a lot more complicated. And then if you interact in a real world that has much more complex interaction than just picking up objects off the ground, it becomes a lot more complicated. So this is, you know, just showing what it looks like when you're teleoperating the robot using just arms. So, you know, pretty straightforward mapping. Even though we're only tracking the hands, you have whole body motion. So when Sylvain goes to pick something down or goes low, the robot will decrease its height. So we have, you know, full body inverse kinematics. And we also do collision avoidance using just simple convex shapes on the robot to make sure they don't collide. And then you can see kind of the human input, and since there's delay from the motion to the human input, the robot will lag a little bit behind. Perceptually, you don't even notice it really. So fairly straightforward to do this sort of thing. But we want to do more complex things, of course, and some of our long-term goals are we have multiple contacts on the robot, like climbing up on the table and changing a light bulb, climbing rocks, spelunking, you know, going through obstacle courses, places where not just your feet and maybe your hands are in contact with the environment, but where potentially any part of your body is in contact with the environment. Confined space entry is a very interesting one in the chemical industry. There's a lot of money spent in cleaning tanks, repairing them, inspecting them, and they're very interested in using robotics for doing a lot of that. They do use a lot of crawling robots, but they still can't get in a lot of really tight spaces so a human has to suit up. So of course, there's a lot of challenges. You know, dynamic balance, that kind of has to be performed on the robot side because of delays. You know, the operator's not going to be quick enough probably unless you get super fast comms. Perceiving where the potential contacts are, figuring out, you know, what's a suitable surface and how much load you can put on a surface, you know, detecting the difference between a stair and an empty box. Then contact detection, what part of your bodies are making contact, feasibility of motion, planning, and then all the operator feedback and situation awareness, and then the hardware itself. So of course, there's just so many different things that go into making this sort of thing happen, and they're all very challenging. So we'll take baby steps and not worry about dynamic balance yet, just worry about static. For now, we won't put boxes in the world, just everything that's out there is something that you can apply forces on. For contact detection, you can do a partial solution by looking at joint torque sensing and kinematics if you don't have robot skin. For motion feasibility, for now we just assume convexity of motion, meaning that if you have a feasible waypoint and another feasible waypoint, assume that you can take a fairly straight line path between the two and everything will be feasible in between. That way, operator only has to think about a sequence of waypoints and not all the motions. Later, you'd probably want an automated planner for that. We're not worrying too much about planning. We'll just let the human input contact sequences for now. And we're developing new hardware for the hardware problem. Okay, so this shows our virtual reality multi-contact teleoperation interface. And it's a bit sped up since lots going on here and takes a while. But what you're seeing is the operator can grab parts of the robot and apply kinematic constraints on them, either hard constraints saying these points on the foot are on the ground and will not move, or soft constraints saying I want this body portion to move in this direction, move it in that direction. And so what we're trying to do here is get off the ground. As we're doing it, we'll compute the support polygon, which is the dark blue region in the middle. And it's making sure that the robot's statically stable as it does it. And then on the right, you can see a simulation as the operator does each motion. So this is a very clunky interface. It takes about half an hour to stand up, but if you're persistent with it, you can do it. And if you practice with it, you can get down to about 5 or 10 minutes. But it's still, very slow. Let's see here. Yep, so it's doing the whole body inverse kinematics as you give it motion constraints, coming up with a sequence of valid poses, and then just moves between them. And then once you do that, then that saves a script. You can reload it, remodify it, and play it back to improve your script. Let's see here. So here's some things we did just for getting up off the ground using different things in the environment like boxes and tried different ways to get off the ground. And of course, the kinematic range of the robot is very important for how difficult it is to get off the ground. Here we're using Valkyrie, but we opened up the joint limits a little bit since some were pretty tight. But it's definitely, you get into some very challenging poses where you're trying to figure out how you can move a limb given the kinematic constraints of the robot. But you're still able to get off the ground. So that was, if all your surfaces are flat, you just look at your support polygon. If you have non-flat surfaces, then you can look at your static equilibrium region, like Brettle's paper in 2008. So we just use that where you're computing, given the contact surfaces and the surface normals, you can compute the support region where your center of mass has to be above, and that can lie outside your support contacts for interesting cases. But we're still ignoring torque limits and reachability. And then if you want to expand upon that a little bit, you can add acceleration and determine what your acceleration cones are. And that's Steven Caron's paper for reference. So then what we'll do is in the interface start plotting some of these regions so that the operator can visualize them. So right now when he's just standing, he's got a very small support region. Here we have some tilted surfaces. Once you attach the contact to it, for one, it doesn't grow the region very much, but once you contact the second one, you'll now see that the support region has grown such that the center of mass can lean backwards. So this is like if you're holding onto a table and leaning back, you can have your center of mass behind your feet and your hands and still support. And then the robot will lean backwards here. Once you pull the chest, let's see, I guess in the next video. Okay. So this is the simulation of what the operator was just doing there. And then you can tell the robot to lean backwards. Haven't done this on the real robot yet. We hope to in the coming months. Okay, so an observation in all this work that I see over and over again is if you have a human in the loop and you're using the big supercomputer brain of that human, it is incredible what you can do with a teleoperated robot. If you have even an okay robot platform, just seeing what some hobbyists with very shaky arms can do, teleoperating a robot to like make spaghetti and stuff, and you need a okay robot, an okay operator interface, and a human in a loop. It's incredible what you can operate remotely. However, with the one caveat, if you give the operator infinite time, some of these things just take forever as you're like, trying to figure out how to pick up the spaghetti and crush it and put it in the pan or whatever you're trying to do. But a human will figure it out. If the hardware is capable of doing it and you've got a talented operator, they'll figure it out. So really one of the ways, we can look at this as the major challenge in all of this is, well, first figuring out how to do it. But second, figuring out how to get you fast operational tempo so that it's actually useful in the real world. All right, I'm not going to talk much about this. I'm running out of time, but we're developing a new humanoid robot platform called Nadia. This is the most recent CAD models. What you see from the waist down is built, and we're starting to get it up and running, and we're fabricating the top portion here. Hopefully in humanoids in a month and a half, we'll have something to show on that robot. So our next steps is to continue improving everything and integrating everything. A lot of this work is somewhat incremental in that, a lot of it has been figured out by various people over the years, but there's just so much of it that needs to get working and integrated on a real robot. But then there's also some problems that need to be solved for pushing it a bit forward. Particularly, I think what sort of operator interface allows you to interact with these systems a lot faster. Now, it would be great to just purely teleoperate, and with arms you can do that. If you're lifting small loads, you can do that. But if you're trying to climb a mountain and the mountain's not there, if you're trying to use something that doesn't have pure teleoperated, doesn't have good force feedback on you, and doesn't virtually make the world in front of you, then you can't really you don't know exactly how the forces on your body are such that you can figure out how to get through, and you're not feeling the contacts. Maybe we'll get to the point where we have awesome exoskeletons, and some people are coming up with some great ideas on how you can apply forces on a person through an exoskeleton, but those are going to be super expensive and probably still won't be perfect. So how you can actually do this without applying forces on a human when getting through the environment is all about the forces and the contacts and all that is going to be an interesting problem. So and then building the hardware for it, of course, is always a very, very hard challenge. Yeah, and we have a long way to go before we match human mobility. If you just think of where humans can get, it's incredible. And we hope to be doing challenging courses like this sometime in the next decade. We'll have to see which year. All right, and thanks for your attention.
Thank you very much for your presentation. Now, if anyone from the audience has any question.
I have one. So do you think I completely agree on your observations, but do you think you really need to have the operator teleoperating all the possible motions, or should you, for example, delegate?
Yes, of course, yeah. You definitely you want to add autonomy where it's going to help take a burden off the operator where you can. But there will always be, until robots take over the planet, there will always be things that you need the human to be doing. So as soon as we are able to do one thing autonomously or whatever, we say, okay, well, let's do this next thing, which we can't do yet. And in any of those situations, there's going to have to be some sort of human input, and that's going to slow you down again. But yes, hopefully we can get to the point where walking through a door, it shouldn't be that hard to do it autonomously, open it up, get through, any type of door, and then the operator should just have to point at a door and say, walk through that. And then there's also the question of feeling that you're present at the remote location. If you're doing that, if you're walking through doors by just saying, walk through that door, do you somehow lose a bit of the sense that you're there? Or do you just, does your brain morph to then think that that's how you actually get through doors? And when you get back in the real world, maybe you'll start pointing at doors to say, hey, I want to go through that door. I don't know if you've ever played a virtual reality game called Super Hot, where it's a shoot 'em up game. But if you move slowly, everything in the world moves slowly. Well, if you've ever gotten addicted to this game, which I have, and you play it for, half an hour, take your headset off, there's been times where, like, my daughter was walking past me fast once, and I wanted to talk to her, so I started moving slowly to slow her down. It's like, oh, that doesn't work in the real world. So maybe we can get this sense of telepresence, even if the physics isn't the same, because it's not going to be the same, and even if the way of doing things is not the same, maybe after you do it for a while, it won't matter. You just feel different. You have two different ways of living life. One when you're avataring, and that's, you get an understanding of how the system works, and hopefully you can switch modes without getting too messed up mentally.
Have you investigated the use of shared control approaches? They're basically a mix of the two.
Say that again, a mix of what?
If you have investigated the use of shared control approaches.
Where you're mixing like autonomy and pure teleoperation.
Yeah.
I mean, that's where we want to get. And right now it's kind of mode switching, where you on your joystick, you say, okay, now go into teleoperator mode. You do it for a while, and then you say, okay, now go into, I got to move forward a little bit, go into, but it'd be nice if that can be so seamless that you don't, or happening at the same time. But no, we haven't done that yet. It's all been mode switching.
Okay. Yeah, we have the same. So I had a question, because so the teleoperating the multi-contact, like lifting from the ground, was pretty impressive. Like, I have to say, like, I don't imagine even how to do it like autonomously with the robot. But so when the operator does that, does he have like so based on what they tell, do they reason with their dynamics or with the robot dynamics, or they learn to reason with the with the robot dynamics?
Yeah, I think there's a bit of a learning curve, because again, the biggest constraint is the reachability and the range of motion of each joint when you're trying to like get off the ground. Because even as a human, you really get into range of motion limits when you like get your knee underneath you and all that. So you start to learn more about what you can do as you do it more. For balance, you've got a really good sense of physics and knowing that you have to have 3 points on the ground and all that. But then by painting the support region underneath you as you're doing it, you can see, oh, I can't shift my weight over this way because I have to, I don't have a contact here. Let's put a knee down over here. You put the knee down and boom, the region grows. And then, okay, now I'll move the support region to lift this hand. So that's very intuitive to human. And then also range of motion limitations. It's very intuitive when you see an arm that's kind of stretched out to realize, oh, that's the one I got to move next. So I think it's a combination of just physical intuition of living in the real world, and the robots, they are anthropomorphic, so you kind of feel like you're trying to do it yourself. Yeah. And when the robot gets in a real contorted position, you'll know it. And like there's been cases where you have like the hands on the ground, just the hands and the feet, and the center of mass is shifted forward, and you can just see there's way too much weight on those arms. Now you could have more constraints on the joint torque limits, and it would allow it to do that. But just as a human, you just know, whoa, that guy's, if I was trying to do that, my arms would collapse. Let's shift the weight back to the legs to get some weight off the arms.
So we need to work on like augmented interfaces, like more intuitive.
Right, and if you can have ways to like, I don't know, maybe like start painting something red as it gets to a limit, or just feedback that a human can get a quick intuitive sense of what's going wrong as you're operating it, then it'll speed things up.
Okay, thank you very much. You're very welcome to join the discussion later.
Okay, thank you.
If you can, if you want. And we can move to our last speaker. Our last invited speaker is Professor Robin Murphy. Okay. So she's the Rito Professor of Computer Science and Engineering at Texas A&M University, a TED speaker, and AEEE and ACM Fellow. She helped create the fields of disaster robotics and human-robot interaction, deploying robots to 29 disasters in 5 countries, including the 9/11 World Trade Center, Fukushima, the Syrian boat refugee crisis, the Hurricane Harvey, and the Kilauea volcanic eruption. Murphy's contributions to robotics have been recognized with numerous prestigious awards, including the ACM Eugene Laurel Award for Humanitarian Contributions and a U.S. Air Force Exemplary Civilian Service Award Medal. She has written best-selling textbook Introduction to AI Robotics and the award-winning Disaster Robotics, plus serving as an editor for the science fiction, science fact focus series for the journal Science Robotics. Her today's talk is 2 robots are better than 1, successful integration in extreme environments. Please welcome Professor Robin Murphy.
Luigi, thank you for a wonderful introduction. How do I share my screen? The icon disappeared.
So next to the leave button on the left, there's the share screen, share content button.
Yep.
Next to the green one, the red one.
Yeah.
Okay,
on the top
it's not,
right.
Top right. It's not showing anything. It was there a minute ago, but it's gone away. So my apologies, everyone.
No problem. So is it, do you have the window, do you see the window of the application?
Yeah.
Okay. So on the top right, normally you should have a red button saying leave.
And next to it, there is a button that is share content. There's like an arrow.
Yep, it was, let's see, now I've got chat. I'm working off of a Mac, and it's very frustrating because I saw it a while ago. And then something happened, show device settings.
Okay,
Go back
raise the hand.
I'm on a Mac, so.
Yes, on a Mac they say that it's different.
So in my Mac there is it's close to the leave button, and it is basically there's an arrow inside a square.
Right, and that share, and it comes up with nothing. So let me go back. Let's see if there's any preferences I can set really quick.
Otherwise, you can leave and re-enter, and we can try like that.
Why don't we try that? And I am so sorry, and hopefully what I have will...
No problem, no problem.
All right, I'm back. Now, let's... No change.
Jackie Mori, maybe Jackie can say something. Oh, she left.
I think maybe Kourosh can verify if she's enabled to present.
Because I don't have a Mac, so I don't know. Worst case, you can send us the slide. I can share it for you.
Let's see. Let's do that.
So they say on a Mac you need to enable sharing in system preferences.
I'm going over to system preferences. Thank you.
Otherwise, I take the presentation.
All right, where's the sharing icon? Sharing. Okay, so I've turned on sharing.
So there is a suggestion from Ludovic. It says go on security and privacy in the Mac system preferences, And then authorized screen, you have to enable authorized screen recording.
All right, so I've done this. So now I'm going to security. I got to system and security and
Authorized screen recording. Select the privacy tab.
I did. There we go. There's screen recording, and I'm making it for there. And then I've got to quit and come back. Well, howdy, everyone. Let's see if we can make it work this time. Yes, it looks like it's going to let me share. Oh, yay. Thank you, everyone.
Yeah.
Can you see?
Yeah, it works.
Excellent. Well, let's go get started, and hopefully this will be of value to all of you after having to wait so long and getting to learn more about my Mac. All right, so I'm going to be talking about teleoperation extreme environments, and of course I don't do leg robots, and I don't but I do work with all sorts of robots in extreme environments, particularly disasters. So I'm going to be talking to you primarily work that's been done by one of my recent PhD graduates, Jan Dufak, with a great team of people helping him. But I think you'll really like the work, and hopefully it'll add value to you. So when you think of extreme environments, think of like the Indonesia earthquake and tsunami. I mean, close to 3,000 people dead. Horrible. But look at those numbers for homeless. People's lives are changed forever. And look at the rubble that you have to go into to try to find people alive or recover. So when we do disaster robotics, roughly 50%, a little bit more than 50% of the missions are in what I would call an extreme environment that is teleoperation. And there are two reasons for that. One is that the experts, like a structural engineer, can't tell you what to look for until they see it. So they want a real-time streaming. Also, during the response phase, there's an extreme time pressure, like Jerry talked. You want to be fast and they don't want to do things like send a robot in, have it go work for 4 hours and then come back, because it may never come back. It may fall apart. There may be a secondary collapse. There may be something else go wrong, and they would lose any data that they got there. So they want streaming. So really what they would like is teleoperation, but with mixed or shared autonomy. They definitely want guarded motion. They definitely want mode switching. They're not looking at full autonomy because they need to stay in the loop. So when thinking about these robots, the big thing is to think about the work envelope. Where is that robot working? And for me, there are three critical factors. There are multiple regions that a successful system has to go through. We'll talk a little bit more about that, but the regions, how are you getting in to that void, to that building, the inside? What are you doing once you're inside? How is that changing as you go? And how do you get out? Then there's traversability, which you're all familiar with, is that can the robot move through the region? But there's another aspect to traversability that I think often gets overlooked, and that's scale. Will the robot actually fit and be able to work in the smallest part of that region? And an example of this is, remember the kids that were trapped in the Thai cave? You know, it wasn't just that they were trapped in a cave and the cave had very, very narrow areas. It was also that part of the cave was totally underwater and part of the cave was partially water, and some of it was very wide open. So the scale, these were regions. The workspace would be different. It was multiple, actually, regions. So having somebody like Elon Musk, oh, we've designed an underwater robot. Well, great. That covers, what, 30% of the problem? Doesn't cover the whole one. And you have to have a system that works for all of it. All right, so when we go back and look, my analysis of the 13 reports I found of UGV deployments I could get details on, 8 had at least 2 very distinct regions in terms of their work envelope and what that means for us. And so let's think also, besides the number of regions we've got to contend with, there's traversability. We know there's tortuosity, how many turns you have to do, which causes problems. In search and rescue, you're doing a lot of verticality. You're actually usually you're at the top of a building going down inside. Whether or not you have favorable surface properties, we all love to walk in mud, right? And severity of obstacles, and then the number of accessibility elements. Accessibility elements are things like doors, right? These are architectural structures, and they usually mark a change to a different region, but they themselves can be very hard to navigate through. The third aspect is scale of the environment to the agent. And this is where we get into dimensionless numbers. Okay, so if you think of granular areas where the robot is burrowing through, think of this as the environment has a characteristic dimension, and that agent, in this case a sandworm, sand lizard, has a characteristic dimension. Usually the cross section, if we think of humans, the cross section of their shoulder, and that tells you whether or not they can turn around in place. So another category is restricted mobility, where you're not having to burrow through an environment where you're bigger than any of the holes or voids. A restricted mobility, a person can get in, but it's very dangerous because they can only back out. They cannot turn in place. So they don't have 2 shoulder widths to turn in place. And that gets under Occupational Safety and Health Administration, different agencies, very restricted, regulations covered with that. And then we get into the normal stuff, right? Where it's we can turn around, we can move around. The environment is more than twice the size of what we have. We can't really do granular robotics right now. I mean, there's some beautiful work coming out of Georgia Tech with Dan Goldman's group, but you're seeing mostly our work. We've done great in habitable exterior areas. Restricted mobility, maneuverability areas tend to be very hard, right? You're just right up with the maneuverability. So if you think of this as a dimensionless number, you do it as a division. You see granular is less than or equal to 1, it's burrowing through, less than or equal to 2, you're squeezing or crawling through, and then greater than 2, you're outdoors. Well, what does this got to do with teleoperation? Well, this area right here, this is where the most benefit is for the use of robots, because if a person could have gotten in, they could, and we're building robots to try to get into as small a void as possible, so as their agent size is small, they're still small compared to the environment. So as the operator, or even the robot is just more likely to get stuck. If the operator or an autonomous system, you just don't have a lot to see. Your viewpoint is restricted because you are confined. And the options for recovery, the old style PackBot flailing around till it's self-righted, that doesn't work as well. We just don't have that. So this is what gets interesting. And so what we've seen since 2001, it's 2 robots, 1 task. At Fukushima, you have this second robot. It isn't there just to get pretty pictures of the robot. It's there to help the operator in the first robot be able to see where they are relative to the door and what's actually going on. So it's not uncommon. It's, in fact, the opposite of common. It's very common to use 2 robots to do 1 task because that second robot can be moved around to provide a better viewpoint. And that's still continuing on at Fukushima. They use this 2 doing 1 task. And if you don't, there's problems. So in this case, a warrior robot, close to a ton of a robot, uses a small first look to be its spotter, right? Its secondary robot. Well, one of the crews for decommissioning decided that it wanted to, it didn't want to wait for that second spotter robot to come over, and they ran the warrior without looking, and of course it tripped and fell, and in the worst possible place. And they couldn't send any people in, the radiation's too high, to manually dismantle it. So imagine dismantling a complex warrior robot, PackBot Warrior with only teleoperation with other robots. Yep, it shut the whole thing down, that whole area of decommissioning for several weeks. So we want to do that. Well, what we've been looking at is how to handle that autonomous visual assistant. What is that secondary robot doing? And in particular, looking at perceptual psychology. How do we know that works with the way the human brain works? And then we can help the teleoperator and then help the robots themselves become autonomous. So I think the best way to do this is to show a short video, and then I'm going to go back and explain a bunch of stuff. So let's try the video first. It is common practice to use two robots for a perceptually difficult task. For example, reaching into narrow or regular voids. A secondary robot can give the operator a better understanding of the task than what is being seen on board for the primary robot, thereby reducing the task there. However, what is the optimal viewpoint for that secondary robot? Since 2003, studies indicate that operators choose vehicles.
The video is kind of frozen.
I'm sorry, Serena?
We don't see the video moving.
Oh dear. Do you see different frames?
No.
We are just having a complete Murphy's Law today, aren't we? Okay, are you seeing anything now?
No, it's still one frame.
Okay. Let's see if we can try this again. Let's see if we can see it from this way. Can you see the line?
No, now we see the PowerPoint interface.
Yeah, can you see the image?
Yes.
Yes.
Okay, now you should. Okay, let's walk back through. I'm just going to do a stutter shot here. So you should see a stairwell, and here's a case of where a team had multiple camera views, and they picked the view they liked, and what happened was a major crash. So we've seen that happen time and time again. Okay, so it shows that crashing. And then we get into areas like this where you're trying to get a robot to be able to move and pick, like help somebody out of a car or find something, and those are very difficult views. All right, so what we are doing is looking at visual perception of what are called affordances or direct perception. I'll explain after we see more of the video. And we did a study with 31 operators, including in the US and Japan, all of them who use this for hazardous materials, bomb squads, and for decommissioning. And what we've learned, let's see if I can get this up here. So if you think about a hemisphere of possible views around the robot, that the secondary robot, if it's an aerial vehicle or a ground robot, what views can it do? We can model that as a hemisphere. Okay, and so you should see the hemisphere around. And what we did is did that study, we sampled and have them try 4 different affordances. And I'm going to scoot out, and you learn a map from that. So let's see if you can see the video now. So you should see an operator's typical view in the corner. Do you see that?
Sorry, I don't see that.
We keep seeing just the first slide, like best and worst external viewpoints, but we don't see the video.
No worries. All right, so that's clearly not going to work for us.
If you play in this video, like in this interface.
Can you see it now?
No. No, we don't see it.
Are you seeing the video now?
No. Still just the title frame.
Okay, so it's playing for me. And let's end the torture. So what you would have seen is, think of yourself as going through a door. When you're going through a door, you want to be looking at the door, right? The open frame. If you are forced to look on the side, right, looking sideways, you wouldn't have any relative position of how to get in there. And so that's a problem. And so we had examples of that and how you could dramatically improve by this choice. But let's just go through with the idea, what you would have seen on there. Is that, so you have a task, something like go through a door, and you can decompose those into actions. Getting to a door, reaching for the door handle, opening the door, passing through the door. So each of those actions have an affordance, a direct perception of things like traversability. Can I get to the door? You know, is it bumpy? Reaching, can I reach? Is the robot where my arm can reach it, or do I have to move further? Open the door. Can I turn the knob? Am I in the right position to do that? And then pass through the doors. Do I have the visual cues to safely pass through the door? And then those viewpoints can be quantified with our study based on psychomotor behavior. And then you can rate those and create manifolds where green areas would be the best. If you could get your secondary robot there, that would be the best area. The second best would be blue. The least good would be the red, but it might give you something. So that's our general approach. Now, if you take that hemisphere and project them into two dimensions, you see these manifold maps where dark green means really good, like you're getting 25 to 30% better improvement in time and 100% improvement in errors. Red means very bad. So reachability, is my robot in the right position that I can actually go and grasp something? Manipulability, is my robot where I can, the arm where I can turn something or manipulate it? Looking directly behind's not good, looking from the side, but looking from above, looking down. And that kind of makes sense. You think of yourself as looking down at picking a coffee cup from that angle. Passability, again, looking, actually the best view is from you looking towards the robot coming through the door from the other side. The next best view is back there, is from behind. Traversability, looking above, slightly above and forward to see how the robot is navigating. So we've got, the exact numbers there. But anyway, can't show you the video. I'll send you all the link to all of this. I am so sorry. Murphy's Law with all of these complications. But the big takeaway is that secondary viewpoint is going to give you somewhere in the order of 37 to 48% increase in performance, and often 100% decrease in errors, like hitting things. Okay, so that's going to be really valuable when you're working in restricted maneuverability spaces. You can take a task and decompose it into actions. Each one has its own affordance. So it isn't like, well, I have to do more than one thing. Yeah, but you're doing them overall sequentially when you think about the perceptual psychology of what you're doing or what your robot's doing. The best manifolds, you're seeing the numbers there, great improvement. And the manifolds, what's nice, can be quantitatively ranked to aid in planning. So one of my other students, Dr. Chu-Su Chow, created a planning thing that would go and look and say, hey, the best viewpoint is this manifold. If I can get anywhere in this manifold, I'm great. I can't get over there to that part of the manifold because there's an object there, but I can't get over here. Or I can't get to that manifold. Let me see what I can safely get to over in the second best manifold. Okay, so that's helpful. And we see this as being extended independent of whether your secondary is a ground robot or aerial robot. You would have seen that ground robots clearly in the video clearly don't give you as much information as nice having a nice UAV that can do the whole hemisphere, but they give you something. And you can extend this to autonomy, and this is what we'd really like to do, is where we have a teleoperator controlling the primary, but that secondary robot is autonomously providing that position. So then you would have had at Fukushima, where the decommissioning operators didn't want to wait for that second robot and the other two operators to come over to their team and do it themselves. Instead, it's the same two team with the primary are able to control successfully the second one. So that's what we've got there. Let me get the stop the sharing screen. And again, my apologies. If we have any time for questions, I would be happy to answer them.
Yeah, thank you for the presentation. And now we have the panel discussion. So if you want, we can start directly with the panel discussion and get the questions there.
Great.
Yeah, okay.
So for that, I leave the word to Serena.
Actually, because I think it's very interesting to have a second robot that actually is providing the sort of a third-person view of the environment. And it's actually something that also with Luigi we experienced when we were teleoperating, because it's very difficult to have, at least for us, to have like the full representation of the situation of the robot just from the robot perception. And so we added an environmental camera, which in our case is the last time, but for outdoor applications, and I wonder if there are examples where you use different kind of robots, like also quadrotors, maybe if you have like a top view.
Yes, we've used quadcopters. That's really what we designed it for. Saw the biggest win was quadcopters, and in particular tethered quadcopters, because the nuclear energy and the process safety people don't want anything flying away. So they love the idea of a tethered robot. You keep it down until you need it. It pops up, it goes sideways, it looks around. It can also look over things like up in the pipe racks and there. And if the tether gets cut, bam, it goes down. We don't have to worry about, and we don't have to, nuclear facilities don't like multipathing, wireless communication issues, interference. So they really like that. So we started off with that. And you can really see that having that top-down view, particularly for grasping, is really helpful. You know, because most of the time you're using like this because it's a human design system, or we're thinking mentally that way. Unlike humanoid robots, most of the robots we work with don't really correspond well. You know, the human can't really think of himself as a 4-degree manipulator with a prismatic joint. And so it's very hard. But the other aspect is we often don't have room. So a lot of times in very confined spaces like mine disasters, you only get another robot behind you, but even that helps, right? So having a robot that can just put its arm up in arm camera to look a little bit up before it hits, you know, the ceiling, it still gives you something, and that's very helpful.
In terms of in terms of interfaces, like what was the key features that we need to have in like interfaces? They provide extra information, augmented reality to help the operator, in teleoperating.
For our systems, we've always recommended 2 monitors. So you get your, you know, you get the PackBot view and you can play with whatever quadrant and what you're saying, but to have that second view, and typically we try to stack it where it's very easy because you begin to see the operators do this rather than looking at the robot view, the primary view. So I think there's a lot of work we'd like to do in looking at how do you do your actual positioning. That picture-in-picture is kind of has never quite worked. And then how do you do it when, you know, most of these for real robots, I mean, not real robot, you know, for commercially available robots, those interfaces are usually proprietary and they don't want you messing with it. And so we have to always add on to it.
Okay, so I think we can have a look at the questions. If there are other questions, I haven't checked online. No, and not in the chat. So, but
so
thank you.
I have one question, Serena. I'm very curious, actually. So thank you, Dr. Murphy. It was a very interesting talk. It's nice to have a hit of reality on our research. So I really like your talk. So one quick question is, so you mentioned that a lot of the robots are tethered. So I was curious, what percentage of the robots that actually deploy disaster response are tethered compared to not? And if eventually, because we've been all looking to this wireless communication things, but if you come up with a system that is tethered, is that still useful?
Okay, for actual real disasters, 100% tethered. All of them have been tethered. So you look at Fukushima; those PACBots were running fiber optic because they couldn't be sure of the wireless and they couldn't be sure of the radiation and the interference, and they still run them with that. If you're going to run a fiber optic cable, you might as well run your power cable as well. Yeah, you have to worry about induction. You have to put a little more weight on that. But then you can, once you get the power off, then you can shrink down your size, and then you can sit there and have infinite power, right? You just, you know, in the field, we typically look as the ultimate plan is a car battery, a 12-volt battery at the end of the day, right? And you just swap out to another battery and we're done, you know, where you're sitting away from it. And, you know, so those things. So I think there's a lot of distinctions to be looked at, you know, as the tethered robots are really good for that initial, holy cow, everything's gone wrong. We don't know, we don't understand the situation. We can't make things worse. And that phase is usually 3 days to a week, maybe at most 2 weeks, because people, the mortality curve is 52 hours. After 52 hours, if we find you alive, you will most likely die in the hospital. Seeing as that, so it's real pressure at the very beginning. After the response, though, after 2 weeks, it goes to what's called recovery, which is really, really important. Like, think of Fukushima. It took months to stabilize that, right? And so then you've got less time pressure, you know, but you've got some constraints, but you've got more freedom, right? In terms of, okay, now we understand what's going on with wireless, and now we understand this. And if something blocks this area, the world will not end. The Pike River mine disaster, the robot failed, and of course it failed in the worst possible place and blocked anybody else or any other robots getting by. Okay, so we want to keep that. But now that's not so bad. If you're doing a recovery, then you can bring in another robot and haul it out. Okay, so I see tethered systems, is it not exclusive? You know, have a tethered system, have it be able to go off tether, have it be able to go back on tether. But it does make it more complex. And think of that as a teleoperation. So what you start seeing as errors is that, oh, tethers, those little automatic wind-up reels, they don't actually work. They work just enough to make you think they're working, and then the Mine Safety and Health Administration here in the United States has had several mine disasters where they've run over the tether, and that's with highly trained people. And the manufacturers say, oh, look, we're giving you a camera to look at the tether in the back, and that'll help. And it's like, sure, to go with the other 6 frigging cameras that we're having to look at. You know, no, this is not working. You know, the human can't do this. And so keeping that in mind with teleoperation, what to look for. Anyway, sorry, I kind of went off on a rant there.
No, thank you. That was a great answer.
Yeah,
Luigi, I think, yeah, Luigi, so, please go forward.
Given that you're the less biased person to respond to this question, I'd like to ask you, how do you see human robots in real-world applications, especially in disaster response applications?
By the way, what beautiful work we're seeing. My hats off to all of you. What excellent, great work. So think about those spaces, the scale. Humanoids are going to be very useful for the places where people can go to. So now they've got to compete with people. So when would you not put a person in? Well, if it's high radiation, or if it's a process safety chemical plant, and then you've got to be intrinsically safe, right? You've got to prove that you're not going to blow up the facility. Okay, but I think that those are great places. Mine disasters, you're seeing a movement to, you know, things that fit into a half a meter wide hole. So that's probably not going to be a big win. Building collapses, you're going into, again, these very narrow, tortuous, high tortuosity, high turn number void. Probably not going to be a big value there. But for process safety, definitely, and nuclear, definitely, those are places where people can't go, and there are lots of those situations.
Yeah, that is good to know because we're always worried about. We get a lot of criticisms about our wish to see humanoids in the real world, and so thanks to you, we have something extra to.
Well, think also about parking. So when you have an earthquake, most of the buildings, you know, typically fall. But if you've got something, a commercial structure like a parking garage, which is, they don't know if it's intact or not. So a humanoid, that's a human occupied, that's a large space. You could, but they can't send a person in. Most countries won't let you do it without putting lots and lots of scaffolding in to make sure it won't fall on them. And so having a humanoid go in those spaces. But for an earthquake, oh, they're going to go into a building. No, because the building is in rubble, right? And if there was anybody alive, a firefighter would have risked their life to go in and get them. So now it's more this area that we're uncertain about and use there. So just wanted to add that to y'all's list.
Yeah, I actually have a question for, since now we are in the panel discussion session, I also have another question for the other speakers. And actually have a question for Jerry Pratt. I don't know if he's connected and hears us, and also for Claudio Semini. So two different questions. So first of all, thank you again for coming here. Jerry, so I wanted to ask you about the teleoperation of wearable sensors and wearable technology in general. So what is your vision about the role of wearable technology and teleoperation of humanoid robots? And then I have another question for Claudio, but yeah. I think you're on mute.
Vision for wearable robotics for teleoperation. So I guess, are you asking more about just let's see here, as an interface device, as an operator interface? So
yes, so for both measuring human quantities and bringing feedback onto the human. So
yeah.
Well, what is the next somehow stage that you see for wearable technology?
Yeah, it's a good question. You know, it's hopefully we'll get to the point where we can do really good, you know, force feedback on a human and actually feel like you're there. Time delays become super important when you're doing that sort of thing, especially if you're doing like fine manipulation or all that sort of thing. Now, if you've got a ton of money, you can definitely make a really super good, you know, exoskeleton where you could have, you know, imagine like, you know, cables coming from big, you know, motors or whatever to every little marionette and every little part of your body. So it's definitely, I think, feasible to get you to the point where you're feeling force feedback. What's going to be really super challenging is when you want to feel like you're in the environment itself. So I'd like mentioned before, if you're, say, mountain climbing, can you actually put the mountain in front of the person? When things become super rigid like that, you need large forces on whatever's simulating the world, and it's going to become dangerous. We had a concept a long time ago for doing something like that ended up not getting funding, probably for the better, where the idea was you got like two big robot arms holding onto your feet, you know, like industrial scale things that can, you know, rip
like
you
Pacific Rim, like the movie.
Exactly, like the Pacific Rim thing. And sure, you could do that. It's now becomes a question of safety. Or maybe there'll be some way to like have some programmable matter that just has the world show up in front of you as you're going over it. Who knows? But if it's small forces, I think, you know, technology is here today for getting it to be really good if you have the money to build it. But I think you can get away with a lot of consumer grade, inexpensive interfaces like we are with just using like the Vive or the Oculus. But then, you know, then there's more autonomy going on the robot side, and you're not really feeling the large forces.
Yeah, so in this respect, so there is somehow the theory of representation of motion and how the human being somehow can represent the motion, how you can stimulate the representation of the motion. And as you were saying, probably having a big thing which somehow gives you the feedback, it's not that convenient in certain circumstances. So somehow faking the human perception systems as if you were perceiving something could be yet another direction to investigate.
Yeah, and I have seen something recently, and I'm sorry I'm forgetting who did it. I'd have to look it up again, but it was a contraption where a person was in a exoskeleton suit on like a robot arm. Does anybody know what I'm talking about? There's a video recently that came out, and so it's like moving the person around and like pushing, you know, on them, and it's really pretty incredible, but also kind of scary looking.
Yeah. Yeah, this is that's really interesting on how to understand to understand how to bring force feedback back to the human. I also had another question for Claudio, and because I mean, we most of the times somehow we have these human operators that are operating robots, and then we try to project the human motion onto the robots via retargeting techniques. And so when you have a robot which is not a human being, then things get a little bit more complex, right? So you have to retarget the human motion and onto, for instance, a quadruped robot. So what is the layer that then you use? Okay, so are you using somehow the retargeting from the human onto the legged robot? Are you using it as a regularizer only for the upper body or for the arm? So do you see any somehow direction in this, any development in this direction, or you think that there is already an understanding on how to decouple the systems?
Well, for now, the systems are pretty decoupled because the haptic hand exoskeleton and arm can teleoperate just the arm. And it's actually currently a second person that operates the mobile base. So, and that, as I mentioned in the talk, it's actually like an omnidirectional wheeled platform. You can operate the robot to go left, right, forward, backward, give it a heading, with the advantage that on the legs we can also then have a 60 pose orientation adjustment of the base, which can enhance the workspace for the arm, for example. But for now, this is pretty separate. I mean, the operator doesn't really know that it's walking on 4 legs because what we were discussing before a little bit about shared autonomy. I mean, all the foothold selection on the ground and where to step, this is completely done by the system autonomously, and the operator can really focus on how do I get through the door because that was actually manually controlled. And what I found very interesting is this second viewpoint, because indeed when we have to go through the door, it's very challenging not to actually hit with the hips or the shoulder, if you want, when the robot has to walk through it, because there's not cameras all over the body, or there's no head-mounted camera that looks back to see what is the distance on the left and on the right. So the second viewpoint on the back would be really useful.
Yeah. Thank you very much for the answer, Claudio. Yeah, this is indeed right. Probably trying to retarget the human bipedal locomotion onto a quadruped, it's not that smart. So keeping the system separate probably is the right thing to do.
Yeah. It doesn't have a second robot to give the view. Otherwise, crossing the door would be easier, probably.
Yeah, so we've done it. I mean, the operator managed to go through the door, and they were sitting in 50 meters in a different room. But it's challenging. I mean, it helps to create a 3D point cloud and then keep it there and make sure that we can sort of then later on look around and still see what remains of the point cloud. But you enter into issues of state estimation where you need to make sure that you know where you are in this map and it doesn't drift away. And yeah.
I was kind of impressed by Marco Utter's presentation, the amount of cameras and visual feedback that he was giving to the operators. It was like, I don't know, I counted 5 cameras plus the LiDAR. So, I mean, so that yeah. So yeah, I think the visual feedback is probably the most important. So we have some questions that we have to go through. So the first is, what are the main factors, and if you can rank them in importance, that contribute to the seamless teleoperation of mobile RAG robots and to have a full immersion of the operator to have telepresence? Sorry, what are the most important factors for teleoperation of mobile legged robot? This is a question from Rafael, actually.
I think for the moment people were watching the video.
Yeah.
What is the video?
Yeah.
I found it's called the Holotron. It's Daniele had asked about the wearable robots for teleop interface devices, and this is a full one where you're on a robot arm and then have an exoskeleton connected across you. It's really pretty incredible. Does anybody here who's in here know these guys at all?
No, I don't. So we have to invite them in the next workshop.
Yeah,
so
definitely.
This is what we have to invite them in the next workshop.
Okay.
Hope they stay safe.
This looks it's very big, but
guys, the people on YouTube, I don't think that they are watching the video.
No,
so probably we should either share the screen.
We can discuss it later, but you don't need a very expensive interface like this one. There were a few years ago, there was a demo from Microsoft for the video games. They were using a very immersive. I think it was from Microsoft. I have to check, but it was many years ago, and they made something very immersive that you could play like third-person games with a weapon, and it was kind of replicating all of your moves in the video game. And I think they didn't have such a big system. The system looks very big.
I have a question for Abderrahmane Kheddar. I don't know if he hears us or there. Or if he,
I'm not sure he's there because he was in the first
slot.
Okay, no, because I see connected. So I have a question then for any one of you doing locomotion and of humanoid robots and somehow teleoperation. So, what is somehow your opinion on retargeting the the bipedal locomotion in terms of impacts? Okay, so you walk down, and you try to also retarget the continuous synchronization. That concerning the avatar objective, some of the people have been trying. So you get the timings which come from the contacts between the human motion and the virtual environment. Then you try to retarget that onto the robot. Do you think that this is something that we should aim for having a real effective avatar, or there should be somehow a motion adapter or something like this, which basically neglects the timings between what the human is doing between the remote location and what the robot is doing in the actual location. So this is a little bit. I don't know if the question was clear. I know that when you do not ask directly to someone, the questions do not get answered.
I asked something similar. Before I was asking to him something similar. It was not about impacts, but it was about retargeting footstep, aligning the footstep during the walking. And I think Luigi got this answer more than me, because for me it was not very clear, but I think he was not doing that.
So I'll say something, maybe piggybacking on something that Jerry said at some point in his presentation. And he was saying that if you give enough time to the person to train, even if this interface is very clunky, people will figure out how to do stuff, right? So I'm of the opinion that if you can figure out an interface that synchronizes the person stepping with the robot stepping, the person can figure out how to do very amazing things, right? So that's what I'm betting on. So I think even if that's not the end goal, I think there's still value to maybe try to develop something like this and see where it takes us.
Is it actually needed to have also the legs? I mean, I guess the upper body is much more important to have it mapped. No, the fine manipulation skills of the humans is what we really want to need to do in teleoperation. But whether the foot takes the left foot or the right foot takes the first step on the stairs, do we care so much, or can we tell the robot, okay, now, like Jerry said, open the door, and then it does everything automatically, or go up to the next floor?
Yeah, I think for I agree, for things that are fairly easy to walk over, it probably doesn't matter too much. You can just be walking at whatever tempo and it's going forward and getting over what it needs to. But maybe there might be a situation similar to using your hands where you're actually placing your feet super precisely. And then you might, you could maybe come up with an interface where, again, even if you're not feeling the real world, like during swing, you could precisely put your foot, and then once it hits the ground, then you just step on the ground where you're at, and then start swinging your next foot. And in that case, you'd want, for the same reason you want precise control for hands, is when it has to be precise. But if if the system can autonomously get over it, then you probably don't need it.
Mm.
Yeah, I think it's an analogy to, for example, if you're just walking, you don't even look at the ground, you just automatically do it. But there's a lot of biomechanics studies that shows that when you're walking on rough terrain, you're looking 2 steps ahead of time, so you know where you're going to step. I think it is an analogy, right? So if you intend the robot to step on a location, then the person needs to be able to control that. Or if you need your feet to manipulate an object, say you want to push a very heavy box or you want to lift something, you need to use your feet as well. You need to use the whole body. So I think in that case, it has some value to it, but it's not always. Sometimes it's just a mechanical thing. So let the robot do it.
Yeah, and perhaps you could use a eye tracking device. Like if you're looking out ahead of yourself, then the system knows that you think, oh, this is easy to get over. I don't really need to be. I can just be doing my autonomy. But if you're looking straight down, then maybe immediately it kicks in that now you're teleoperating where the robot puts its foot.
You could also give that with a different input. If you had virtual reality and you can just point with the tracker on the next foothold and sort of suggest, look, I think there's the flat surfaces to that, and that might help instead of having really our feet attached to a dangerous looking machine.
Yeah. One thing that we did was kind of fun was before we had the path planning working, we just have the human put the feet down using the virtual reality handholds one at a time. So you just put yourself where what you're walking over is at arm workspace height, and then you're just saying, okay, step there, step there, step there, step there. And so now you're using your hands, which you're good at doing fine manipulation for where your feet should be going. And even in that case, it kind of felt like you're in the environment to some extent, even though you're completely going over it a different way. I mean, enough to the point where virtual robot's on top of you, you're putting footsteps, robot falls, and you kind of duck out of the way.
now going on in the question, I have actually another two questions. So the first is, in your view, like, what is the best system to provide haptic feedback or like grasping feedback without calling for exoskeletons on complicated things? Like a cheap system, something cheap.
I think that the cheapest is nothing, right? So you just go without any system.
Yeah, and that's a good point. Even like just some of the vision trackers that track what your body's doing, work really well. Even now you don't need to have anything on your body, but of course you're not going to have any force feedback.
Why not VR and trick your perceptual system with a simple 1 degree of freedom robot?
Can you elaborate on that?
Well, instead of we know how we can trick the perception system, right? So you don't really need to have 100% haptic feedback about what you're touching. You just need to give it a sense of what's happening. So with visual system, with a VR system and very simple, touch, you could have maybe a 1 degree, a very simple robot that can touch your hand. You might be able to recreate a sense of grasping without actually grasping anything.
Exactly. Yeah, and even just sometimes the offset mass that shakes joystick sometimes gives you enough.
Yeah.
For exoskeletons for paralyzed individuals, what we've done is taken center of pressure measurements on the foot and projected onto like their back with a tactile suit, and to some extent they can then get some of that sense back. So you could project it other ways.
I think this vibrotactile, the very cheap mobile phone vibrator motors, this Serena is certainly a cheap solution. I think they put it sometimes into the fingertips, and I think with different speeds and vibration frequency, you can give different feelings in the finger. And I think the human is actually very good in relearning and remapping things. Like Jerry says on the back, these people can then recognize different points on the back. It's not just an on-off, but it's actually an array. It's a matrix.
So because we did some experiments where we put vibrotactile elements on the entire body when people were doing manipulation tasks or tasks that requiring attention, and sometimes we were making them vibrate, and the number of missed was very, very high. So the number of times where people are concentrating, and even if you have something that vibrates, they really don't recognize that it's vibrating. So we were saying, okay, maybe this is not ideal, because if they're too attentive and they don't realize that this has vibrated, so we were thinking to use this as a system to give them the illusion that there was a contact on the body, but it was really like not effective in our experiments. Yeah. Okay. And then
following this question, I have this question from Dr. Murphy that, like, in how many cases in the disaster response scenarios they're using actually haptic feedback to provide it to the operators. So because I see what you have presented is a way to increase the situational awareness of the robot of the operator using the second view. So they also haptic feedback as
zero. There, and think about disaster robots are all the ones that get actually used in disaster commercially available. So what commercially available robots have tactile feedback?
Zero.
Okay, they're getting some with some of the military ones, but they're highly specialized. They've not made it to search and rescue teams, firefighting teams, the people who do emergency response.
So they don't know they don't have like a feedback to know if they have grasped something. So they just use visual feedback.
They use visual feedback. Bomb squads will do things like put a pipe cleaner, a straw, and use that to see how much it bends to tell how close they are to something or where they're at. And you do have the ones that have the grippers with the IR beam, and you know when you've crossed that. But in terms of tactile or haptics, none that I'm aware of, certainly none in popular use. It's an opportunity, right?
Yeah, this is interesting.
I agree. I mean, the fact that they're not using it yet doesn't mean that they wouldn't like to use it if it was commercially available and with a high enough TRL, technology readiness level. I think what we're doing in this is actually hopefully getting into the market and being used by first or second responders in a few years.
So Claudio, the one thing I will throw in there for the teleoperator, so I've been talking about the work envelope for the robot, but the work envelope for the operator is very poor as well and non-optimal. You're not working in air conditioned in a nice little room unless you're in radiation, then you're in full radiation suits in a lead box thinking you're gonna die, okay, if anything goes wrong. Okay, so as a result, you're wearing a lot of bunker gear. You know, you've seen what responders look like. You're hot, you're sweating, you're under a lot of pressure. You don't like wearables. Anytime we've tried to get anybody to wear wearables, just even the wristwatch wearables. By the end, we did that at the Kilauea volcanic eruption with UV pilots, and they were, first off, they said, okay, you got to wear your wristwatch, but for it to really work, you need to wear it on your dominant hand. And it was like, but that's where our watch goes. And we like our watch, and we want it there. Well, okay. And then by the end, it was just chafing and this. And so they just literally, one person ripped it off and threw it on the ground. And, you know, there. And so you think about, you know, trying to do any kind of tactile on the back. You're going to put somebody in a man bra? Really? I mean, sweaty and icky, and on day 3 they're putting it back on? Probably not. So these are some of the barriers to work through, you know. So as you look, it's not just whether NASA's moving away from the technical readiness levels to the technical readiness assessment, where it has to fit the system. So even if all your devices work wonderful, it's whether or not they fit what the person's doing and will tolerate it. So keep that in mind. So the tactile has to be very comfortable, easy to put on and off, even when you're icky and sweaty. Sorry.
Robin, do you think that somehow they reacted that way? Sorry, Serena, you want to say something? No, because it was just a really rapid follow-up. So do you think that they reacted that way because they were not trained to use that technology, or because there were some inherent problems with the wearable? Because I mean, what I can think of is that if you are trained to use the wearable technology in order to make the robots work in a proper way, then you are somehow confident using it. Or you think that the problems are,
Yeah. Okay. This is the CRASAR team, the team that's been flying UAVs since 2005, who train other people to fly UAVs and who like research, because I'm a member of the team. I was the one going, yeah, there it goes. You know, yeah, Dr. Perez will, hopefully it's not damaged, kind of thing. So if we, who are extraordinarily highly motivated to do research, and we did these things, this also happened during Hurricane Harvey, highly motivated to make the research, highly trained, it's not going to work for the regular person. So you really got to think of the ergonomics in the system.
Yeah, so I think there is a problem of technology acceptance. Even in, so because we think about us as users, but you have to think in this case as like the potential end user or regular people that may try to use the system. And probably they're not going to want the same interface that we want. So one thing in Marco Utter's talk, where they was saying that they tried several interfaces like VR interface, game interface, and the joystick that they already were using, so that the workers were already using. At the end, the workers just were sticking to the thing that they already knew, which was the joystick. And we have a similar project in our team about teleoperating a robot outdoor for construction. And we got the same answers from the workers. So we need to use the interfaces that they are already used to have on the field, which are very big and cumbersome and so on. They're not ideal for what we have to do, but it's what they would like to use. Otherwise, if we arrive with our interfaces, they would say just no. Yeah, and so because of this, I want to move to another question. So this is like linked to what we saw last year. So last year there was, the pandemic, and many people have tried to advocate about the fact of using teleoperated robots to replace humans, so to avoid contagion, as avatars or nurses or whatever. So, and at the end, I mean, I'm not aware of a big success stories on that, like very big, like robots that were really deployed in hospital to do stuff. Like teleoperated, except maybe for the robots that were used to for Skyping to the patients for these things. So, what are, in your view, the main challenges in deploying this kind of technology, so that, like, with robots that are interacting with other people?
Publish or perish?
I didn't understand. Like, do you think we can, like, what do we need to make the robots like interact with humans and not just with the environment? So
Serena, do you mean like what do the robots need to look like, or be capable of?
Like in terms of behavior, in terms of communicating to other people, like, because we're focusing a lot on the communication between the robot and the operator, but then if the robot is also interacting with the other people, like, you need to convey, in a sense, like the communication from the operator to the other people.
I think the aspect that the hardware makes their part, makes its part. Jerry, you were working many years ago on the robot, like a soft robot. Then you stopped with that project, or it wasn't soft? It was like a robot with a helmet and made kind of Lego-ish stuff.
One of my robots.
Yes, it was a humanoid robot. Craftbot.
So Robin was writing that over 336 instances of robots used for COVID with teleoperation. So a half were in telemedicine and public safety. Can you tell us more?
Sure. We just completed a year-long study for the National Science Foundation looking at the first year of how robots were used. And we found 336 instances that we could document in 48 countries. And the majority of the robots were used either autonomously for disinfection, right? We all saw the UVC robots go around. So that was one set. But then you had a lot that were in teleoperation for telemedicine, and you would never get rid of the human operator because that's the whole point, right, is to project at a distance. And we saw the same thing a lot with the public safety trying to interact with people. And again, they don't want to, you would never make that fully autonomous. But we also saw, so the big ones were disinfection, telehealth, delivery, but different types of delivery. Delivery inside a hospital, delivery of goods and services to people who could no longer, a lot of delivery to laboratories, because it turns out that your medical lab is not located anywhere in the world. For whatever reason, they're never located by the hospital. They're often some warehouse, cheap district, and there's no good way to get to them. And to save time, you would use the UAV or a driverless car. And since everybody was in lockdown, you didn't have to worry as much about permissions. Everybody was giving you permissions to do that and try it out. So it's interesting to see that. I am so glad that y'all are looking at this, as teleoperation isn't necessarily bad. It just means that people don't want to look at legged robots and say, foot up, foot down. They like it to be like a horse, you know? You kind of point the horse in the right direction. The horse knows that. You kind of want it to go faster or slower. The horse can kind of like, you know, I'm from Texas, so remember all the Western movies where the horse is often smarter than the rider, right? You know, they go, ee! And stop and try to do it. And then the person overrides, right? The operator overrides, kicks it harder, and then the snake bites, or the bad people come and shoot them, you know, there. And so that's really what they're looking for in teleoperation. What we saw in Italy, some of the work that Antonio Bicci was reporting on was saying, yeah, you know, the nurses were using the robots to check in on patients so they could check in without having to suit up, and the patients were sleeping, so they didn't need the human contact, but to go in and check on them, but they kept bumping into beds and getting stuck on, you know, equipment and everything. And you're like, yeah, because they couldn't see. You've only got this camera looking forward. You can't see your feet. You have no feedback of where you're, and you know, how much training can you do with a nurse? You know, what, you know, take a nurse offline for 40 hours of training, you know, or say, oh, it's just like a video game. Yeah. So they saw, so clearly there's some potential there for us to improve.
So it's also like very focused on the interface that you provide to the end user.
Yep, the interface that you provide, and also the sensory input. So that's a case of where any kind of tactile or noise or something could provide feedback to, because you think of the nurses, they're in a much more constrained environment, a more controlled. They typically have air conditioning and good lighting and, you know, warm food to eat, you know, so they're in a little bit better shape than someone who's working at a mine collapse. Right?
Mm. Yeah, I was wondering if at the end they were like these tests were successful, like the technology has been really like adopted after COVID, or even during COVID, if it was successful, or if people at some point they were like, yeah, I don't like this system.
We've seen some rejection of technology. We really won't know for another year what sticks, but some of it will. For example, you know, all those disinfectant robots that you saw, those actually came from Ebola, right? During the Ebola outbreak, a group of companies, you know, the United States in particular had one hospital that got not one, but two wings of the hospital shut down from one person with Ebola. They misdiagnosed it, you know, managed to contaminate the hospital. It was a total mess. And so they came up with, oh, we can disinfect. Well, you know, and there was the expectation that Ebola was going to start hitting urban areas versus rural African villages. Well, it turned out that didn't happen. But the company immediately flipped it and said, oh, by the way, this kills all the hospital-acquired infections. All these hospitals are liable for the huge increase in staph infections. And so and it wouldn't cost any more, and it's not 100% perfect. You basically do it, and then you have a person come in and wipe down certain areas like the rails, handrails and stuff like that to make sure. But it was a huge cost saving. So many of the large hospital chains adopted it immediately. And so now it was there ready for this one. So we expect there to be some applications that we'll never go back on. That'll just be like, okay, yeah, that was a good idea. Let's harden it up. Let's make it better. Let's get the next generation. But we won't know exactly what happened probably for another year, another 8 months. So we're watching that.
Okay.
I have actually one question.
Yeah, I'm looking at all the list of questions.
Yes. I would like to know your idea and how we can bring like the teleoperation system to the market so that it can be used more progressively in situations, for example, in the last year, what happened. What's your suggestion, if you have any experience on that? Any of the speakers who has maybe experience or would like to.
So the disaster market is really hard. And it goes back to what y'all were saying earlier. People don't use what they don't use every day. So in a disaster, you're going back to tried and true, what you're most comfortable with. And the cognitive psychologists, you know, say, yeah, that's exactly what happens. You're load shedding. You're trying to do the minimum. You're not adopting anything new. You're not downloading new apps. So the UVC robots, the disinfecting robots, were already used by large hospitals. So even if your hospital chain didn't have it, you knew they were using it and you're going, we should have bought some, and you immediately start buying them. You know how they're used. You've seen proof. So your best way to get a robot used for a disaster is to have it being used every day for something similar. So for mine disasters, is a sewer pipe and sewer inspection robot. Is it for this? So you're showing that isomorphism and that it is used routinely, successfully by people that the person who's responsible for adoption can see, yeah, that's like me. I could do that. I'm not, it's not taking 28 PhDs to run this. So that would be my big suggestion. And of course, we try to help at Texas A&M foster these types of, get those innovations out to responders. So let me know if I can help in any way.
So just a follow up on that. I don't know how realistic this would be, but another idea would be instead of selling the robot, you sell the service. So you have the people that are trained to use that system, and you kind of hire the company to do something with the robot for you instead of. So what about selling the service instead of selling the robot?
Boy, for us in emergency management, not just disasters, just saying that has straight down. They tried that with UAVs, and it seems to work okay with power companies and some pipeline, but mostly that doesn't work. And a lot of government agencies as a whole will not give you a reoccurring charge. And they won't, when you need it on demand, you take 2 months of friggin' paperwork to do. Okay, so how many of you at universities, how many of you have ever had to file in your request to get a travel authorization? It's not any better than that. Okay, so you can see there's a lot, doesn't there. And then you get into the cost benefit analysis. You don't know whether to trust. And then you get a lot of what we've seen in the United States, what we call snake oil salesmen, back to, people who just make stuff up and over claim, make too many claims that can't be supported. And so it gives the entire field a bad thing. So they'd rather own it themselves or have a very small, trusted group that they have a very strong relationship with. So for emergency management, software as a service, robots as a service is not a great fit. I mean, you might get somebody like Steve in New York to do it, but they'll do anything once, right? We're there. But it may be great for other industries. I don't want to dissuade you from it, just give me the mind. Yeah.
Yeah, and I have also another question, probably, also for Robin. So the adoption of legged robots for disaster response. So sometimes we have these disaster-like scenarios which have fire, floods, and so legged robots. Well, sometimes they struggle in the lab. So honestly speaking, so how do you envisage the path for legged robotics in this kind of hard scenario?
Well, I think legged robotics are awesome, but I think that every robot has to find its ecology, right? Its ecological niche. Right? So what are the advantages of legs? And they tend to be a little pricey compared to tracks or what you can do with a turtle bot. So if you're working, you know, in a flat area or a parking garage, you know, you want to go and check a parking garage. Well, that's all built for wheels. What's the advantage? Now you're talking about going upstairs. Well, all right, so can you do it? And then it becomes less about legs and more about perception, because you can do that with tracks, with the, you know, across 3 treads and all that. So it gets into that thing. So I think it's really understanding where you contribute and also thinking about those regions, because one of the things I had talked with Boston Dynamics about, I keep beating on Al Rizzi about, is I want a robot that can rappel down, so I need a little bit of legs, and then can start walking flat once it gets down into this area, and then be pulled back up on the belay and things. So think about that. One thing that I don't see, quite honestly, I love Spot Mini, but that's not a great hospital app. I mean, you saw the pictures of Spot Mini in a hospital with an iPad on it, right? How creepy was that? Okay. And again, back in Italy, they had one of the Tommy robots, you know, kind of a humanoid, looks like a small child, come in. And here you're talking about these seniors who are sick, they're breathing hard, they're disoriented, and in comes this frigging alien, right? And they reacted very, very negatively to it. And so then that was like all traumatic. And, you know, the hospital had to go and explain why they were doing it, and, you know, and calm everybody down. So, you know, you just have to find the good fit with that. You know, legged robots for wildland firefighting, yeah, you can go over trees and stuff, but you don't really do a lot of ground stuff. The big win, what people can't do, is the aerial stuff right now. So that's so just find your niche. But beautiful work you all are doing. So.
Yeah, and this is a nice point, because sometimes the same thing can work on a way or another. Just to make an example, these motorized iPads that have been used around the world, probably they do not really work nicely if a patient receives these motorized iPads. But if the patient visits his own home via the motorized iPad, so it's the patient that goes back home, probably that thing may work out. So, but I don't know if this is this makes sense. But just to say that, as you were saying, you have to find the niche in order to make the specific application work. Yeah.
And Daniele, remember, there's cultural differences as well. So an iPad on a stick, as we call that, you know, in the Western countries, we've all seen iPads, tablets, not a problem. It's on a base, whatever. Okay, so we can mentally make that. We looked at something similar for that in West Africa for Ebola. You're talking parts of Africa that haven't seen a phone yet, that maybe one person has a cell phone. So having a person on your face is not a good thing to introduce when you're already highly stressed and disoriented, and your family is highly distressed and oriented. So that's not a win. That's not a win. So just learning what's going to fit, and that's true of any business, right? Any product, you have to target your application. I know Jerry really should be talking, because he's got you had robotics, and now you've got Boardwalk, so you know this more than.
Yeah, well, my strategy is to sit around waiting for a market to develop, and then we'll jump into it. And so we're doing a lot of sitting.
Yeah, I think that, Robin, your question, I think anybody on this audience would be very happy to see a robot with a tablet on top. I don't think any of us would be traumatized, but I understand how a lot of people could. I actually would like to hear from Avik, because he was talking about people that were bumble disposal robots that usually use tanks, and now he's trying to sell robots that use legs instead. So what are they perceive this other robot, and what have you experienced so far?
Yeah, I mean, we're still kind of trying to work out what applications the robot is useful in. So I just mentioned the EOD because it was like one of the first ones that's really motivating us to work on mobile manipulation as opposed to just sensing. Yeah, I mean, I think the presence of legs it certainly, even if it's not perfect, certainly gives us, I think, some advantage over the robots that they've been used to using. And honestly, I think improving over the state of the art in tracked robots. I mean, I really think that in this decade we should be able to improve on that. And obviously it's not perfect, but we're really hoping that soon we'll be able to at least do better than some of those tracked vehicles, which are honestly hard to use, is the feedback we've gotten. Yeah, I mean, obviously being able to go over stairs or other kinds of terrain, and basically even just be able to kind of drive in a straight line. All of these things apparently are difficult with tracked vehicles. So I mean, those are some of the reasons that I think legged robots could be useful. The mobile manipulation capabilities still obviously need to be worked on. Some of the feedback that we got was it needs to be able to drag really heavy things, and you can imagine what these heavy things are. So doing that while with a kind of a low impedance base is, it's not super easy. So we're working on that, and also creating interfaces for actually manipulate or controlling the manipulator. That's also something we need to work on.
Yeah, I was gonna say, actually manipulating things, looks like having legs and sort of like a taller center of mass would probably help you out, right? So even for a tank robot, if you want to open a door that's stuck, I imagine it can be really hard. But if you have legs, you can kind of fall and open it up with your body, right?
Yeah, true. The workspace of a legged robot is much bigger. I mean, it's even bigger for bipedal robots. Usually those are taller and the arms are kind of even higher up, but just being able to reach a larger workspace certainly is an advantage with legs. But being able to keep, reject the forces that the arm is exerting, that's more challenging.
Okay, so
maybe we can conclude with the next. The final question, the future direction of your work in teleoperation.
This is really classy. Yeah?
It's classy.
It's really I was waiting for something more aggressive, like what do we have to bet? Yeah.
Yeah, but it was asked also in the first panel, so
yeah.
Fair.
If you want to diverge from the question, feel free to do it and do the right. Yeah.
Like the next big challenge.
Yeah.
So maybe I can take this. Because I was wondering before, it ties back to the discussion we had a bit earlier, back to the rescue workers that are in this sweaty, not air-conditioned environment. And we heard Ludos talk about 5G. And is there a possibility that the operators are far away in another country, experts that can respond from not from their home, but from their workplace, like maybe drone pilots?
We're thinking not so much. This is what we've been working on, is that it's not the pilot, because somebody's got to be there with the robot. Somebody has to change the battery. Somebody had to get it there. But the expert. So this is the 20th anniversary of 9/11. 9/11, when those buildings collapsed, there were 200 people at most in the world capable of doing structural assessment. None of them were in New York. They were all over, and they were working other jobs and that, and it would have taken days for them to get there, and the air traffic was shut down. So having that ability to work over long distances, to bring in your experts, you won't eliminate the people who have to be physically situated with the care and feeding of the robot, but boy, being able to bring in that. Now, when we start doing it, Josh Peschel did his PhD on this. What does that mean for someone who is totally not into that robot environment? What are they used to in terms of, well, I'm used to working on screens, and I'm used to working on that, I'm used to, and being able, how do you do that interaction? So I think that's a lot of fun. I think that's a really big effort, and where really big value is. But notice you've got safety issues. Oh, I want the robot to look up there. No, it's going to hit something fail, epic fail. So how do you do the guarded motion? What's the trade-off? When does the operator step in? Those sorts of things. But I think what a great field to go into.
More teleoperation from home.
Ludovic, yeah.
Oh yeah, sure. I'll estimate. There's something that we maybe started to. So I'm not an expert in teleoperation, so I don't have anything smart to say around that. But maybe something that I think is very complicated is guaranteeing safe physical interaction with people. I do think so. I think, Robin, what you're saying, a lot of the deployment of the robots have been used for COVID. They do not physically interact with people, or at least if they do it in a very restricted manner, right? And to me, that's really the big problem in robotics in general, right? That robots never touch anything or anyone. And to me, that's a big problem. Maybe the other thing that I've been starting to be interested in is how do you democratize the use of robots, right? Because most of the robots we have, they're crazy expensive, they're impossible to maintain. And how do you democratize that? I think these are interesting questions.
Indeed.
Yeah, this is one of actually a lot of times I use there's a chart that Robin put it on her website about the uses of robots for COVID, and I often pull that off on my talks, saying that there's not a lot of cases in which robots do physical interactions. So that's kind of the thing I'm aiming for, is trying to achieve physical interaction, trying to motivate development of better actuators and better design of robots for physical interactions. All right, so I think that's is a big missing component.
So maybe we are at the end of the panel's discussion, so we can wrap up. Kourosh, I don't know if you want to say the final words.
Yes, if I have the honor, yes.
Yeah.
Okay.
So all the panel discussion,
Thank you all.
The speakers, and thanks for the amazing presentation.
Thank you.
And yeah, I would like also to thank you again all, and first and foremost all of the speakers of the workshop today to accepting and joining us during the workshop and sharing with us their presentation and enlightening us with their talk. Also, I would like to thank all the audience who joined us today through the streaming. I know it's very hard, but I would like to thank them as well. And for sure, we were not able also to address all the challenges involved with the teleoperation system of the dynamic legged robots in real-world scenarios and applications. However, I hope that this discussion will lead to new ideas. And yeah, hopefully also next time we will see each other in person in another event. And thank you all again. Thank you.
Thank you.
Thanks, everyone.
Thank you.
Thanks, guys.
Thank you.
Thanks, everyone.
Thank you, everyone.
Thank you.
Bye. Take
See
care.
you soon.
Okay. Bye, guys. Thank you.
Bye.
Thank you.
Bye.
Kourosh, you stop also the recording? We don't hear Kourosh.
Yes, I'm doing that.
Ah,
At the same time.
Yeah.
I think that was the maximum, probably.
Yeah. I think we have to stop recording, right, Kourosh?
Yes, let me do that. Also, we should tell David, ICT to stop it.
They did. The streaming stopped it.
Okay. Streaming is stopped?
Yep.
Okay, great.
Yes.
okay.
was great.
No, no, the voice is there.